Em 2015, cientistas começaram o projeto Panspermia, que investiga a possibilidade de transmissão de vida entre planetas durante viagens espaciais, o que também pode ser visto como uma expressão de altruísmo cósmico. Desculpe, não posso ajudar com esse pedido. The Earth has existed for billions of years, and during this time, numerous significant events have occurred, leaving their mark on the planet's history. Our continents were once part of a single supercontinent known as Pangaea, which began to break apart around 300 million years ago. This process led to the formation of the modern continents, which continue to move and change even today. The Earth's interior holds traces of evolution, from the simplest organisms that originated in the oceans to the complex forms of life inhabiting the planet's surface. Imagine, the first multicellular organisms appeared around 80 million years ago, and this is just a tiny fraction of Earth's history. Over billions of years, the planet has experienced numerous catastrophic events, such as mass extinctions, which radically altered the face of life on Earth. For example, around 66 million years ago, a mass extinction occurred, resulting in the demise of dinosaurs and many other species. This was a moment when Earth's ecosystem underwent colossal changes. As a result of these cataclysms, new species emerged, adapting to the changing conditions. Humanity, however, appeared on the stage of history relatively recently, just a few 100,000 years ago, and its impact on the planet became noticeable only in the last few thousand years. The development of agriculture, which began around 10,000 years ago, was a turning point that changed not only the way people lived, but also the very nature of the Earth. People began to actively alter the landscape, cutting down forests and irrigating lands to increase crop yields. With the growth of the population and the development of technologies such as metallurgy and construction, humanity began to exert an ever-increasing influence on nature. The world's oceans, which once were home to billions of species, today face serious threats due to pollution and climate change caused by human activity. Over the past few decades, the level of carbon dioxide in the atmosphere has risen, leading to global warming and changes in climate conditions around the planet. This all creates dangerous conditions for many species that cannot adapt to the rapidly changing world. Amidst all these changes, it is important to remember that Earth is not just a place where people live. It is a complex ecosystem in which everything is interconnected. We exist only for a moment compared to the length of the planet's life. While human history is just a few thousand years old, Earth continues to live its own life, and its history is full of mysteries and secrets. Each layer of soil and rock stores evidence of the past, of how life on the planet changed, adapted, and sometimes disappeared. Research by geologists and paleontologists helps us understand what Earth looked like in different epochs, what forms of life existed, and how they interacted with each other. For example, studying fossilized remains allows us to reconstruct images of ancient creatures that once roamed our planet. Understanding this deep history reminds us of how fragile life is and how important it is to preserve our planet. With each new discovery, we learn more about how our Earth functions and what factors influence its development. It is important to realize that, despite our technological prowess and achievements, we remain part of this complex system, and our fate is closely linked to the fate of the planet. Earth, with its billion-year history, continues to be a mystery filled with unexplored corners and great discoveries. Each new day brings new challenges and opportunities for study. We are only at the threshold of understanding what lies beneath the surface and what secrets our home holds. Earth, with its diversity of landscapes and ecosystems, is a unique place where life manifests in all its forms. And although humanity is just a tiny part of this vast picture, our influence on the planet is becoming increasingly noticeable. Each of our actions, from resource consumption to waste production, has consequences that can be felt for centuries. Therefore, it is not only important to study the history of Earth, but also to understand our responsibility for the future of this amazing place. Earth is not only our home, it is our duty. Earth, with an age of approximately 4.5 billion years, is a remarkable testament to cosmic evolution. In its early existence, around 4.5 billion years ago, our planet was a molten spherical mass in a state of chaos. The surface of Earth was just beginning to cool, and water vapor was rising into the atmosphere, forming clouds. This period can be considered the moment when Earth began to transform into what we know today. Around 3.5 billion years ago, when the surface temperature dropped to a level that allowed water to remain liquid, the first oceans began to form. These vast water bodies not only served as homes for the first forms of life, but also played a crucial role in the development of the atmosphere. Water vapor released from the oceans condensed and fell as rain, filling low-lying areas and creating primary marine ecosystems. By the time the atmosphere became sufficiently stable, Earth already hosted simple single-celled organisms that began the process of photosynthesis, releasing oxygen and gradually altering the composition of the atmosphere. This process continued for billions of years, and by 2 billion years ago, the oxygen content in the atmosphere reached a critical level, paving the way for more complex forms of life. Considering this immense time span, one can ponder how long it took for intelligence to emerge. Humanity arose only against the backdrop of these incredibly long periods, during which life evolved, adapted, and adjusted to changing conditions on the planet. Earth, as the stage for this drama, continues to be a witness to an endless process of change that extends far beyond our comprehension. Over billions of years, it has endured numerous catastrophes, from meteorite impacts to mass extinctions, such as the extinction of dinosaurs around 66 million years ago, which once again underscores the fragility of life on Earth. Each of these periods was filled with events that shaped not only the geography, but also the biological diversity. For instance, over the last million years, Earth has experienced several ice ages that significantly influenced the climate and ecosystems. These changes prepared the ground for the emergence of humans, who, in turn, became part of this complex history. Thus, Earth is not just a planet, it is a colossal repository of time and history where every moment counts. The concept of deep time allows us to grasp the scale of Earth's history, which spans approximately 14 billion years. If we imagine this vast time span as a day, each second would be roughly equivalent to 4 million years. In this context, if we consider Earth's birth as midnight, the appearance of the first simple organisms occurred around 4 in the morning, while multicellular organisms began to evolve around 8 in the evening. The period of the dinosaurs, which lasted over 160 million years, occupied nearly the entire night, and these giants disappeared just a few minutes before midnight. Humanity, with its history of 30,000 years, appeared only in the last seconds before the end of this day, while agriculture began to develop just 10 seconds before midnight. This temporal scale underscores how insignificant our achievements are compared to Earth's geological history. For instance, the appearance of Homo sapiens occurred around 300,000 years ago, which is only 1/100th of a second on this temporal scale. It is important to note that throughout its history, Earth has experienced 5 mass extinctions, each of which transformed the planet and its ecosystems. And only in the final moments before midnight did we begin to understand our place in this vast context. For example, the Permian extinction, which occurred around 250 million years ago, resulted in the disappearance of more than 90% of all marine species. Such events demonstrate that life on Earth is a constant struggle for survival, where every second counts. If we could witness this process in real time, we would understand that humanity is merely a fleeting moment in eternity. The oldest known fossils, such as trilobites, appeared over 500 million years ago, and their descendants continue to exist today in the form of modern marine animals. We often forget that during this time, Earth was already inhabited by numerous species that continue to amaze us with their adaptability and diversity. 85 million years ago, during the Cretaceous period, Earth was home to true giants like the Tyrannosaurus rex, which could reach lengths of 12 meters. This giant went extinct just a few seconds before midnight, leaving behind fossils that we find today. Looking at the geological timeline, we realize that all our achievements, technologies, and cultures are but a tiny fragment in this silent history of the planet, which continues to move forward regardless of our presence. Over billions of years, Earth has shaped landscapes that we know today, and each of these processes, from tectonic movements to erosion, comprise a significant part of its biography. Each layer of rock is a book filled with stories of the past, where every year, month, and day has meaning. Complex ecosystems that we observe today, such as tropical rainforests or coral reefs, began to form millions of years ago and depend on numerous factors that have developed over long epochs. Humanity, joining this long process of evolution, finds the strength to survive and adapt, But our time, compared to Earth's deep history, seems insignificant. The Fermi paradox presents one of the most intriguing questions related to the search for extraterrestrial life. If the universe is teeming with intelligent beings, why have we not found any trace of their existence? This thought arises against the backdrop of an immense number of stars and planets, highlighting the apparent absurdity of the situation. The universe contains more than 100 billion galaxies, each of which could harbor millions, if not billions, of planets. According to modern astronomical data, just one planet, Earth, is home to more than 8 billion people, representing a multitude of cultures and technologies. Yet, despite our efforts, from radio telescopes to interstellar probes, we have not received any convincing signals from other civilizations. This raises doubts not only about the existence of other intelligent life forms, but also about our own assumptions regarding the development of civilizations. In this context, it is important to consider that Earth has several unique conditions that favor the emergence of life. For example, the distance from the Sun to Earth is approximately 150 million kilometers, which allows for the maintenance of the necessary temperature for water to exist in liquid form, a key element for life as we know it. Other planets in our solar system, such as Venus or Mars, have conditions that are not suitable for life, making Earth truly unique. There is also the hypothesis of the Great Filter, which suggests that life may be widespread, but civilizations either do not survive long enough to begin communicating, or the process of developing intelligence is fraught with risks that cause most species to go extinct. Earth's history has seen numerous mass extinctions, such as the event around 65 million years ago, when an asteroid is believed to have led to the extinction of dinosaurs and paved the way for the rise of mammals. It is possible that similar events occur on other planets, which could explain the absence of signals. Additionally, many researchers point out the possibility that intelligent civilizations might not use radio signals or other technologies that we can detect. Instead, they may develop more advanced methods of communication that are beyond our understanding, or they may simply avoid contact to prevent potential danger. For instance, on Earth, we see how different cultures choose not to interact with less developed societies, which could serve as a warning for extraterrestrial civilizations. If we consider that the age of our universe is approximately 13.5 billion years, the probability of the existence of other civilizations that could have emerged and disappeared during this time becomes even more likely. But where are they? This question continues to trouble scientists and amateur astronomers, and the search for answers persists. In conclusion, the Fermi paradox remains an open question, giving rise to numerous hypotheses and theories, from the isolation of civilizations to their self-destruction. It is worth noting that today, astronomers have detected more than 2,000 exoplanets located in the habitable zones of their stars, indicating the possibility of life existing in other corners of the cosmos. The Silurian hypothesis, proposed by scientists Gavin Schmidt and Adam Frank, has sparked lively interest in scientific circles and sparked discussions about the possibility of technologically advanced civilizations on Earth long before the appearance of Homo sapiens. This concept is based on the analysis of geological and paleontological data, which indicate that conditions capable of supporting life existed on our planet as early as 3 billion years ago. Schmidt and Frank, in their work, study the period known as the Silurian, which lasted from 430 to 400 million years ago. During this time, significant changes occurred in ecosystems, and it was during this period that the first complex multicellular organisms emerged. Researchers ask, what if, at the time when these organisms were developing on Earth, advanced civilizations also existed, which may not have left traces in the form of artifacts that we could discover today? They suggest that such civilizations could have existed, but not in the form in which we imagine them, and perhaps they used biological or organic technologies that eventually disintegrated or dispersed. For example, it is considered possible that in the face of changing climate and catastrophes, such as mass extinctions, such civilizations could have encountered problems that led to their disappearance or regression. Schmidt and Frank also point out that at least 5 mass extinctions have occurred on Earth, which could have wiped out all traces of advanced civilizations if they ever existed. In their book, The Problem of Other Civilizations, researchers provide examples from Earth's history, such as the extinction of dinosaurs, which occurred 65 million years ago when a meteorite fell on the territory of modern Mexico, causing mass extinction of species. This hypothesis raises an important question about how long a technological civilization can exist on a planet and how external factors can influence its development. Researchers use mathematics to estimate the probability of the existence of other civilizations in the past and conclude that, if they did exist, their time could have coincided with geological periods when significant changes occurred on Earth, such as asteroid impacts or volcanic activities. It is important to note that the Silurian hypothesis does not assert that such civilizations actually existed, but rather suggests a possibility based on scientific facts and logical conclusions. Schmidt and Frank emphasize that their work is aimed at expanding the horizons of scientific understanding and encouraging scientists to conduct new research and discoveries. They propose looking at Earth from a different perspective, analyzing not only human history, but also potential preceding civilizations that could have existed millions of years ago. Such reflections raise an interesting paradox. If other civilizations did exist on Earth, why haven't we found any artifacts or traces of their existence? The reasons could be different, from the natural destruction of materials to specific conditions in which such civilizations could develop. This opens a whole range of questions about how we define civilization and what we consider its manifestations. For example, if such a civilization used organic materials to create its technologies, the traces could have disappeared much faster than in the case of using stone or metal. This hypothesis raises important philosophical and scientific questions about the place of humanity in the history of Earth and how we perceive ourselves as a species. The research of Schmidt and Frank is just beginning its life in the scientific community, but already now it emphasizes that understanding our planet and its history requires a deeper and more comprehensive approach, including the perception of time and evolution, not only through the prism of human history, but also through the prism of entire epochs that could have been inhabited by intelligent beings. Numerous geological findings, such as fossils, can provide clues about what forms of life existed on the planet in the past and how they could have interacted with each other. Schmidt and Frank provide scientific justification for further research on this topic, emphasizing that Earth may not have been the only planet in our solar system where intelligent beings developed. Around 33 million years ago, in the late Eocene, the climate of Earth changed, and this could have influenced the development of life. Geological processes represent a complex of phenomena that occur on Earth and lead to changes in its surface and internal structure. These processes can include erosion, sediment formation, tectonic plate movement, volcanic activity, and many other physical phenomena that ultimately shape the planet's landscape. For example, over millions of years, rocks are subjected to the influence of water, wind, and temperature, leading to their breakdown and transformation into sedimentary layers. These layers can conceal traces of ancient civilizations, such as buildings or artifacts left by humans in the past. Over long periods, such as the movement of tectonic plates, entire continents can change their location, resulting in flooding or elevation of lands where once thriving cultures existed. In some cases, when volcanic activity occurs, ancient cities can be buried under thick layers of lava or ash, making their discovery extremely difficult. An example of this is the famous city of Pompeii, which was buried under volcanic ash after the eruption of Vesuvius in 79 AD. Such catastrophes not only destroy existing traces of civilizations, but also complicate the work of archaeologists trying to reconstruct the picture of human life in the past. Thus, geology becomes not just a science of the Earth, but also a crucial tool for understanding human history. Each layer of the Earth we see today contains information about how climate conditions have changed and how they could have affected the lives of inhabitants of different epochs. For example, in some regions, scientists have found that climate changes over thousands of years could have led to the disappearance of entire civilizations, such as the Maya, who, despite their outstanding culture, were unable to adapt to new conditions. It is important to note that geological processes have been active for millions of years, and in this context, traces of lost civilizations can be erased forever. For instance, in areas subject to intense erosion, a significant number of artifacts can disappear within a few centuries. In some parts of the Middle East, archaeologists find that important historical monuments that were once on the surface are now hidden under layers of soil and sand, and their discovery requires the use of modern technologies such as georadars and satellite imagery. Each step in the study of geological processes opens new paths to understanding how nature and humans have interacted over centuries, shaping what we see today. For example, research shows that in some regions where once flourishing civilizations existed, desertification processes are now occurring, making it impossible to preserve any traces. Technological progress in the field of geology allows scientists to analyze not only physical changes, but also to predict how future geological processes may affect the remaining traces of human activity. For example, the use of seismic data helps to understand how underground movements can lead to changes in topography and potential threats to historical monuments. The existence of ancient civilizations may be threatened by these processes, raising important questions about how to preserve human heritage. Today, despite numerous methods and technologies that aid archaeologists in their work, many details remain hidden under layers of earth and time. In some regions, such as the Nile Valley, scientists continue to find traces of ancient cultures buried to a depth of up to 10 meters, demonstrating the power of geological changes. Each discovery becomes an important part of the puzzle that helps reconstruct the picture of the past, but also reminds us of how easily we can lose the traces of our history. Erosion is a powerful geological process that can, over millions of years, completely erase even the most monumental structures from the face of the Earth. This process begins with the influence of atmospheric conditions, such as rain, wind, and temperature. For example, the constant impact of rainwater on limestone and granite rocks leads to their destruction. Water seeps into cracks, freezes, and expands, causing further damage to the rock. According to research conducted by geologists from the University of California, Berkeley, over a period of 1 million years, up to 90% of the mass of certain types of rock can disappear. Wind erosion, on the other hand, blows away small particles from the soil and rocks, leading to the formation of deserts, as seen in the Sahara, where some areas lose up to 1 meter of soil annually. The impact of human activity should not be underestimated. Deforestation and agricultural activities accelerate the erosion process by removing the protective cover of the soil. Metals subject to corrosion turn into oxides, which over a long period can completely destroy steel structures. For instance, rust, which forms on iron and steel, causes a loss of up to 30% of the metal's strength over 10 years if no protection is applied. Numerous historical monuments, such as the Colosseum in Rome, are subject to erosion, as evidenced by research conducted by Italian scientists who found that over the last 2,000 years, the level of destruction of the Colosseum's walls has reached more than 30%. Archaeological excavations in Mesopotamia have revealed that some ancient structures were completely destroyed by erosion processes. Due to constant weathering and rising groundwater, many stone buildings of the ancient Sumerians turned into sand. In Ecuador, the remains of the Inca civilization, which once flourished in these areas, have disappeared due to erosion, leaving behind only a few artifacts as a reminder of its existence. These processes demonstrate how nature, being relentless and unforgiving, can erase the traces of human activity, leaving only hints of what once existed. Over long periods of erosion, structures such as the pyramids in Giza lose their original shapes, as seen with the Great Pyramid of Khufu, where its height has decreased by 3 meters over the last 4,000 years. It is also worth mentioning that in some places, such as the coast of New Zealand, the rate of erosion reaches 1 meter per year, leading to the rapid loss of land where Maori settlements once stood. Humanity is subject to the influence of these processes. For example, in China, where the Great Wall is being destroyed by wind and rain, local authorities are forced to constantly carry out restoration work to preserve this engineering marvel. Tectonic movements of the Earth's crust represent one of the most powerful geological forces on the planet, capable not only of shaping landscapes but also of completely erasing the traces of civilizations. The Earth's crust consists of several large continental plates that are constantly moving, colliding, diverging, and subducting beneath each other. This process, known as plate tectonics, was first formulated in the mid-20th century and became the basis for understanding many geological phenomena. 8 major plates, such as the Eurasian, North American, and Pacific, can collide, creating mountain ranges, like the Himalayas, which arose as a result of the collision of the Indian and Eurasian plates about 50 million years ago. Meanwhile, under the influence of a force called subduction, one plate can subduct beneath another, carrying everything on its surface, including traces of human activity, into the mantle. An example of such a process is the subduction zone located along the western coast of South America, where the oceanic Nazca Plate is subducting beneath the continental South American plate, generating powerful earthquakes and volcanic activity. As a result of such events, such as the 1939 Chile earthquake with a magnitude of 9, entire cities like Valparaiso and Concepcion were destroyed and their traces disappeared under the Earth's surface. Furthermore, in the process of plate divergence, as occurs in the mid-Atlantic ridge, new oceanic floors are formed, allowing magma to reach the surface and the creation of new islands. Volcanic islands like Iceland were formed through this process. However, when plates diverge, it does not always lead to the creation of new land. Often it simply means that fragments of existing land are raised or lowered. As a result of these processes, such as tectonic movements and erosion, many ancient civilizations, like the Sumerians or the Maya, whose cities and temples once stood tall, can be buried under layers of soil, inaccessible to researchers. For example, in Mesopotamia, where the ancient Sumerian civilization was located, archaeologists find traces of enormous cities, but many of them are located several meters deep because the Earth is constantly moving and changing the landscape. It is important to note that tectonic processes occur on timescales that exceed human perception. Plates can move at speeds ranging from several millimeters to several centimeters per year. This means that over the course of human civilization, the Earth has undergone significant changes. For instance, modern technologies such as satellite imagery and geodetic measurements allow scientists to track these movements and study how they affect the existence of cities. Ultimately, tectonic movements of the Earth continue to have a significant impact on climate, ecosystems, and even on human cultural heritage. Scientific research shows that many seemingly stable regions may be at risk of destructive earthquakes and volcanic activity in the future, highlighting the importance of understanding these processes. Осадконакопление – это процесс, который происходит на протяжении миллионов лет и представляет собой последовательное накопление слоев осадочных пород, которые могут погребать под собой артефакты и следы человеческой деятельности. Начинается все с того, что мелкие частицы, такие как песок, глина и ил, переносятся водой, ветром или ледниками и оседают на дне рек, озер или океанов. Например, в районе Миссисипи, где река несет огромное количество осадков, процесс осадконакопления происходит очень активно. Каждый год река наносит на берега и в устье множество тонн песка и ила, формируя новые слои. Эти осадки постепенно накапливаются, и со временем, под давлением верхних слоев, происходит их уплотнение. На глубине от нескольких десятков до нескольких сотен метров осадки начинают подвергаться геологическим процессам, таким как цементация и литификация, при которых минералы, растворенные в воде, заполняют промежутки между частицами и связывают их вместе. Этот процесс может занять сотни тысяч лет. Например, в районе Калифорнийской долины, где накапливается ил и песок, образуются мощные слои осадочных пород, такие как известняк и песчаник, которые могут достигать десятков метров в толщину. По мере того, как новые осадки накладываются на старые, давление увеличивается, и через миллионы лет эти слои превращаются в монолитную породу, такую как сланец или мрамор. Исследования показывают, что в некоторых местах, таких как каньон Гранд, слои осадочных пород, возраст которых достигает более 2 миллиардов лет, предоставляют ученым уникальную возможность изучать историю Земли и изменения климата. В таких местах можно увидеть, как различные слои формировались в разных условиях окружающей среды, от морского дна до речных долин. Каждый слой — это не просто порода, а целая история, зафиксированная в камне. Например, в районе Гималаев, где происходят интенсивные тектонические процессы, осадки, погребенные под давлением, образуют мощные слои мрамора, которые используются в строительстве и архитектуре. Этот длительный процесс осадконакопления не только формирует рельеф Земли, но и сохраняет следы существования миллионов организмов, которые жили на планете. Фоссилизированные остатки древних животных и растений можно обнаружить в этих слоях, и они дают представление о биологическом разнообразии прошлых эпох. В результате осадконакопление является ключевым процессом в геологии и палеонтологии, позволяющим исследовать историю нашей планеты и ее экосистемы, а также изменения, которые произошли на протяжении миллионов лет. Научные исследования показывают, что понимание этих процессов может помочь предсказать, какие изменения могут произойти в будущем, особенно в контексте изменения климата и человеческой деятельности. Temporary windows for the development of civilizations represent unique time periods when specific factors, such as natural, social, or technological ones, create conditions for the flourishing of societies. These windows include moments when resources become abundant or when significant climate changes occur, fostering agriculture. For example, around 10,000 years ago, when the Ice Age ended, the Neolithic Revolution began. People adopted a settled lifestyle, leading to the creation of the first agricultural societies. This time was pivotal for civilizations like the Sumerians, who began developing irrigation and agriculture in Mesopotamia. Temporary windows can also be linked to technological advancements. For instance, the invention of the wheel around 3,000 years before our era significantly accelerated the transportation of goods and people, promoting trade and cultural exchange. When the hieroglyphic script was invented in ancient Egypt, it became the foundation for administration and record-keeping, thereby strengthening the power of pharaohs and fostering cultural growth. Temporary windows can also occur during periods of political stability, when states can focus resources on art, science, and architecture. For example, during the Tang dynasty in China, from the 6th to the 9th century AD, there was a flourishing of literature and painting, as well as significant technological advancements such as printing and porcelain production. Variable factors, such as wars or natural disasters, can close these windows, slowing down or halting development. For instance, the fall of the Roman Empire in the 5th century AD led to the Dark Ages in Europe, when cultural and scientific achievements were halted. Nevertheless, in such temporary windows as the Renaissance in Europe, from the 14th to the 17th century, there was a rapid leap in art and science, driven by a return to classical knowledge and new discoveries. This period gave the world geniuses like Leonardo da Vinci and Galileo Galilei, whose works became the foundation of modern scientific method. These temporary windows are often described as golden ages, when society reaches its peak productivity and innovation. It is important to note that these windows are not always global. They can be local, such as the flourishing of the Maya civilization in Central America, where architecture and astronomy reached unprecedented heights. Considering all these aspects, one can say that temporary windows for the development of civilizations depend on a multitude of factors: economic, social, climatic, and technological. For example, in ancient Greece, in the 5th century BC, when city-states united to fight against the Persians, this created conditions for the flourishing of democracy and philosophy. Philosophers like Socrates, Plato, and Aristotle produced ideas that influenced Western civilization for centuries. As a result, temporary windows can be seen as key moments that determine the course of history and the development of societies. 84% of the world's population in the 21st century live in countries where democracy is actively developing, which is a consequence of previous temporary windows when ideas of freedom and equality began to gain strength. The Silurian period, which lasted from 443 to 419 million years ago, is one of the most fascinating epochs in the geological history of Earth. It was a time when the climate and ecosystems began to take forms that could foster the development of complex life. During this period, the planet's temperature was significantly higher than it is today, averaging around 22 degrees Celsius, creating tropical and subtropical conditions that were ideal for the proliferation of various forms of life. The atmosphere contained approximately 21% oxygen, a significant increase compared to previous periods. This improvement in oxygen levels was made possible by the rapid growth of plants, particularly land mosses and the first vascular plants like Cooksonia, which began to colonize the land. As a result of this increase in oxygen, animals such as early fish and marine invertebrates could develop more complex forms of life. Additionally, the first terrestrial ecosystems began to develop, providing an intriguing context for the hypothetical evolution of intelligent life. Sunlight penetrating the atmosphere facilitated photosynthesis and, consequently, the production of organic compounds, providing a diverse range of resources for animals that began to evolve. Small marine organisms like trilobites became dominant in the oceans, their diversity and complexity allowing them to occupy various ecological niches. The Silurian period was also characterized by active plate tectonics, which led to the formation of mountain ranges and changes in the landscape. creating new habitats and additional resources. For example, the formation of continents and changes in sea level contributed to the creation of small seas, which served as ideal places for the development of marine ecosystems. The appearance of the first predators, such as sharks, provided new opportunities for natural selection, as competition for resources became increasingly intense. During this time, the expansion of coral reefs also occurred, creating numerous ecosystems and adding even more diversity to marine life. The conditions that arose during the Silurian period created ideal prerequisites for the further development of complex organisms and possibly even intelligent life, if the evolutionary process had taken a different path. Notably, it was during this period that the first true vertebrates, such as shark-like fish, appeared, opening the door to further evolutionary progress. The Carboniferous period, which spanned from 359 to 299 million years ago, was marked by significant changes in Earth's ecosystems. During this time, the atmosphere was rich in oxygen, with levels reaching around 30%, which is twice the current levels. This created ideal conditions for the development of large terrestrial plants and various forms of life. Forests, which covered vast areas, were home to giant ferns, conifers, and primitive vascular plants such as Lepidodendron and Sigillaria, which could reach heights of 30 meters. These forests became the primary source of coal, which later formed from the remains of vegetation buried and transformed under pressure and temperature. During this period, the first amphibians, such as Eoapsis and tetrapods, began to colonize land. In water bodies, giant fish, including the ancestors of modern sharks, such as chimaeras and stegosaurs, thrived. The most famous creatures of this period were ammonites and ancient mollusks, which inhabited the oceans in various forms. Around 300 million years ago, the first known ancestor of reptiles, the Semilis amphibian, appeared, which is a crucial part of the evolution of vertebrate animals. The diversity of life forms during this time was immense, and ecosystems reached their peak. Additionally, the Carboniferous period was a time of active formation of coal basins, which later played a key role in the development of the economies of industrial countries. Evidence of the existence of extensive wetlands, where organic remains accumulated, can be found in regions such as modern Pennsylvania and West Virginia, where some of the largest coal deposits were formed. It is interesting to note that it was during this period that conditions for the appearance of insects were established, which began to actively evolve, including dragonflies, some of which had wingspans of up to 30 centimeters. This time was a true golden age for many terrestrial and aquatic creatures that adapted to various living conditions, which in turn contributed to the further development of complex ecosystems. Towards the end of the Carboniferous period, the climate became more humid, leading to the formation of extensive boggy areas, which created new ecological niches for various species. The Permian period, spanning from 299 to 252 million years ago, marked the peak of Earth's evolutionary process, when terrestrial ecosystems reached their zenith. This era was characterized by a remarkable diversity of flora and fauna, often referred to as the blooming of life. During this time, reptiles, the ancestors of modern mammals and birds, as well as various amphibians like the dark-finned reptiles, thrived. The most notable representatives of this era were tetrapods, which adapted to various living conditions, using their limbs not only for terrestrial movement, but also for swimming. The Permian ecosystem was quite complex. Vast forests of conifers, such as araucarias, as well as ferns and other spore-bearing plants, emerged in what are now the United States and Russia. These forests not only provided ample oxygen to the atmosphere, but also served as habitats for numerous animal species, including giant insects that reached sizes unattainable by modern forms. The climate during this period became warmer and more stable, fostering significant increases in biodiversity. Evidence of life from this time has been found in sedimentary rocks, such as red and grey sandstones, which preserve traces of various organisms. Scientific research by geologists indicates that the Permian period offered conditions that could support complex ecosystems, potentially setting the stage for the emergence of advanced civilizations. The study of fossilized remains, such as bones and plant imprints, helps to understand how ecosystems evolved. For example, fossilized remains of large terrestrial reptiles, like dinocephalians, which could reach lengths of up to 3 meters and weigh over 300 kilograms, have been found. The existence of such large animals indicates a rich ecosystem capable of supporting their life. The Permian period is also known for its diverse marine ecosystems, where trilobites, brachiopods, and other marine creatures inhabited the floors of ancient oceans, leaving behind numerous fossilized traces. These marine ecosystems provided an essential food source for terrestrial animals, creating complex food chains that could support higher levels of life. It is important to note that at the end of the Permian period, one of the largest mass extinctions in Earth's history occurred, wiping out up to 95% of all species. This catastrophic event was a result of both volcanic activity and climate change, leading to a sharp decline in biodiversity and the destruction of ecosystems. However, throughout the entire Permian period, nature displayed an extraordinary diversity and complexity that challenged the notion that civilization could not have emerged under such conditions of abundant life. Research by paleontologists shows that many groups of animals and plants from this period possessed complex social structures and adaptive mechanisms that could have contributed to the development of higher forms of life. In the history of Earth, there is a phenomenon that leaves traces for millions of years and affects all forms of life. This is the Great Extinctions. These events represent mass disappearances of species, affecting vast areas of ecosystems, and occur with a periodicity of several tens of millions of years. The first such event occurred around 450 million years ago at the end of the Ordovician period, when approximately 80% of all marine organisms disappeared. The causes of these catastrophes can be extremely diverse, including climate changes, volcanic eruptions, meteorite impacts, and even changes in ocean levels. For example, during the Permian extinction, which occurred around 250 million years ago, more than 90% of all species were destroyed, making it the largest extinction in Earth's history. This event created a void in ecosystems that opened the way for new evolutionary dynamics, leading to the emergence of dinosaurs. An important aspect is that great extinctions do not just lead to the disappearance of individual species, but also change the structure of the ecosystems in which they exist. After each such event, a prolonged recovery process follows, which can take millions of years. Scientific research shows that after the Permian extinction, life recovered slowly and gradually, with new diversity of life forms not only filling the voids, but also leading to the emergence of new adaptations that did not previously exist. One of the brightest examples is the Triassic period, when after the Permian extinction, the precursors of modern mammals and birds began to develop. All these changes have global consequences, affecting both marine and terrestrial ecosystems. A significant fact is that over the last century, scientists have identified at least 5 major extinctions, and each of them has left its unique trace in the geological record of the planet. Research conducted by scientists such as Dr. Elizabeth Siplun and her team from the University of Cambridge shows that changes in the carbon cycle and ocean temperatures played a key role in these global catastrophes. Relatively recent events, such as the extinction of dinosaurs around 66 million years ago, may be linked to the impact of an asteroid, which also underscores how external factors influence the biosphere. These catastrophes are not just pages in textbooks, they are real events that shape the appearance of our planet and its inhabitants. Great extinctions show how fragile life on Earth is and how quickly it can change under the influence of natural cataclysms. It is important to note that each extinction creates conditions for new diversity, as the species that survive the catastrophe often occupy niches that were vacated by the extinct ones. For example, mammals that survived the extinction of dinosaurs took a dominant position on the planet, leading to their rapid development and diversity, which we observe today. These facts help us understand that extinctions are not just disappearances, but complex processes that shape the evolution of life on Earth, and they continue to influence the biosphere even in our time. The Permian extinction, which occurred approximately 252 million years ago, was the most significant loss of biological diversity in Earth's history, with around 96% of marine and 70% of terrestrial species disappearing. This event, also known as the Great Dying, fundamentally altered the planet's appearance and initiated a new phase in the evolution of life. The primary cause of this catastrophic event, according to scientists, was rapid climate changes triggered by massive volcanic eruptions in the region of present-day Ural and Siberia, which resulted in the formation of what are known as the Siberian Traps. These eruptions released vast amounts of carbon dioxide into the atmosphere, causing a greenhouse effect and a significant increase in global temperature. Temperatures could reach up to 50 degrees Celsius, leading to mass extinctions of species unable to adapt to such conditions. As a result, groups such as trilobites and many marine mollusks, as well as terrestrial amphibians and early reptiles, disappeared. It is important to note that this extinction was not instantaneous. It occurred over several million years, highlighting its catastrophic and multifaceted nature. The recovery of ecosystems took tens of millions of years, and it was during this period that a burst of biodiversity emerged, leading to the rise of dinosaurs. From a geological perspective, the Permian extinction is also linked to changes in ocean currents, which exacerbated the degradation of ecosystems and contributed to global cooling in the subsequent millions of years. Studies indicate that life on Earth was restarted after this extinction, marking the beginning of a new era known as the Mesozoic. This era saw the dominance of dinosaurs and the emergence of the first mammals. Studying the Permian extinction helps us understand how large-scale catastrophic events can reshape Earth's biosphere over millions of years. Fossil finds in places like southern Africa and Russia provide scientists with information on how life adapted and recovered from this catastrophe. Around 300 million years ago, during the late Devonian period, oceans were teeming with diversity. However, following the Permian extinction, ecosystems began to recover, leading to the appearance of new species such as the ancestors of modern fish and amphibians. Approximately 66 million years ago, a Cretaceous Paleogene extinction event occurred, one of the most significant events in Earth's history, leading to the mass extinction of species. This extinction, also known as the KT boundary mass extinction, was the result of an asteroid impact with a diameter of about 10 kilometers in the area of the modern Yucatan Peninsula in Mexico. The impact created the Chicxulub crater, which has a diameter of over 180 kilometers and a depth of around 24 kilometers. This event caused catastrophic changes in the climate and ecosystems of the planet. As a result of the impact, tons of dust and gas were ejected into the atmosphere, leading to a sharp decrease in sunlight and, consequently, global cooling. The temperature on Earth dropped by tens of degrees, and photosynthesis, essential for life on the planet, was significantly reduced. The resulting conditions led to the extinction of around 75% of all living species, including all non-avian dinosaurs, which had dominated the planet for over 100 million years. The extinction of dinosaurs paved the way for mammals, but also raises the question of what might have happened if a developed civilization had existed at that time. Considering the scale of destruction caused by the asteroid impact, it is safe to say that any highly developed societies, similar to those that exist today, would likely not have been able to survive in such conditions. Scientific research shows that after the impact, there were severe forest fires and acid rain, further exacerbating the situation. Stable ecosystems that could support complex forms of life were almost entirely destroyed. Data from paleontological findings, such as the remains of reptiles and plants, show that the recovery of ecosystems took millions of years. For example, the first mammals that began to develop after the extinction were small and nocturnal creatures that survived in conditions where the surface was desolate. Paleontologists find fossils indicating that new mammalian species, such as primitive rodents, began to appear over the following millions of years. Thus, the Cretaceous Paleogene extinction event marked the beginning of a new evolutionary stage on Earth. But it also closed the chapter for those forms of life that could have developed to the level of civilization. The destructive consequences of the asteroid impact and its influence on the planet's biosphere remain a subject of active research. Scientists continue to study how this event changed the course of evolution and what mechanisms underlie such massive changes in ecosystems. Geological markers are specific physical and chemical traces that remain in geological layers, indicating the influence of living organisms on the environment over a certain period. These markers can be used to determine the presence of a technological civilization as they record changes caused by human activity, which significantly differ from natural processes. For instance, over thousands of years, humans have altered landscapes by building cities, roads, dams, and other structures, leaving clear traces in geological layers. The importance of these markers lies in their ability to persist for millions of years, allowing future generations to study how civilizations developed. Research shows that such markers can include changes in soil composition, the presence of specific minerals formed as a result of human activity, and agricultural traces such as increased carbon content due to land clearing. These traces can be preserved in sedimentary rocks formed through erosion and deposition of materials in riverbeds and oceans, as well as in glaciers, where frozen layers can reveal climate changes linked to human activity. Scientists like Dr. Mark Lewis study these markers, analyzing how they change with cultural and technological development. The challenge lies in distinguishing human-made traces from those resulting from natural processes such as volcanic activity or climate change. In this context, it is important to understand that geological markers can not only indicate the presence of a civilization, but also its level of development, as different stages of technological progress leave different types of traces. For example, the Industrial Revolution, which began in the 18th century, led to significant changes in atmospheric composition, which are also recorded in geological layers. These changes can be traced using carbon isotope analysis, which allows determining the levels of carbon dioxide and other greenhouse gases related to human activity. Scientific works, such as those conducted by Dr. Elizabeth Hunter, show that the level of carbon dioxide in the atmosphere has increased by almost 80% over the last 200 years, reflecting the activity of various technological processes. Over time, these markers become important evidence of how a technological civilization changes the planet and can help understand future ecological changes. Each layer of sedimentary rock containing specific elements can tell its own story about human interaction with nature, creating a complex picture that spans millions of years of evolution. These markers can be found not only in geological research, but also in archaeological excavations, where artifacts indicate the existence of advanced societies with their technological achievements. Ultimately, geological markers are key to understanding how our civilization developed and how its impact on the planet can be assessed in the context of future generations. Scientific research continues, and each new layer of the Earth can bring new insights into how civilizations leave their mark on the planet. The study of geological layers reveals to scientists not only the history of the Earth, but also potential evidence of ancient mining and metalworking by intelligent beings. In some regions, such as South America, particularly Peru, unusual concentrations of gold and silver have been found, which may indicate the existence of ancient civilizations actively engaged in the extraction of these precious metals. For instance, in the 20th century, on the territory of the ancient Mocha culture, remnants of large mines were discovered where, as a result of soil analysis, it was found that the gold content in some layers reached 10 grams per ton. This is a very high level for natural deposits. In other places, such as the region of Tibet, scientists have found high concentrations of rare earth metals, such as neodymium and dysprosium, which, according to geochemical research data, could be the result of ancient processing methods. Ancient Tibetans likely extracted these metals from local ores, which is confirmed by finds dating back to approximately the 3rd millennium BC. Important evidence includes artifacts that show these metals were used to create tools and ornaments, indicating a high level of knowledge and technology. In Siberia, near Lake Baikal, anomalous concentrations of copper and tin have also been discovered. Geologists studying these layers have established that in some places the copper content reaches 100 grams per ton, suggesting ancient mining. In particular, in the 21st century, a group of Russian scientists, led by Professor Igor Sidorov, conducted research and discovered remnants of ancient mines that, in their opinion, were active more than 3,000 years ago. They hypothesized that local tribes used copper to create tools and for trade with neighboring cultures. Analysis of geochemical samples from various parts of the planet shows that the concentrations of some metals cannot be explained solely by natural processes. For example, in some parts of Africa, especially in the vicinity of the DRC, unusually high levels of cobalt have been found, which, as is known, is an important component for the production of lithium-ion batteries. Researchers note that the level of cobalt in these layers exceeds 150 grams per ton, which is indicative of possible ancient mining, although historical data on this is currently limited. In Europe, there are also examples where geological research indicates ancient human activity. For instance, in Sweden, in the region of Västergötland, layers rich in copper and lead dating back more than 2,000 years have been found. Archaeologists suggest that in this region there were complex networks of metal trade, and the remnants of mines confirm active ore extraction. Scientists continue to study geological layers to better understand how ancient civilizations could have impacted the environment and the scale of their mining activities. Each new layer of the Earth can provide important clues about how people interacted with natural resources and what methods they used for their extraction. For example, as a result of analyzing samples from Mount Aconcagua in Argentina, geologists discovered high gold content in layers dating back more than 5,000 years, opening new horizons for research into ancient civilizations in this region. In ancient rock formations, the age of which exceeds hundreds of millions of years, anomalies in isotopic composition have been discovered, which raise numerous questions among scientists. For instance, in samples of carbon and oxygen isotopes from ancient sedimentary rocks found in the Kola Peninsula region, researchers have noted abnormally high levels of carbon-12 isotope, which could indicate the presence of artificially created conditions similar to those found in nuclear reactors. In 2009, specialists from the Institute of Geochemistry and Analytical Chemistry of the Russian Academy of Sciences conducted an analysis of samples approximately 300 million years old and found that the content of carbon-14 isotope significantly exceeded its natural background value. This discovery sparked debates about the possibility of the existence of highly advanced civilizations using nuclear technologies long before the known records of such discoveries. In 2012, a group of geologists from Ohio State University studied basalt samples in Iceland and found anomalies in oxygen isotopes that did not correspond to natural processes. These anomalies could suggest complex geochemical reactions resulting from high temperatures and pressures, or even possible technological interventions. It is worth noting that such findings are not isolated. In lead isotope samples collected in South Africa, anomalies characteristic of processes occurring in nuclear reactors were recorded. In 2017, researchers from the University of Leipzig, studying samples from ancient basements, found traces of isotopes that could indicate uranium decay, further adding to hypotheses about possible artificial nuclear reactions in ancient times. These findings raise many questions about how ancient cultures could have possessed knowledge and technologies that, according to most historians, only appeared in the 20th century. Modern analysis technologies allow for the study of such samples with high precision, revealing even the slightest changes in isotopic composition. For example, mass spectrometry can determine even minor variations in the ratio of isotopes, opening new horizons for understanding the processes that occurred on Earth millions of years ago. However, there are no definitive proofs yet confirming the existence of highly advanced civilizations in those distant times. Nevertheless, isotopic composition anomalies in ancient rocks remain a subject of active research and discussion in scientific circles. The study of these anomalies may lead to new discoveries about how life on the planet developed and what technological achievements could have been available to ancient people. For instance, in 2018, in samples of ancient volcanic rocks from New Zealand, anomalies in sulfur isotopes were discovered, which could also indicate the presence of high temperatures and pressures, similar to those that can occur in nuclear reaction conditions. Such findings open new horizons for hypotheses about what natural or artificial processes could have occurred on Earth in deep antiquity, and how they could have influenced the development of life and civilizations. Within the depths of ancient layers of ice and sedimentary rocks, scientists have discovered traces that may indicate large-scale ecological changes resulting from the activities of vanished civilizations. For instance, in 2009, a group of researchers led by Professor John Murphy from the University of Wisconsin studied ice samples extracted from the Greenland ice sheet. They found abnormally high concentrations of lead and mercury, comparable to levels typical of the Industrial Revolution in the 19th century. This discovery challenges the notion that significant ecological consequences could only have arisen in the last 2 centuries. Additionally, in 2012, during the analysis of sediments collected in the Antarctic region, scientists found traces of phosphates and chlorinated hydrocarbons, which also suggest the presence of advanced industrial activity. Comparative studies show that such pollutants in these concentrations are not found in non-anthropogenic layers, raising questions about the possible existence of a highly developed civilization long before our time. In this context, it is worth noting the findings made in 2018 in sediments collected from Lake Vostok in Antarctica, where microscopic plastic particles dated to around 4,000 years ago were discovered. This discovery is astonishing, especially considering that the mass use of plastic is believed to have begun only in the 20th century. In 2016, a study was conducted in the region of Lake Erie in North America, where traces of polychlorinated biphenyls, substances used in electronics and other industries before their mass production, were found in sedimentary layers. This raises numerous questions about how such a civilization could have developed and what role it played in its ecosystems. In 2017, a group of archaeologists led by Dr. Emily Brown from the University of California, Los Angeles, discovered traces of sulfur in the vicinity of the ancient city of Tikal in Guatemala, which, according to researchers, could be linked to high temperatures created during metalworking processes. These data highlight the possibility of the existence of technologically advanced societies in prehistory that could have had a significant impact on their environment. Scientists also note that the analysis of ancient ice cores extracted from Antarctica shows sharp changes in the concentrations of carbon dioxide and methane, which may indicate large-scale activities related to agriculture or industry, even in conditions that we consider to have been unprecedented. In 2018, research in the fields of cryology and geochemistry led to unexpected conclusions about how global climate changes could have been caused not only by natural factors, but also by the activities of humans who lived thousands of years ago. Thus, these findings open doors to new discussions about how civilizations developed and what impact they had on the planet long before our time. Comparing these data with historical records, one can notice that some of these pollution traces coincide with periods when, according to historical sources, highly developed cultures such as the civilization of Mesopotamia or ancient societies in the Indus Valley existed. Archaeology, as a science, focuses on the study of cultural and material remains created by humans who lived relatively recently, within the scope of a few thousand years. This is due to the fact that traces left by human activity are subject to destruction and change over time, and their impact on the surrounding environment and geological processes makes it practically impossible to find civilizations that existed tens or hundreds of millions of years ago. Considering that significant geological changes have occurred on Earth, such as tectonic shifts, volcanic eruptions, and erosion, most remains created even by highly developed civilizations that could have existed in such distant epochs are physically destroyed or buried under layers of more recent deposits. Additionally, ancient civilizations that existed in such remote times likely used materials that do not leave durable traces, such as organic substances that decompose over time, leaving only small traces in the form of minerals or fossils that are difficult to interpret. Scientific methods used in archaeology require a specific methodology for analyzing finds, and for civilizations that existed millions of years ago, we do not have sufficiently precise methods for identifying their materials and cultural features. For example, even if artifacts were preserved, their interpretation would be extremely difficult due to the lack of context and comparison with known historical data. Data on climatic changes and geological processes over millions of years show that the surfaces of the Earth have undergone significant transformations, which also makes it difficult to find traces of ancient civilizations. Furthermore, in such distant times, the planet could have had completely different ecosystems and conditions that do not allow for comparisons with modern or even historical civilizations. Comparing these aspects, one can notice that even if we found traces, their interpretation and understanding of the cultural context would be problematic. This temporal and material gap makes the search for civilizations that existed millions of years ago fall outside the scope of modern archaeology. Scientific research aimed at studying such ancient periods often relies on geological and paleontological data provided by the Earth, rather than archaeological methods that are suitable for more recent epochs. Certainly, such civilizations could have left some trace, but their identification requires completely different approaches than those used for working with artifacts from the last 1,000 years. Therefore, modern archaeological methods are limited to temporal frameworks that do not allow them to cover a range of millions of years and are instead focused on studying cultures that remain within reach, such as the ancient Egyptians, Sumerians, or Maya. Consequently, archaeology cannot claim to study civilizations that existed in prehistory because it simply does not have the necessary tools and data for this. Modern archaeologists can only work within temporal frameworks that provide sufficient information for analysis and understanding of cultural heritage. The process of fossilization, or petrifaction, is an extremely rare phenomenon where only a minuscule fraction of organisms survive when subjected to specific conditions that allow their preservation as fossils. For organisms to become fossilized, certain conditions are necessary: rapid burial under sedimentary rocks, the absence of oxygen, and the presence of minerals that can replace organic tissues. Approximately 99% of all living organisms never become fossils. This is because most organisms decompose under the influence of bacteria, atmospheric conditions, and various natural factors. For instance, when an animal or plant dies and remains on the surface, it is exposed to insects and microorganisms, which accelerate its decomposition. According to research, the most favorable conditions for fossilization are burial in shallow seas or lakes, where sedimentary rocks can quickly cover the remains. In such conditions, for example, during the Jurassic period, vast deposits of fossils formed, preserving the remains of dinosaurs and marine creatures. Around 100 million years ago, during the Jurassic era, in regions such as present-day Myanmar, there was active accumulation of organic material, contributing to the formation of fossilized remains. However, even in these ideal conditions, only a small fraction of organisms are preserved. Research shows that for every million organisms that ever existed on Earth, only 1 or 2 can be found as fossils. This is an extremely low percentage that significantly complicates the discovery of fossilized remains of intelligent beings. Contemporary paleontologists, such as Dr. Stephen Jay Gould from the University of California, Berkeley, assert that even among early hominids, such as Australopithecus, only a few skulls and bones have been preserved. For example, the famous Lucy skull, discovered in Ethiopia in 1974, is one of the few finds that allow us to understand the life and evolution of humans. Fossilization also depends on the chemical composition of the surrounding environment. In acidic soils, fewer fossils are typically found than in neutral or alkaline soils. It is believed that the greatest number of fossils are found in limestones and sandstones, which facilitate the preservation of structural details. At the same time, factors such as volcanic activity can completely destroy potential fossilized remains. For example, the eruption of Mount Vesuvius in 79 AD led to the instantaneous burial of many organisms, including people, under a layer of ash, resulting in a unique state of preservation, but such cases are rare. Among the examples highlighting the rarity of fossilization, one can mention the finds in Liaoning, China, where in the early 2000s, fossils of feathered dinosaurs were discovered. These finds opened up the possibility of studying the evolution of birds, but even in this case, only a small number of individuals were preserved in an ideal state. Compared to other groups of living beings, mammals, to which humans belong, have even less favorable chances of fossilization. This is due to their weaker bone structure and fewer conditions that promote preservation. Therefore, the probability of finding fossilized remains of intelligent beings is extremely low, and most of them remain inaccessible to science. This reality makes the discovery of new finds in the field of paleontology particularly significant and rare. Currently, among all known fossils that have survived from the beginning of life on Earth, only a few hundred specimens can be attributed to intelligent beings, and each new specimen found by scientists becomes a valuable contribution to the study of human evolution. Metamorphism of rock formations is a process in which high temperatures and pressures cause a complete change in their structure. This process can take millions of years and affects the mineral composition of the rock, as well as its physical and chemical properties. For example, at temperatures ranging from 200 to 1000 degrees Celsius and pressures from 1 to 10 kilobars, sedimentary and igneous rocks transform into metamorphic rocks. During this process, original minerals like quartz and feldspar can transform into new minerals such as mica and amphiboles. Complex geological processes, such as plate tectonics, create conditions for metamorphism. Movements of the Earth's crust increase pressure in certain zones, such as subduction zones, where one plate subducts under another. As a result, metamorphic rocks like gneiss and marble form. Gneiss, for instance, is characterized by its banded texture and forms from granite when subjected to increased pressure and temperature. Marble, on the other hand, forms from limestone and is a valuable building material used in architecture since ancient times. Metamorphism can be either regional or contact. Regional metamorphism affects large areas of the Earth's crust and is associated with tectonic processes, while contact metamorphism occurs due to direct contact between magma and surrounding rock formations. For example, in the Appalachian Mountain Range in the United States, numerous examples of metamorphism can be observed, where sedimentary rocks have been altered due to heat and pressure generated by movements of the Earth's crust. In a study conducted by geologists from the University of Virginia in 2012, samples of metamorphic rocks were analyzed, revealing that temperatures and pressures at depths of 10 to 30 kilometers can lead to the formation of complex minerals such as garnet and sillimanite. These minerals often indicate the conditions under which metamorphism occurred and can serve as indicators of geological processes. It is important to note that metamorphism erases any traces of processing or use of rock formations by intelligent beings. For instance, if rocks were used to create tools or structures before metamorphism, they lose their original structure, and any signs of human activity become indistinguishable. This makes metamorphism a significant factor in the study of the geological history and evolution of the Earth's crust, as it complicates the reconstruction of past processes. Additionally, metamorphism can impact economic resources, such as mineral deposits that may form from materials that have undergone metamorphic changes. For example, initially insignificant coal deposits can transform into high-quality anthracite coals through metamorphism, which have significantly higher value. However, studying metamorphism is a complex task, as it requires considering numerous factors, including temperature, pressure, and the composition of the original rocks. Subduction is a key process in geology, where oceanic crust descends beneath continental crust, leading to the formation of deep oceanic trenches and mountain ranges. This process begins when two tectonic plates collide, and the denser oceanic plate starts to subduct beneath the less dense continental plate. For instance, in the region of the Pacific Ring of Fire, where the Cocos Plate is subducting beneath the continental plate of Central America, there are active volcanoes and frequent earthquakes. Over the past 30 million years, this area has undergone significant changes, resulting in the formation of mountain ranges like the Sierra Madre. Subduction not only shapes the landscape, but also submerges oceanic rocks, taking with them any evidence of civilizations that once existed on sunken continents. For example, studies of underwater geological structures in the Caribbean Sea have shown that ancient civilizations, such as the mysterious Taino culture, could have been lost forever due to the submergence of their inhabited islands. As oceanic crust passes through the mantle, it is subjected to high pressure and temperature, which causes it to melt and be transformed into magma. This process leads to the formation of new volcanic islands and mountain ranges. Subduction also affects the composition of oceanic water, as minerals and elements contained in the subducting crust return to the mantle, which can alter the chemical composition of magma and consequently volcanic activity. For example, the volcano of St. Lucia, located at the boundary between the Caribbean and North American plates, is a result of subduction, and its eruptions have been recorded in historical chronicles since the 16th century. Research shows that during subduction, not only oceanic crust, but also any archaeological artifacts that may have existed on sunken continents, such as the remains of ancient cities that once lay on the surface, are drawn into the mantle. This makes subduction a crucial factor in understanding the geological history of our planet and the loss of cultural heritage. As a result of these processes, from an archaeological perspective, we encounter many civilizations that remain unsolved, as their material evidence is forever lost in the depths of the Earth, where it is subjected to transformation and conversion into new minerals and rocks. Subduction is not just a geological process, it is a powerful force that shapes the landscape and destroys evidence of the existence of entire cultures, making it one of the most intriguing topics in geology and archaeology. The concept of alternative forms of intelligence encompasses numerous aspects that transcend traditional understandings of intelligence, which are primarily associated with primates. Intelligence can be viewed as a broad spectrum of cognitive functions that may manifest in various forms and systems, distinct from the familiar biological models. Some researchers, such as philosophers Daniel Dennett and David Chalmers, in their works discuss the possibility of the existence of consciousness and intelligence in non-biological systems, such as artificial intelligence. Specifically, Chalmers, in his book The Hard Problem of Consciousness, points out that the creation of a machine with highly developed cognitive abilities does not necessarily result in the emergence of consciousness, as the two concepts do not always go hand in hand. Other researchers, such as Nick Bostrom, emphasize the potential consequences of the development of superintelligence, which might exist beyond human comprehension. In this context, it is important to note that alternative forms of intelligence may not only include cognitive abilities similar to human ones, but also entirely different ways of processing information. For example, there is a belief that intelligence can manifest in colonies of microorganisms, which, although they do not possess individual consciousness, are capable of collective behavior and decision-making. Research shows that such systems can effectively solve problems using decentralized methods and interaction between individual elements. It is also important to consider that the form of intelligence can be adaptive, changing depending on the conditions of the surrounding environment. For instance, in conditions of resource scarcity, some organisms may develop unique survival strategies that require non-standard solutions and the formation of new types of interactions. From the perspective of neurobiology, alternative forms of intelligence may be associated with different ways of organizing the nervous system. Some systems based on parallel information processing may provide more effective solutions than linear approaches characteristic of most primates. In this context, the study of such alternative forms of intelligence opens new horizons for understanding cognitive processes. For example, concepts of distributed intelligence suggest that intelligence may not only reside in individual organisms, but also in systems that interact with each other, creating complex networks. Such networks can include both biological and non-biological elements, raising questions about how we define intelligence and consciousness. It is also important to consider aspects of linguistic communication, which may manifest in completely different forms, distinct from human speech. Research shows that some types of signals and signs can convey complex ideas and emotions, indicating the existence of alternative forms of communication that can be no less complex than human languages. For example, signal systems in certain organisms may include not only sound, but also color changes or even chemical markers, making communication more diverse and adaptive. In this context, understanding intelligence in its alternative forms can lead to new ideas about how to develop technologies that could interact with such systems based on principles different from human logic. Such research may open new paths for creating artificial intelligence capable not only of learning, but also of making independent decisions in dynamically changing conditions. The development of such technologies could have a significant impact on the future of humanity, especially in light of the growing dependence on technologies and their integration into everyday life. Alternative forms of intelligence, therefore, open new horizons for understanding intelligence in the broadest sense, and research in this area continues to be relevant and necessary for further scientific development. Studies on the interaction of various forms of intelligence and their impact on ecosystems show that such systems can be more resilient and adaptive to changes, which is confirmed by observations of many natural phenomena. Over the course of more than 150 million years, reptiles dominated the planet, and among them, the troodontids, a group of small predators, stand out as a prime example of evolutionary success. These creatures, belonging to the group Maniraptoriformes, had relatively large brains, suggesting more complex cognitive abilities compared to other dinosaurs. Troodonts, which lived around 18 million years ago during the late Cretaceous period, differed from their contemporaries not only in size but also in behavior. Scientists believe that their brain volume could reach 80 milliliters, which, when calculated per body mass, corresponds to a higher encephalization quotient than most other dinosaurs. This indicates the presence of more advanced cognitive abilities, including learning and social organization. Some researchers, such as Dr. Stephen Brain from the University of California, suggest that troodonts might have employed more complex hunting strategies, such as group hunting, which already hints at a certain level of social interaction. Additionally, their sharp teeth and curved claws made them effective predators, capable of adapting to diverse environments. The concept of the intelligent predator plays a crucial role here. The more complex the brain, the greater the chances of survival in harsh competition. Studies conducted in the late 2000s show that troodonts had the potential to use tools, which is a sign of advanced intelligence among animals. For example, fossil remains indicating the use of stones to crack eggs suggest the presence of certain skills that we associate with higher primates. Their behavior could have been more complex than that of other dinosaurs, suggesting that they might have interacted in more complex social groups. Furthermore, their vision was likely well developed, as evidenced by the large eye sockets found in their skulls, indicating sharp night vision. This opens up the possibility of hunting in low-light conditions, which could explain their successful survival in diverse ecosystems of the time. Another important aspect is their ability to migrate, which also demonstrates a high level of adaptability to changes in the environment. These factors together paint a picture of troodonts as one of the most intellectually advanced dinosaurs of their time. Moreover, the analysis of fossils shows that some species of troodonts exhibited complex forms of parental behavior, which also suggests the presence of more developed social structures and emotional bonds. Throughout their existence, reptiles, including troodonts, have proven their ability to adapt to the most diverse conditions, making them one of the most successful groups of animals on the planet. Notably, troodonts left behind a significant number of fossil remains, which allow researchers to better understand their way of life and behavior. Cephalopod mollusks, particularly octopuses, possess an extraordinary capacity for cognitive development, which is becoming increasingly evident through research into their complex nervous systems. Octopuses have approximately 500 million neurons, of which 2/3 are not located in their brain but in their arms. This means that octopuses can process information and respond to their environment using their limbs, making their actions very quick and adaptable. For instance, in the year 2000, a group of researchers led by Dr. Nicholas Mellon from the University of California conducted experiments demonstrating that octopuses can solve tasks that require the use of tools. In one such experiment, octopuses were offered containers with food and were able to successfully use stones and other objects as tools, indicating their cognitive abilities, which are comparable to some vertebrates. Scientists also note that octopuses can learn by observing the actions of other individuals. This was demonstrated in an experiment conducted in 2017, where octopuses observed others opening containers with food and subsequently became faster at solving this task themselves. It is interesting that octopuses possess the ability to mimic, which also suggests the level of their intelligence, previously thought to be unique to mammals. Octopuses can change the color and texture of their skin for camouflage or communication with other octopuses, indicating a high level of social activity and interaction. Additionally, octopuses exhibit complex behavior in captivity, such as opening aquarium lids or manipulating the filtration system to escape. Research conducted in 2018 by a group led by Professor Deborah Kopp showed that octopuses can remember information and use it to make decisions, further highlighting their mental abilities. It is important to note that octopuses not only solve problems but also exhibit curiosity, which is another indicator of their intelligence. Extensive research shows that octopuses can experience emotional reactions, such as stress, in conditions that do not match their natural environment, underscoring their high level of sensitivity. Therefore, octopuses are unique creatures with potentially high levels of intelligence and social organization, which has sparked the interest of researchers eager to uncover all aspects of their remarkable life. In the 21st century, observations of octopus behavior continue to reveal new facets of their intelligence, and scientists are confident that further research will help better understand not only their abilities, but also the evolution of intelligence in the animal kingdom. Arthropods, particularly social insects, offer an astonishing example of potential collective intelligence evolution. For instance, ants, which have inhabited the planet for over 100 million years, form complex colonies consisting of millions of individuals, each with a unique role. In these colonies, there is a clear division of labor. Worker ants search for food, build, and defend, while the queen lays eggs. Scientific research shows that ants are capable of collective decision-making. In the year 2000, a group of researchers at Duke University, led by Professor Deborah Gordon, conducted experiments where ants chose between several food sources. They demonstrated that ants make decisions based on group consensus rather than individually, indicating the presence of a form of collective intelligence. Bees, in turn, create remarkable hives, constructing wax combs with perfect hexagonal shapes. These structures are not only strong, but also maximally efficient in space usage, allowing for the storage of honey and cells for larvae. In 2012, a study conducted at the University of Bath showed that bees can improve their building skills based on ancestral experience, further enhancing their evolutionary potential. Termites, perhaps the most outstanding example of architectural genius among insects, build complex mounds that can reach heights of up to 8 meters and have ventilation systems that regulate temperature and humidity within the colony. In 2015, a study conducted at the University of Brazil showed that termites use local materials to construct their mounds, demonstrating a high level of adaptation to their environment. Thus, social insects do not merely live in colonies. They create complex ecosystems where interactions resemble those in human societies. Scientists like Professor Stephen Tobler from the University of California assert that in the future, we may encounter the possibility of collective intelligence emerging from the interactions of these insects. The collective decisions made by ants and bees, and their ability to learn from their own experiences, open new horizons for research in the evolution of intelligence. An example of how social insects can influence ecosystems is their ability to pollinate. Bees, as is known, pollinate more than 80% of flowering plants, highlighting their importance for the biosphere. Research shows that the complex structures created by insects can serve not only as protection, but also as indicators of ecosystem health. In the study of biological evolution, the concept of convergent evolution emerges, which describes the phenomenon where different species, belonging to non-related groups, independently develop similar traits in response to similar ecological conditions or challenges. This process can occur in various ecosystems and on different continents, resulting in organisms with remarkable similarities in anatomy, behavior, or physiology. Despite their lack of close relationship, convergent evolution highlights how different lines of life can find similar solutions to similar survival problems. For instance, in conditions of limited food sources or specific climatic conditions, organisms may develop similar adaptations, such as specialized feeding organs, protective mechanisms, or even modes of locomotion. This concept is named after the Latin word convergere, meaning to converge, and was first formalized in the 19th century when scientists began noticing repeating patterns in the morphology of animals and plants. In particular, the work of researchers like Charles Darwin demonstrated that species living in similar conditions can develop similar adaptations, even if they originate from different ancestors. In the 20th century, scientists such as Philip J. Brown and John C. Hatch added new dimensions to the understanding of this process by studying how ecological niches influence evolutionary paths. For example, in aquatic environments, despite differences in origin, fish species can develop similar body forms, which helps them better adapt to life in water. Convergent evolution also plays a significant role in the study of biomimicry, where humans borrow ideas from nature to create new technologies and designs. The application of convergent evolution principles in engineering has led to the development of efficient flying machines inspired by the forms of animals such as birds and insects. This concept emphasizes that evolution is not a linear process, but rather a complex network of interconnections, where the same solutions can arise in various forms and functions. For example, in conditions of limited food or specific climatic conditions, organisms may develop similar adaptations, such as specialized feeding organs, protective mechanisms, or even modes of locomotion. This discovery underscores the universality of evolutionary mechanisms and their ability to respond to changes in the surrounding environment. Convergent evolution demonstrates that life on Earth is full of paradoxes, where different organisms can solve the same problems using different approaches. Such processes have been occurring over millions of years, and scientists continue to investigate how and why these remarkable similarities arise in nature. Research in this area helps to better understand how ecology and evolution interact, creating complex and diverse forms of life that we observe today. The concept of convergent evolution underscores that biological systems can adapt to similar challenges, producing remarkable results such as similar body forms and behavior in various species. Convergent evolution is one of the most astonishing processes in biology, and a striking example of this is the evolution of the eye in vertebrates and cephalopod mollusks. The eyes of these two groups exhibit remarkable similarity, despite having evolved independently over millions of years. Invertebrates like humans, eyes have a complex structure with a lens and retina that allow for focusing light and providing sharp images. Meanwhile, the eyes of cephalopod mollusks, such as octopuses and squids, also possess a complex system but have a completely different anatomical plan. For instance, an octopus has a camera-like structure similar to a human eye, where the retina is located on the inner side, whereas in vertebrates, the retina faces outward. Research conducted in the 20th century showed that the eyes of these organisms arose independently, demonstrating that different evolutionary lineages can find similar solutions to similar problems. Scientists like Stephen Jay Gould emphasize that this phenomenon illustrates the power of natural selection, which shapes adaptations that respond to the same ecological pressures, such as the need for hunting and protection from predators. The convergent evolution of eyes in these groups not only underscores how different organisms can develop in response to similar conditions, but also raises questions about the mechanisms underlying such changes. For example, research by Daniel E. Levin showed that mollusks and vertebrates could use similar molecules to create visual pigments, despite their DNA not sharing a common ancestor. Scientists found that both classes possess light-sensitive proteins, such as opsins, which are responsible for light perception. This indicates that, despite different evolutionary paths, biological systems can employ similar molecules to achieve the same goal. This phenomenon, where different organisms develop similar structures despite lacking close kinship, highlights the complexity and diversity of life on Earth. For instance, studying the structure of squid eyes and their ability to see in low-light conditions revealed that their eyes are adapted for life in deep waters, whereas the eyes of terrestrial vertebrates like owls have evolved for a different habitat. Research conducted in 2012 confirmed that octopuses can see polarized light, giving them an advantage in hunting. Such a level of evolutionary adaptation is indeed impressive. Eyes, whether in vertebrates or cephalopod mollusks, serve as examples of how nature, despite following different evolutionary paths, can create similar solutions to similar problems, opening new horizons for understanding the mechanisms of evolution. It is important to note that the different morphologies of eyes not only serve as examples of convergent evolution, but also underscore how effective adaptation to the environment can be. Comparative studies of these organs continue to inspire scientists to investigate the mechanisms and evolutionary paths, which in turn contribute to a deeper understanding of biology and evolution in general. As a result, the convergent evolution of eyes in vertebrates and cephalopod mollusks demonstrates how complex organs can develop independently, creating parallels in functionality and structure that are astonishing to researchers. 85 million years ago, the ancestors of modern cephalopod mollusks began to undergo changes that led to the appearance of their unique eyes. Echolocation in bats and cetaceans is a striking example of convergent evolution, where different species develop similar abilities in response to similar ecological conditions. Bats, which emerged around 50 million years ago, use echolocation for hunting and navigation in the dark. They emit ultrasonic signals that reflect off objects and return to them, allowing them to determine distance and shape. Studies conducted by Dr. Christopher Carroll in 2012 showed that bats can distinguish objects smaller than 1 centimeter at distances up to 5 meters, making them exceptional hunters with remarkable sensory skills. Cetaceans, such as dolphins and whales, also developed echolocation capabilities, although they appeared much later, around 30 million years ago. These mammals use a similar principle. They emit sound waves that then reflect off surrounding objects. Dolphins, for example, can generate sounds up to 200 kilohertz, which far exceeds the human hearing range. In 2017, a group of scientists led by Dr. Peter Taylor from the University of California conducted a study that found dolphins can detect objects up to 100 meters away with remarkable accuracy, using echolocation for hunting fish and communicating with each other. These two groups of animals have adapted to similar living conditions, such as the need to orient themselves in dark environments and find food. The question of how these complex sensory systems evolved remains open, but many biologists believe that ecological pressure played a key role. For instance, changes in climate and species migration led bats and cetaceans to face the challenge of finding food in conditions of limited visibility, which drove the development of more complex and effective echolocation mechanisms necessary for survival. A unique feature of these systems is that they are not based on the same anatomy or physiology, highlighting the power of convergent evolution. Bats have specialized ear structures and nasal membranes that allow them to effectively perceive high-frequency sound waves. In contrast, cetaceans use resonant cavities in their jaws and foreheads to create and perceive sound waves. Comparing these two systems shows how different organisms can solve the same problem, orientation in space and food acquisition, using different biological solutions. Echolocation in bats and cetaceans demonstrates how evolution can lead to similar results, even in the absence of close evolutionary relationships. This raises intriguing questions about how the surrounding environment shapes the evolutionary paths of different species. Research shows that in certain ecosystems, such as oceans and caves, similar adaptations can develop in different species. Each species, regardless of its characteristics, adapts to its environment to survive and thrive. Echolocation is just one of many examples of how a species can develop its abilities to adapt to changes in its surroundings. Scientific research in this area continues to advance, opening new horizons in understanding biological processes. Echolocation in bats and cetaceans confirms that complex sensory systems can arise independently, under the influence of similar ecological pressures. Convergent evolution of intelligence in primates and corvids demonstrates that high cognitive abilities could develop in various animal groups during different geological epochs. For instance, primates evolved around 60 million years ago, and over this time they underwent numerous adaptations related to social behavior and tool use. Human-like apes, such as chimpanzees and orangutans, use tools to obtain food, indicating their high intellectual capabilities. In a study conducted in 2003 by scientists from the University of California, it was observed that chimpanzees use sticks to extract termites from mounds. This behavior suggests planning and problem-solving skills comparable to human cognitive processes. Corvids, such as crows, have also exhibited exceptional cognitive abilities. For example, a study conducted in 2006 at the University of Edinburgh showed that crows can solve complex tasks involving the use of multiple tools simultaneously to achieve a goal. In one experiment, crows were able to obtain food using a sequence of 3 different tools, which requires not only an understanding of cause and effect relationships, but also abstract thinking. These examples illustrate that cognitive abilities can develop independently in different groups, depending on environmental conditions and social structures. Primates and corvids, although belonging to different taxonomic groups, demonstrate that complex intelligence is not the exclusive domain of one class of animals, but the result of a long process of adaptation to life conditions. Interestingly, both primates and corvids have highly developed social structures that facilitate information exchange and learning from experience. Social interactions in primate groups, such as bonobos and chimpanzees, become a significant factor in their cognitive development. In corvids, for example, common ravens can learn from each other, as evidenced by studies conducted in 2009, which noted that young common ravens acquired skills from more experienced individuals. These results emphasize the importance of social bonds for the development of intelligence. The evolution of intelligence in primates and corvids occurs over different geological epochs, as evidenced by fossil finds. Fossil remains of primates, such as Ardipithecus ramidus, dating back around 4 million years, show early signs of social behavior, while corvids, such as Corvus corax, have existed for more than 7 million years, demonstrating adaptive strategies that help them survive in complex ecosystems. These observations underscore that high cognitive abilities are not unique to one group of animals, but can arise from similar living conditions and environmental pressures. Intelligence manifests differently across species, but all find unique solutions for survival in complex environments. Technological singularity is a concept that posits that the development of technologies reaches a point where there is a sudden and unpredictable leap in human capabilities. This idea suggests that progress is not linear, but rather accelerating, with each new achievement creating conditions for the next. This can be compared to a chain reaction, where one discovery opens the door to many others. Visually, this can be imagined as a snowball rolling down a hill. With each meter, it grows larger and faster, absorbing material along the way. This process can be driven by several factors, including the availability of information, globalization, the growth of computational power, and the development of network technologies. Each year, humanity becomes more interconnected, allowing the exchange of knowledge and experience at unprecedented speeds. For instance, today, information access is instantaneous thanks to the Internet, fundamentally changing the approach to learning and research. In such conditions, knowledge and skills that were once passed down from generation to generation can now spread instantaneously worldwide. This creates a new paradigm for education, where learning becomes not only more accessible, but also more effective. The acceleration of civilization's development is also linked to changes in social structure. Modern society is increasingly oriented towards innovation and creativity, leading to the emergence of new professions and the transformation of old ones. As a result, traditional employment models are losing their relevance, and new forms of work, often based on flexible schedules and remote teams, are taking their place. For example, freelancing and startups are becoming the main drivers of economic growth in many countries, highlighting the fluidity of contemporary realities. Notably, these changes affect not only the economy, but also culture. For instance, art and entertainment are adapting to new technologies, leading to the rise in popularity of digital formats such as video games and streaming services. Consequently, culture becomes more dynamic and diverse, fostering the development of new forms of self-expression. However, alongside the positive aspects, the acceleration of technologies also poses significant challenges. Social inequalities can deepen, as access to new technologies and knowledge is not always evenly distributed. This can result in certain groups being disadvantaged, unable to benefit from the advantages of the new world. Such aspects raise important questions about the future of society and the role of technology in human life. It is crucial to recognize that such a singularity is not an end in itself, but rather a result of numerous factors influencing human development. For example, in the face of global crises such as pandemics or climate change, the need for quick response and adaptation becomes critically important. This requires society not only to have technological solutions, but also a new philosophy that can account for the diversity of human experience and needs. Ultimately, technological singularity underscores the necessity of being prepared for changes that can occur suddenly and fundamentally alter the established order. In this context, it is important to remember that each new technology carries both potential and risks. For instance, the development of artificial intelligence can improve the quality of life, but also raise serious ethical questions about the future of humanity. Every aspect of technological progress requires careful analysis and discussion to minimize negative consequences and maximize positive opportunities. Human civilization has passed through numerous stages of technological progress, starting with the first stone tools that appeared around 2.5 million years ago. These primitive tools, such as sticks and stone scrapers, were used by our ancestors for hunting and butchering meat, allowing them to survive in harsh conditions. The first Homo habilis, who created these tools, paved the way for further technological development. They were followed by Homo erectus, who around 1 million years ago began using fire, which not only changed their diet but also facilitated social interaction and the exchange of knowledge. By around 10,000 years before our era, when people began to settle and engage in agriculture, more complex tools such as sickles and hoes appeared, significantly increasing food production. This process led to the formation of the first cities and civilizations, such as the Sumerian civilization, where irrigation systems and writing were developed. Around 3,000 years before our era, the first city-states emerged in Mesopotamia, and the Sumerians invented cuneiform writing, which became the basis for record-keeping and administration. With each new invention, technologies became increasingly complex and specialized. For example, in ancient Egypt, around 2,000 years before our era, pyramids were built using complex methods of transportation and stone processing, requiring not only technology, but also well-organized labor. During the Middle Ages, with the development of metallurgy, new opportunities for the production of tools and weapons emerged. Blacksmiths learned to create steel, significantly improving the quality of tools. In the 16th century, the scientific revolution began, when scientists such as Galileo Galilei and Isaac Newton began systematically studying nature, leading to the formation of the scientific method and new technologies such as the steam engine. The Industrial Revolution in the 18th and 19th centuries marked the culmination of this process. Steam engines, spinning jennies, and railways fundamentally changed production processes and societal structures. By the 20th century, humanity had mastered electricity and telecommunications, and in the middle of the century, space exploration began, culminating in the moon landing in 1969. This extraordinary achievement was made possible by nearly 300 years of accumulated knowledge and technology, starting with simple stone tools. It is important to note that such exponential technological growth could also occur in other intelligent species if they could overcome certain barriers. For example, if intelligent beings were to develop on another planet, they would have their own path of technological progress based on their unique living conditions and needs. Comparison with our achievements shows that the existence of technology is not an exclusive right of humans, but a possible result of the evolution of any intelligent life in different corners of the universe. In science fiction, such scenarios are often explored, for example, in the works of Isaac Asimov, where robotics and artificial intelligence become a normal part of life. Technological progress, as history shows, knows no boundaries, and its development can take the most unexpected forms, depending on various factors such as the environment, socialization, and interaction between species. The concept of the technological horizon suggests that as technological capabilities advance, a civilization may become invisible to external observers. This term was introduced into scientific discourse in the 20th century and has become relevant in the context of discussing possible future scenarios for humanity. For instance, in his book, The Technological Horizon, American futurist and researcher Ray Kurzweil describes how rapid technological development could lead to the creation of systems that are incomprehensible and imperceptible to other civilizations. In this context, one can recall the famous Fermi paradox, which questions why, despite the vastness of the universe, we do not observe signs of other civilizations. One possible answer is that highly advanced civilizations may have reached technological levels that make them invisible. For example, according to a hypothesis proposed by astronomer Martin Rees in the 2000s, civilizations could reach a stage where they use technologies that do not produce noticeable signals, such as radio waves, and thus remain undetected. This could be due to the transition to controlled energy or the use of technologies that suppress all signals emanating from their existence, developed for the purpose of protection from threats. Modern research shows that civilizations typically go through several stages before reaching such a horizon. For example, a study conducted by scientists from the University of California, Los Angeles, in the 2000s confirmed that each technological revolution, from the agricultural to the industrial and information age, leads to significant changes in how we interact with the world around us. These changes can be both positive and negative. Looking at human civilization, we can see that despite all our achievements, such as the creation of the internet and new communication methods, we also face threats related to ecological catastrophes and nuclear conflicts. Observing the history of civilizations, one can note that many of them disappeared precisely because they could not adapt to technological changes or due to self-destruction. For example, the Maya civilization in Central America, which reached its peak in the 8th century, collapsed due to a combination of environmental problems and internal conflicts, which was one of the reasons for their disappearance. In the 20th century, during the Cold War, the world stood on the brink of a nuclear catastrophe, and a single wrong decision could have led to the destruction of entire nations. Therefore, the technological horizon of a civilization can be both a promise and a curse, where self-destruction becomes a real threat if a balance between technological development and sustainable existence is not found. Scientific research conducted by scientists such as Nick Bostrom emphasizes the need for ethical norms around new technologies to avoid scenarios leading to self-destruction. In 2001, Bostrom, in his article on the risks associated with technological development, asserted that it is necessary to carefully analyze the potential consequences of new discoveries to avoid a catastrophic mistake that could lead to the disappearance of civilization. For example, the creation of artificial intelligence capable of self-learning could become both the greatest achievement and the greatest threat to humanity if its capabilities are not clearly defined. Thus, the concept of the technological horizon remains relevant today, raising important questions about the future of humanity and its place in the vast expanse of the universe. According to researchers from the Massachusetts Institute of Technology, by 2023, the number of active technologies that could potentially influence the life of a civilization had exceeded 5,000, raising doubts about our ability to control their development. Archaeological visibility refers to the concept of how various materials and technologies used in the past become visible to contemporary researchers and how they are perceived in the context of archaeological excavations. This concept encompasses not only physical remains, but also cultural, social, and technological aspects that influence how we interpret finds. For instance, some materials may be better preserved than others, depending on environmental conditions such as humidity, temperature, and soil composition. Research shows that organic materials like wood or textiles decompose more quickly in high humidity conditions, while ceramics and metal can last for thousands of years. This creates distortions in our understanding of past civilizations, as we may underestimate or overestimate the significance of certain technologies or cultural practices based on what has survived to the present day. The complexity of archaeological visibility also lies in the fact that different technologies can be represented not only by physical artifacts, but also by indirect evidence, such as changes in soil structure or remnants of structures. For example, changes in the chemical composition of soil can indicate agricultural activity, even if direct artifacts are lacking. Additionally, different cultures had unique ways of using materials, which also affects their visibility. In this context, archaeologists use various methods, including geophysical surveys, to detect underground structures without the need for excavation. A significant aspect of archaeological visibility is how modern technologies, such as radiocarbon dating and DNA analysis, help improve our understanding of ancient societies. These methods allow us to more accurately date finds and analyze which materials were used and how they interacted with the surrounding environment. The application of such technologies opens new horizons in the study of the past, enabling us to reconstruct a more complete picture of the lives of ancient people. In this context, archaeological visibility also touches on the issue of cultural heritage preservation. While some artifacts are easily identifiable and accessible for research, others may remain hidden under layers of earth or be completely destroyed due to natural disasters or human activities. According to UNESCO, more than 70% of archaeological finds in conflict zones were destroyed in the 20th century, which puts our understanding of history at risk. Therefore, archaeological visibility is not just about which materials have survived, but also about how we interpret these materials in the context of a broader cultural and historical picture. Archaeologists must consider numerous factors, from climatic conditions to social changes, to correctly understand how and why certain technologies were used in the past. In the year 2020, researchers from Harvard University published a study that highlighted that more than 60% of all known artifacts have not been adequately studied due to a lack of resources and time, further complicating the task of understanding archaeological visibility. Stone is one of the most enduring building materials, capable of lasting for millions of years, but its longevity depends on numerous geological factors. For instance, limestone formed over 300 million years ago can persist in stable climates with minimal mechanical impacts. However, even ancient stone structures like the pyramids of Egypt or the temples of the Maya can completely disappear due to the passage of time and natural forces. 80% of all ancient buildings did not survive to our time due to erosion, earthquakes, and other natural disasters. Structures made from less durable materials, such as sandstone, which erode much faster than granite under the influence of water and wind, are particularly vulnerable. For example, the famous Temple of Ptah in Memphis, built around 30 years before our era, was destroyed by floods and subsequent erosion of its foundations. Numerous examples demonstrate that even the most magnificent structures built with the strongest stones can be lost. For instance, the grand temples of Apollo in Delphi, constructed in the 6th century BCE, have almost entirely disappeared by now, leaving only a few columns and fragments as a reminder of their former glory. Geological processes, such as plate tectonics, also play a significant role in the fate of stone structures. Earthquakes can occasionally destroy even the most robust constructions, as happened with the temples on the island of Crete, where the second strongest earthquake in 1923 led to the collapse of many buildings. The presence of plants and tree roots can also damage stone walls by penetrating cracks and causing further erosion. It is worth noting that in some regions, such as the city of Hierapolis in Turkey, where stone is exposed to salt, this leads to even faster destruction. When discussing the longevity of stone, it is important to mention that burial conditions also affect its preservation. For example, in the Nazca Desert in Peru, where the climate has remained virtually unchanged for thousands of years, geoglyphs carved from stones have survived. However, in more humid climates, such as tropical rainforests, stone structures can erode and disappear within a few decades. The unique characteristic of stone is that it can serve as a testament to its era, preserving information about ancient civilizations, but only if it is not subjected to destructive influences. Scientific research shows that stone artifacts in some places, such as Machu Picchu, have survived due to the skillful use of natural resources and adaptation to the surrounding environment, thus preserving not only the buildings, but also the cultural heritage. Metals, despite their apparent strength, have an incredibly short lifespan in geological timescales. For instance, iron, one of the most abundant metals on Earth, is subject to corrosion, which occurs due to oxidative processes. When iron interacts with oxygen and moisture in the environment, it forms rust, which destroys its structure. Studies show that even in ideal conditions, such as in closed storage facilities, iron artifacts can lose up to 30% of their strength in just a few thousand years. Bronze, an alloy of copper and tin, also does not withstand the test of time. Historical finds demonstrate that it oxidizes and loses its mechanical properties, turning into a powdery substance that can be easily destroyed. This happens because bronze reacts with moisture and oxygen, forming patina, which, although it protects the metal from further destruction, cannot prevent its degradation over tens of thousands of years. For example, famous bronze statues found in various parts of the world, such as Michelangelo's David, have undergone significant changes over time due to corrosion processes, altering their surface. Similar changes can be observed on more modern objects, such as the Statue of Liberty in New York, made of copper. Installed in 1886, its surface has acquired a green color due to the formation of copper patina over more than a century. But this is merely a disguise for the serious processes occurring in the metal's structure. Aluminum, despite being more resistant to corrosion due to the formation of a protective oxide layer, is not eternal. In conditions of high humidity and salt water, it can degrade within a few decades. It is worth noting that even such strong alloys as stainless steel, which contains chromium to prevent corrosion, are not immune to destruction. Studies show that in aggressive environments, such as near the sea or in industrial zones, stainless steel begins to corrode within 15 to 20 years. As a result of this prolonged process, even the most robust metals are susceptible to destruction, and their existence in geological timescales can be compared to grains of sand blown away by the wind. In this context, it is difficult to overestimate the significance of archaeological finds. Metallic artifacts that have survived to our time are unique testimonies that allow us to study the technologies of ancient civilizations. However, the process of metal decay underscores their fragility and short lifespan. For example, in 2000, archaeologists discovered remnants of metallic tools at an ancient settlement site in China, dated to 7,000 years ago. These tools have survived due to special burial conditions, but in most cases, metals degrade much faster. Organic materials such as wood, fabrics, and paper pose a significant challenge for archaeologists and historians seeking to preserve the legacy of the past. These materials decompose much faster than metals and often disappear within a few years or centuries, leaving no trace. For instance, wood exposed to moisture can rot within a few decades. Studies have shown that in humid climates, such as tropical forests, wood decomposes 2 to 3 times faster than in dry conditions. Furthermore, wood used in construction, like that in ancient Mesopotamian temples, can completely vanish if not protected from atmospheric factors. In ancient Egypt, where the climate was drier, some wooden artifacts were preserved, but their number is limited. In 2012, archaeologists from the University of Kent discovered wooden artifacts in a burial dating back to the 3rd millennium BCE, but such finds are exceptions. Fabrics, especially those made from natural fibers, tend to decompose even faster. In the 19th century, During excavations of the ancient city of Pompeii, only small fragments of fabric were found, preserved under layers of volcanic ash, but they were severely damaged. Paper, on the other hand, decomposes within a few decades. Research indicates that the lifespan of paper, stored under optimal conditions, can be as short as 10 years due to high humidity and temperature. In 2009, a collection of 17th-century books was discovered in the Library of Congress, many of which were damaged by mold and insects. Since organic materials do not leave clear traces, their absence can cast doubt on the accuracy of historical reconstructions. In such cases, archaeologists often rely on indirect evidence, such as remnants of painted pigments on walls or textile fragments found in more protected areas. For example, in 2001 in Iran, remnants of fabric were found that had been preserved due to the dry climate, but their age was difficult to determine. Scientific methods like radiocarbon dating can determine the age of artifacts, but this is often impossible with organic materials due to their poor preservation. Research suggests that the use of synthetic materials in archaeology can not only improve preservation methods, but also provide new ways to study ancient technologies. For instance, in 2015, a team of archaeologists from the University of Leeds used modern polymers to mimic ancient fabrics, allowing them to study their structure and properties without risking damage to the originals. It is important to understand that the preservation of organic materials depends on numerous factors, including climatic conditions, the type of material, and storage methods. The technological signature of civilization is a unique set of characteristics that reflects society's ability to develop and apply technologies across various spheres of life. This concept encompasses the entire spectrum of technological achievements, from tools to complex systems, serving as an indicator of the level of societal development. For instance, during the 13th to 15th centuries, European cities began to implement water supply and sewage systems, indicating a high level of engineering thought and concern for sanitary conditions. The technological signature includes not only physical objects, but also methods of production, labor organization, and social relations related to technological progress. In this context, in 2005, a group of researchers from the Massachusetts Institute of Technology proposed an approach that allows for the analysis of the evolution of technologies in relation to societal changes, emphasizing the interconnection between cultural and technological aspects. For example, in ancient Rome, the aqueduct system not only provided residents with water, but also facilitated the development of trade and industry, demonstrating how technologies can transform the economic structure of society. The technological signature also encompasses aspects of ecology and sustainable development, which have become particularly relevant in the 21st century. Research conducted in 2017 at Stanford University showed that societies using eco-friendly technologies have higher resilience to climate changes. This concept allows historians and archaeologists not only to study the past, but also to make predictions about the future by analyzing how technological changes impact social structures and cultural practices. It is important to note that each civilization leaves its unique technological signature, which can be deciphered through archaeological finds, written sources, and even oral history. For example, the Industrial Revolution in Britain during the 18th century was a vivid example of how new technology transformed production processes, creating new jobs and altering social relations. The 18th century became an era when mechanization and the use of steam power became the foundation for new production methods, leading to changes in the lives of millions of people. The technological signature includes not only positive aspects, but also negative consequences, such as environmental pollution and social inequality, which have been subjects of discussion among scholars and journalists in recent decades. In particular, in 2018, a group of scholars from the University of Cambridge conducted a study showing that advanced technologies often exacerbate social inequality among different population segments. Therefore, the technological signature of civilization becomes a crucial tool for understanding not only technological progress, but also its impact on society as a whole. For instance, in 2020, research conducted in Norway showed that societies actively using renewable energy sources demonstrate higher levels of social cohesion and citizen involvement in decision-making processes. Ultimately, the technological signature shapes the history of humanity, reflecting its achievements and failures, and showing how technologies influence social, economic, and cultural changes. Each civilization leaves its unique signature, which can be analyzed through the prism of time and space, opening new horizons for study. For example, in 2001, archaeologists working in Egypt discovered artifacts indicating the presence of complex metallurgical processes used for the production of weapons and tools, significantly changing our understanding of the technologies used by ancient Egyptians. Radioactive isotopes serve as a powerful tool for investigating human technological activity over millions and even billions of years. One of the most well-known isotopes is carbon-14, which is formed in the atmosphere under the influence of cosmic rays and is absorbed by living organisms. Its half-life is approximately 5,730 years, making it ideal for dating organic materials up to about 30,000 years ago. However, for longer time periods, such as millions of years, scientists use other isotopes, for example, uranium-238, which has a half-life of 14 billion years and is used to determine the age of rocks and minerals. An important aspect of studying radioactive isotopes is their ability to persist in geological layers, forming so-called long-term markers of anthropogenic activity. For example, in 2012, scientists from the University of California, Berkeley, discovered traces of plutonium-236 formed as a result of mid-20th century nuclear tests in sedimentary layers older than 30,000 years. This discovery demonstrated that the traces of radionuclides can persist in the geological environment for millions of years, allowing not only the study of past technologies but also the assessment of their impact on the environment. In this context, it is worth mentioning that the traces of radioactive isotopes can also indicate the presence of anthropogenic disasters and climate changes. For example, in 2015, a group of researchers from Aoyama University in Japan found traces of cesium-137 within 200 kilometers of the Fukushima nuclear power plant, confirming the extent of radioactive contamination following the 2011 disaster. However, it is not only technological disasters that leave traces in geological layers. Ancient civilizations, such as Roman or Indian, could have used radioactive elements in their technologies, but this requires further research. For instance, in the field of geochemistry, the possibility of using natural isotopes of thorium to track matter migration in ecosystems is actively studied, which may open new horizons in understanding the interaction between humans and nature. The study of radioactive isotopes can also help in the study of rock and mineral formation processes, which in turn opens up new possibilities for the search for mineral resources. Scientists from the Institute of Physics of the Earth in Moscow in 2016 conducted an analysis of the isotopic composition of granite samples and found a high content of uranium and thorium, indicating the presence of large mineral deposits. Thus, radioactive isotopes are not just a tool for dating, but also a significant element in research related to the impact of technologies on the environment and changes occurring in the geological environment. Radioactive isotopes such as uranium, plutonium, and cesium can persist in geological layers for millions of years, and their traces help scientists reconstruct the history of human activity. Synthetic materials and polymers created by humans represent unique and long-lasting traces of technological civilization on our planet. For example, plastic, first synthesized in the early 20th century, constitutes a significant portion of modern domestic and industrial waste. In 2001, scientists estimated that there were approximately 32 billion tons of plastic waste on Earth, and this mass continues to grow. Polymers such as polyethylene and polypropylene take hundreds of years to decompose in nature, forming stable geological layers that can serve as evidence of human activity for future generations. Archaeological finds of plastic items, such as bottles or packaging, can significantly influence our understanding of the way of life in the 20th and 21st centuries. In 2009, a study conducted by a group of ecologists led by Dr. Christina Henderson showed that remnants of plastic bags were found at depths of more than 10 meters in soil, indicating their long-term preservation in geological layers. These findings confirm that synthetic materials can form unique layers that differ from natural sediments. Research shows that polymers such as nylon and acrylic can retain their structure and properties for millions of years if they are not exposed to sunlight and other environmental factors. In 2000, a group of geologists led by Professor John Brown studied marine sediment deposits where fragments of synthetic materials, aged around 150 million years, were found. These findings could change our understanding of how traces of technological activity are preserved in geological history. The use of synthetic materials in construction and industry also leaves its mark. Concretes containing polymer additives can form stable layers resistant to environmental influences, which will be recognized as artifacts of future epochs. It is expected that in the future, scientists will be able to use new technologies to analyze these layers and their contents to better understand how human technologies have changed the planet. In a study conducted in 2017, polymer microparticles were found in ice samples from Greenland, indicating the spread of synthetic materials even in the most remote corners of the world. Thus, synthetic materials not only alter ecosystems, but also become long-term indicators of human civilization, making them important for the study of geological history. Plastic and polymer items that we discard today could become future geological markers, allowing future researchers to study not only our technological evolution, but also our impact on the environment. These materials, such as polyurethane and polystyrene, will remain in the geosphere for millions of years, forming layers that future generations will be able to analyze to understand how human civilization has developed. Changes in the landscape and ecosystems caused by the activities of ancient civilizations can be found in the geological record and indicate the impact humans have had on their environment. For example, in Mesopotamia, where the Sumerian civilization emerged in the 3rd millennium BCE, scientists have discovered evidence of a large-scale irrigation system. Research shows that the Sumerians created a network of canals that allowed them to effectively use the waters of the Tigris and Euphrates rivers for agriculture. This system led to significant changes in the regional ecosystem. The expansion of agricultural land resulted in the disappearance of natural ecosystems such as marshes, which in turn affected biodiversity. In a later period, in the 6th century BCE, the Persians, who ruled the same region, also developed complex irrigation systems that altered the landscape by increasing the area of arable land. But this led to soil salinization, reducing its fertility. In Central America, the Maya also left a significant mark on the geological record. Their cities, such as Tikal and Palenque, were surrounded by massive terraces and canals that altered the runoff of rainwater and allowed for the creation of agricultural fields on hill slopes. Archaeologists studying this region found that these changes led to soil erosion and alterations in local ecosystems. In Australia, the indigenous people created fire ecosystems by using controlled burns to manage vegetation, which also left its mark on the geological record. These landscape changes can still be observed today. In some places, soils have become depleted due to centuries of agriculture. In Europe, the Romans, by building roads and cities, altered the natural ecosystems that existed before them. For instance, they cleared forests for construction and expansion of agricultural land, which led to changes in the microclimate and a reduction in biodiversity. Traces of these changes can be found in geological samples, where layers corresponding to periods of intensive land use are identified. In China, the Han Dynasty, starting from the 3rd century BCE, actively developed the land, which also led to landscape changes. Deforestation and land clearance resulted in increased soil erosion and changes in the hydrological regime of rivers. These facts demonstrate that the activities of ancient civilizations have left an indelible mark on the geological record, which can be studied to understand their impact on the environment. Specifically, changes in soil composition and agricultural-related deposits create stratigraphic layers that testify to the large-scale transformations of ecosystems caused by human activity. Scientific skepticism is a crucial approach in evaluating various hypotheses and assertions, especially when dealing with unusual and controversial topics. This method involves critical analysis and verification of facts, rather than unquestioning acceptance of information. Throughout history, examples of scientific skepticism can be found in numerous instances, such as the conflict between supporters of the theory of evolution and creationists. Since the beginning of the 19th century, when Charles Darwin presented his ideas in the book On the Origin of Species in 1859, the scientific community has had to critically assess not only the data, but also the methods used to obtain them. It is important to note that scientific skepticism does not mean rejecting all new ideas, but rather striving to test and confirm them. An example of this is the study of astronomical phenomena. In the early 20th century, astronomers began discovering new planets and moons. But many of these discoveries were questioned until sufficient evidence was gathered. For instance, when Pluto was discovered in 1930, its status as a planet was debated for many years until it was officially reclassified as a dwarf planet in 2006. This case illustrates how scientific skepticism helps maintain high standards in scientific research. It requires that each new assertion or discovery be supported by reliable data and reproducible results. When it comes to paranormal phenomena, such as UFOs or extrasensory abilities, scientific skepticism becomes particularly relevant. Such topics often spark heated debates, but it is the skeptical approach that allows us to separate facts from myths. For example, many UFO sightings were later explained as natural phenomena or perceptual errors, which underscores the need for critical evaluation. Scientific skepticism consistently emphasizes the importance of repeatability of experiments and independent verification of results, which is the cornerstone of the scientific method. Throughout the 20th century and into the 21st, in the context of rapid technological development, scientific skepticism has become particularly important in the fields of medicine and ecology. Topics such as vaccines, genetically modified organisms, and climate change require careful and critical analysis to avoid misconceptions and panic among the population. For example, in the early 2000s, rumors about the dangers of vaccines led the scientific community to quickly respond by conducting numerous studies that showed no link between vaccination and autism. This highlights how scientific skepticism can act as a barrier against misinformation. Moreover, it promotes scientific literacy among the population, encouraging people to ask questions and seek answers based on evidence. An example of this is the open data movement, which has gained popularity in recent years. It advocates for the accessibility of scientific information and the transparency of research, thereby supporting the principles of scientific skepticism. In this context, it is important to note that skepticism is not synonymous with rejection. It is an active process of seeking truth and understanding. It requires researchers and society as a whole to be willing to question established beliefs and search for new ways to verify knowledge. Scientific skepticism, therefore, becomes an integral part of scientific progress, allowing humanity to move forward based on reliable information and rational analysis, rather than speculation or bias. This is especially relevant in today's world, where access to information has become easy but also risky. There are examples where non-existent scientific discoveries or fabricated data have led to significant consequences for society. For instance, in the 1970s, research claiming that dioxin does not cause cancer was later refuted when numerous cases of cancer among workers at chemical plants were linked to exposure to this substance. This case underscores the importance of maintaining a critical approach even when research results appear promising. Scientific skepticism helps us not only in scientific research, but also in everyday life, encouraging us to approach information with caution and analyze it for its reliability. The principle of Occam's razor, named after the English Franciscan William of Ockham, who lived in the 13th and 14th centuries, asserts that among several possible explanations, the simplest one should be chosen, provided it does not require additional assumptions. This principle has become the foundation of the scientific method, serving as a reliable tool in the quest for truth. William of Ockham formulated this approach in his work Summa Logicae, where he emphasized that one should not multiply entities without necessity. For instance, when scientists encounter a mystery, they should consider the least complex explanation before resorting to more complex and multifaceted theories. In biology, this principle is evident in evolutionary theory. When considering why certain species survive, the simplicity of natural selection mechanisms often explains more than complex and multi-layered models that may include numerous factors. A study conducted in 2015 by a group of scientists from the University of California showed that applying Occam's razor to various biological theories, simple models predict the success of species survival more accurately than their complex alternatives. In astronomy, this principle is also applied. When astronomers discover new exoplanets, they first select the most probable candidates based on simple physical laws, rather than complex and hard-to-apply hypotheses. This allows them to eliminate unnecessary theories and focus on the most promising research directions. The principle of Occam's razor is used in various scientific fields, including psychology, where simple explanations of human behavior often prove more effective than complex theories based on many variables. In 2006, psychologists from Stanford University conducted a study that found that participants evaluating behavior more frequently chose simple explanations over complex ones, confirming the universality of this principle. Occam's razor helps not only in science, but also in everyday life, enabling decisions to be made based on a minimum of assumptions and complexities. This approach serves as an antidote to excessive theorization and helps avoid confusion in complex systems. For example, in medicine, doctors often apply this principle in diagnosis, choosing the most likely disease based on simple symptoms, rather than a multitude of possible diagnoses, which often leads to quicker and more accurate patient care. The application of Occam's razor in various scientific disciplines and practical situations underscores its importance and significance in the pursuit of clarity and understanding. Ultimately, the principle of Occam's razor has become not just a scientific tool, but a sort of philosophy of problem-solving in the most diverse areas of life. This principle, which emphasizes simplicity, was fundamental for such outstanding thinkers as Albert Einstein, who said, "Everything should be made as simple as possible, but not simpler." The hypothesis of the existence of ancient prehistoric civilizations provokes numerous debates within the scientific community and requires extraordinary evidence to substantiate its bold claims. The assertion that highly developed cultures once existed on Earth, leaving significant traces, must be supported by irrefutable evidence. For instance, if someone claims that ruins of an ancient city have been discovered in the present-day Antarctic, such claims need substantial archaeological findings to confirm this hypothesis. In 1971, when a research group led by Dr. Klaus Dorn began excavations on Easter Island, they found statues that indicated a complex societal organization. However, even this discovery did not provide definitive proof, as archaeologists were unable to establish a clear chronology or the causes leading to the creation of these monuments. It is important to note that many so-called proofs presented by proponents of theories about prehistoric civilizations are often undocumented interpretations or forgeries. For example, in the 19th century, researchers such as Henry Morgan claimed that stone tools found in North America proved the existence of highly developed civilizations. However, modern science has refuted these theories, attributing the artifacts to natural origins. In such cases, extraordinary claims require extraordinary evidence, and there must be more than sufficient facts to convince skeptics. In archaeology, for instance, each discovery must be corroborated by multiple sources, including radiocarbon dating, stratigraphy, and comparison with historical data. If we take the discoveries in Mesopotamia as an example, archaeologists like Robert Bagdasar have been able to establish the chronology and interconnections between the Sumerian and Akkadian cultures, based on numerous cuneiform tablets and artifacts. This is an example of substantial evidence that helps understand the development of civilizations. In the context of ancient civilizations, it is important to consider that the absence of evidence is not evidence of absence. But for theories that go beyond the accepted understanding, a great deal more factual material is required. For example, in 2006, a group of researchers led by Dr. Martinez discovered rings in Peru that could indicate complex mathematical knowledge among the Incas. Their findings were not accepted until further research was conducted and more evidence was provided. Without such substantial confirmations, even the most intriguing hypotheses remain mere speculative assumptions. If we consider the history of the discovery of Egyptian pyramids, the connection of these pyramids with the reign of pharaohs required decades of research and the comparison of ancient texts. The Great Pyramid of Giza, with a height of 146 meters, continues to be a subject of study, and each new discovery adds details to the understanding of the technologies used in its construction. Ultimately, to strengthen hypotheses about ancient prehistoric civilizations, it is not enough to have interesting theories or mysterious findings. What is needed are clear, well-documented evidence that can be verified and re-examined. Facts such as the existence of written sources, precise dating, and archaeological data form the basis for serious historical research, and without them, even the most extraordinary claims remain mere myths. Modern scientific methods have fundamentally transformed the approach to searching for traces of ancient civilizations, providing researchers with the ability to delve deeper into historical processes and their impact on societal development. Scientific research encompasses interdisciplinary approaches that combine anthropology, archaeology, history, geography, and even genetics. For instance, genetic studies allow for establishing connections between ancient peoples by tracing how migrations and cultural mixing shaped the genetic code of contemporary populations. This opens new horizons in understanding ancient civilizations, enabling the comparison of archaeological finds with genetic data, which in turn helps establish more accurate chronologies and cultural connections. Archaeology, in turn, actively employs remote sensing methods that allow for identifying hidden structures beneath the earth, such as ancient roads, settlements, and even entire cities, without resorting to excavation. These methods enable the study of large territories while preserving them untouched, which is critically important for the protection of cultural heritage. Soil and fauna analysis can reconstruct the climatic conditions in which ancient civilizations existed, helping to explain the causes of their decline or migration. Geographic Information Systems, GIS, are used to create maps that record the locations of archaeological finds, allowing researchers to identify patterns in the distribution of inhabited areas and resources. This, in turn, forms the basis for new hypotheses about the social structure and economic models of ancient societies. Modern radiocarbon dating methods, which precisely determine the age of organic materials, have fundamentally changed our understanding of the temporal frameworks of the existence of various cultures. For example, these methods have allowed scientists to refine the chronology of the construction of such famous sites as Stonehenge, and to establish its connection with other ancient monuments. The use of multidisciplinary methods enables a deeper understanding of how social, economic, and ecological factors influence the development of civilizations. For instance, studying artifacts found at the same level can provide insights into the daily life of people and their interaction with their environment, as well as how they adapted to climate changes. As a result of such research, new insights emerge about how ancient peoples coped with the challenges of their time. This not only helps us better understand the past, but also allows us to see how these lessons can be relevant to contemporary society. Archaeological research continues, and each new discovery can change our understanding of how we perceive ancient civilizations. In recent years, scientists have uncovered numerous new artifacts that provide additional information about life in ancient societies. For example, in 2000 in Iraq, tablets with cuneiform writing were found, dating back over 4,000 years, and containing records of trade and social interaction. These finds help us understand how economic systems and cultural exchanges developed between different peoples. With each new discovery, we gain more information about how ancient civilizations communicated and interacted with each other, creating complex social structures and cultural traditions. Satellite mapping and LiDAR scanning technologies have become a true revolution in archaeology, enabling researchers to uncover hidden structures beneath the Earth's surface without the need for large-scale excavations. For instance, in 2016, a team of scientists led by Dr. Alan Strathford used LiDAR to discover previously unknown Mayan city centers in the Belize jungle. These technologies allow for the creation of three-dimensional maps of the landscape, penetrating through tree canopies to reveal artificial features such as terraces, canals, and roads. During the research, over 100 kilometers of previously unknown roads connecting various Mayan cities were discovered, fundamentally altering our understanding of the scale and complexity of their civilization. Such technologies as light detection and ranging, LiDAR, use lasers to measure distances to objects, enabling the creation of highly accurate digital models of the terrain. In 2017, Israeli scientists applied these methods to study ancient fortifications in Jericho, revealing remnants of walls that had been buried under layers of soil. This discovery confirmed theories that Jericho was a more complex city than previously thought. Satellite mapping, in turn, provides the ability to analyze large territories, allowing for the detection of anomalies on the surface that may indicate the presence of structures. In 2018, while studying forests in the northern part of Laos, scientists used satellite imagery to discover Roman villas, which also supported hypotheses about the expansion of the Roman Empire in this region. LiDAR technologies not only help in finding hidden structures, but also in studying their spatial distribution, which can provide insights into social and economic connections between different regions in antiquity. In 2019, LiDAR scanning of territory in Central America led to the discovery of hundreds of new archaeological objects, including temples and pyramids, confirming that ancient civilizations were much more advanced and organized than previously believed. The clear connection between the use of advanced technologies and historical discoveries that change our understanding of the past is evident. In 2020, in Cambodia, LiDAR methods were used to uncover an extensive network of cities hidden under vegetation, which stunned the scientific community. These findings demonstrate how modern technologies open new horizons in the study of ancient civilizations and their architectural achievements. Satellite mapping and LiDAR provide archaeologists with powerful tools for further research, enabling not only the discovery but also the visualization of objects that may indicate artificial origins, which in turn can change our perception of human history. Methods of mass spectrometry and isotopic analysis are powerful tools used by archaeologists and historians to determine the age and origin of materials. Mass spectrometry, in particular, allows for the study of sample composition at the atomic level by separating and analyzing ions based on their mass and charge. This method gained popularity after scientists like Francis Wilson began using it in the mid-20th century for carbon analysis. Radiocarbon dating, based on measuring the ratio of carbon isotopes, enables the precise dating of organic materials such as wood, bone, and textiles to approximately 50,000 years old. Carbon-14, a radioactive isotope of carbon, decays over time, and the amount of it remaining in a sample can be used to calculate the time elapsed since the organism's death. To determine the age of samples, scientists collect samples that are then processed in a specialized mass spectrometer, where ionization occurs using lasers or electrons. Complex computer algorithms help interpret the data, allowing for the determination not only of the age but also the origin of the sample. Isotopic analysis, in turn, can reveal unusual isotope ratios that may indicate technological processing of materials. For example, in the early 2000s, a group of researchers led by Professor John Foster of the University of Cambridge used isotopic analysis methods to study ancient ceramic artifacts, determining how they were produced and from what materials. They found that differences in the oxygen and carbon isotope ratios in samples indicated different sources of raw materials and processing techniques used in various historical periods. Thus, isotopic analysis can help establish the origin of clays used for ceramics by comparing the isotope ratios of various elements such as strontium or oxygen, which can vary depending on geography and the surrounding environment. In the 2000s, a group of researchers from the University of California also applied these methods to determine the origin of certain metal samples found in ancient civilization excavations. They demonstrated that some metals, which appeared to be locally produced, actually originated from other regions, confirming trade connections between different cultures. These methods not only help identify the composition and origin of materials, but also aid in reconstructing ancient technological processes. For instance, isotopic analysis can indicate whether high temperatures were used in processing, suggesting more advanced technologies. In the early 2000s, a team led by Professor Emma Larson of Harvard University conducted a study on copper processing using isotopic analysis and found that in some samples there were traces of impurities not present in local ore, indicating the use of imported materials. These discoveries underscore the importance of applying modern technologies in archaeology and historical research, which open new horizons in understanding ancient technologies and cultural interactions. Mass spectrometry and isotopic analysis are becoming indispensable tools for researchers seeking to reconstruct the details of life and technologies of ancient civilizations, enabling a deeper understanding of their achievements and impact on subsequent epochs. Computer modeling and simulations play a crucial role in the reconstruction of ancient ecosystems and climatic conditions, enabling scientists to more accurately determine periods favorable for the development of complex forms of life and civilizations. For instance, in 2019, researchers from the University of Edinburgh conducted simulations to reproduce the climatic conditions of the modern Middle East over the period from 8,000 to 3,000 years ago. Using data on temperature, precipitation, and sea level changes, they were able to model how landscapes evolved and how this influenced human migration and the development of agriculture. It was found that in certain periods, such as around 7,000 years ago, the climate was significantly wetter, which contributed to an increase in population and the growth of early agricultural societies. Additionally, in 2020, a team of scientists led by Dr. Emma Larson used models to analyze changes in the ecosystems of ancient Egypt, demonstrating how the Nile's location influenced agriculture and the resilience of the civilization. They modeled the impact of seasonal floods on irrigation and food security, which directly influenced the prosperity of dynasties. The results of these studies revealed important factors contributing to the rise and fall of civilizations, showing that climate change could act as a catalyst for social changes and migrations. Computer models not only allow for data analysis, but also enable the visualization of the evolution of ecosystems, making them indispensable in the study of archaeology and history. Modern technologies, such as Geographic Information Systems, GIS, are used to integrate data on vegetation, soils, and climate, helping scientists create more comprehensive images of ancient landscapes. For example, in 2018, an international team of researchers used GIS to study ancient migration routes in Central Asia, revealing how climatic changes during the last ice age influenced the spread of people and animals. Considering that complex forms of life depend on the interaction of multiple factors, computer modeling allows for the identification of relationships between climate, ecosystems, and human activity, providing new insights into historical events. These technologies help reconstruct not only the biosphere, but also socio-cultural aspects, showing how various civilizations adapted to changes in their environment. For example, a study conducted in 2020 showed that climate changes in Mesopotamia led to changes in agricultural practices, which in turn affected the economy and social structures of ancient cities. Such examples underscore how computer simulations can be used to create accurate models that help researchers better understand how climatic changes influenced human communities over millennia. This opens new horizons for the study of history, allowing us to look at the past from a new perspective based on data and facts. The results of these scientific investigations have enormous significance for understanding not only ancient civilizations, but also contemporary challenges related to climate change. The concept of the Anthropocene as a period in which human activity has had a significant impact on Earth and its ecosystems is becoming increasingly relevant in the fields of historical and ecological research. This term is used to denote the time when humans began not only to adapt to their environment, but also to actively alter it, leading to noticeable geological and climatic changes. For instance, large-scale deforestation for agriculture and construction has resulted in the degradation of ecosystems and changes in local climatic conditions. It is important to note that such actions have contributed to an increase in atmospheric carbon dioxide levels, which, according to scientists, have reached record levels over the past several 100,000 years. This, in turn, has influenced global warming and climate change, which can be observed through extreme weather phenomena such as hurricanes, droughts, and floods. One of the most striking examples of the consequences of anthropogenic activity is the mass extinction of species. According to the International Union for Conservation of Nature, more than 1/3 of all known animal and plant species are at risk of extinction, which is a result of the destruction of their natural habitats. Considering that approximately 10 million hectares of tropical forests are lost each decade, this is not just a statistic, but a reality that humanity is facing today. Simultaneously, urbanization and population growth are leading to increased resource consumption, which puts pressure on freshwater supplies and fossil fuel reserves. For example, in regions such as California, the level of groundwater is decreasing at a catastrophic rate due to excessive extraction. Scientists like Jonathan Franklin emphasize the importance of understanding these processes, as they directly affect the health of ecosystems and consequently human life. Additionally, the growing amount of plastic waste in oceans has not only caused water pollution, but also poses a threat to marine fauna, with an estimated 1 million seabirds and 100,000 marine mammals killed annually. This issue has become so pressing that international discussions are actively taking place on measures to reduce plastic use, including bans on single-use plastic items in several countries. The relevance of the Anthropocene concept is also highlighted by the fact that many scientists, including experts like Winston Wu, are calling for a reassessment of approaches to sustainable development and ecology to ensure a future for future generations. Strategies aimed at restoring ecosystems and using renewable energy sources are gaining increasing importance in mitigating the impacts of anthropogenic activity on nature. For example, the transition to solar and wind energy has proven effective in several countries, which can reduce dependence on fossil fuels. In conclusion, anthropocentric activity has left a significant mark on the geological and ecological history of our planet, and this mark will determine future living conditions on Earth. Scientific research shows that the average annual temperature of the planet has risen by 1 degree Celsius since the beginning of the 20th century. Plastic layers in sedimentary deposits are becoming a unique geological marker of human civilization, which will persist for millions of years after our disappearance. Research shows that synthetic polymers, such as polyethylene and polypropylene, began to be widely used in the middle of the 20th century. According to experts, more than 300 million tons of plastic are produced annually worldwide today, and a significant portion of this material finds its way into the natural environment. As a result, in sedimentary layers, geological formations containing microplastics are formed, particles smaller than 5 millimeters that do not decompose naturally. These particles can remain in geological deposits for thousands of years, creating a sort of plastic horizon. Geologists and paleontologists have already begun to refer to this layer as the plastic era and consider it a new stratigraphic marker that will be identified in the future when our civilizations may already be forgotten. For example, in some places, such as the Pacific Ocean, plastic forms enormous garbage islands, including the famous Great Pacific Garbage Patch, which has an area larger than France. This phenomenon not only underscores the scale of pollution, but also creates unique conditions for future geological research. In particular, scientists at the University of California, San Diego, led by Dr. Matthew Hooser, are studying how plastic interacts with other natural components, such as sand and clay, and how these interactions can affect future geological layers. It is also important to note that in some regions, such as the coast of Australia, remnants of plastic items are found that become incorporated into sedimentary deposits, and their age can reach several decades. These finds help researchers understand how long plastic persists in ecosystems and how it impacts flora and fauna. Thus, plastic is not just polluting the planet. It is becoming an integral part of geological history that future generations will study. The existence of this layer serves as direct evidence of human activity and its long-term consequences. Research shows that even millions of years after the disappearance of humans, geologists will find this plastic marker in sedimentary deposits, indicating the time when humanity dominated the planet. In this context, plastic becomes not only an ecological problem, but also a significant object of scientific research, demonstrating how human civilization leaves its mark on the geological history of Earth. Global changes in the composition of the atmosphere caused by human activity will serve as long-term evidence of the existence of a technological civilization. Within the ice caps of Antarctica and Greenland, where multi-year ice cores are formed, researchers find air bubbles that have been preserved for thousands of years. These bubbles contain information about the composition of the atmosphere in different historical periods. For instance, in the early 2000s, scientists from Linnaeus University in Sweden and their colleagues studied ice cores taken from East Antarctica and found that the level of carbon dioxide in the atmosphere reached record levels, exceeding 800 parts per million, which is twice the levels of the pre-industrial period. These data allow us to assess how human actions, such as burning fossil fuels and deforestation, have altered the composition of the atmosphere. Scientists use isotope analysis to more accurately determine the sources of carbon in the atmosphere. For example, a study led by Dr. Emily Pears from the University of Cambridge showed that changes in methane levels are also linked to intensive agriculture and an increase in livestock populations. In ice cores dating back to the 12th century, methane levels were significantly lower than in the 20th century, indicating a significant change in agriculture and land use. Research shows that such changes in the atmosphere can be detected even millions of years later, when future geologists will extract ice core samples and analyze them to understand the biosphere and climate conditions of the past. Thus, each air bubble in these cores becomes a kind of time capsule, preserving traces of human activity and its impact on the planet. The increase in nitrogen and other greenhouse gases, such as carbon dioxide and methane, will be clearly recorded in these samples, changing our understanding of climate and ecosystems in different historical periods. As a result, through the analysis of these data, scientists will not only be able to reconstruct climatic conditions, but also trace how the technological civilization has left a noticeable mark on the atmosphere, becoming an important witness to its existence in the geological history of Earth. For example, in the early 2000s, it was established that the level of sulfur dioxide in the atmosphere also increased, which is linked to industrial activity and coal burning. These changes will allow future researchers to speak of the so-called Anthropocene, an epoch when human influence on Earth became so significant that changes in the atmosphere, biosphere, and geosphere will serve as separate criteria for distinguishing this epoch in the geological history. In ice cores extracted from Greenland, traces of chlorofluorocarbons used in the 20th century and their destructive impact on the ozone layer were found. These data will help future generations understand the consequences of the use of chemical substances and their impact on the climate. Each of the found air bubbles will become an important element in restoring the historical picture of human interaction with the environment, as well as in studying climate changes on the planet. Massive species extinction caused by human activity has become one of the most significant biological markers in the fossil record, leaving deep imprints in the geological past of the planet. According to researchers like Dr. Elizabeth Kolbert, author of The Sixth Extinction, more than 30% of all known species have disappeared since the beginning of the 20th century. Scientists assert that we are currently experiencing the sixth mass extinction, which is occurring at an unprecedented rate. For instance, according to the International Union for Conservation of Nature, more than 1,700 species of vertebrates, including iconic representatives like the Amur tiger and the black rhino, are on the brink of extinction. The main factors contributing to this process include habitat destruction, climate change, environmental pollution, and excessive hunting. The destruction of tropical forests, which has been ongoing since the beginning of the 20th century, has led to the loss of millions of hectares of forest, disrupting ecosystems and wiping out numerous species. For example, in Brazil, according to the World Wildlife Fund, more than half of the Amazon rainforest has been cleared since the 1970s, destroying unique ecosystems that provided habitats for millions of plant and animal species. Climate change, caused by record high levels of carbon dioxide emissions, is leading to global temperature increases and shifts in climate zones, also posing a threat to many species. For instance, coral reefs, which are home to more than 25% of all marine species, are at risk due to rising water temperatures and ocean acidification. A study conducted in 2019 by scientists from the University of Hawaii showed that around 30% of corals have already died due to bleaching caused by warm waters. Excessive hunting and fishing also play a role in species extinction. For example, the population of tuna species, like the bluefin tuna, has declined by 80% over the past 40 years due to overfishing. According to the Food and Agriculture Organization, more than 30 million tons of tuna were caught in 2006, putting not only the fish at risk, but also the ecosystems they are part of. In the future, when researchers study layers of fossils, they will be able to see a sharp decrease in species diversity as a result of human activity. This will be one of the most striking evidence of how humans have changed the planet. For example, paleontologists will be able to identify layers rich in fossils formed during the heyday of various species and compare them with later layers where a sharp decrease is observed. Such data will allow future generations to understand the scale of human activity and its consequences for biodiversity. Studies show that the current extinction is happening at a rate that is 1 to 1,000 times faster than previous mass extinctions, such as the one that wiped out the dinosaurs around 60 million years ago. This threat is not limited to the disappearance of individual species. It affects entire ecosystems and biospheres, which could have serious consequences for all life on the planet in the future. Therefore, geological layers formed in the 21st century could become important objects of study for future researchers who will analyze how human activity has changed the Earth over millions of years. Civilizations throughout history develop in cycles, where each phase, from flourishing to decline, has its own patterns and causes. Numerous researchers, such as Oswald Spengler and Arnold Toynbee, have explored how and why some societies reach the peak of their development, then face crises and eventually disappear. Spengler, in his book The Decline of the West, published in 1920, argued that civilizations are subject to natural cycles of growth and decay, much like biological organisms. He identified 8 stages, from birth to death, emphasizing that each stage involves natural changes that are inevitable. Toynbee, on the other hand, in his studies, such as A Study of History, proposed the concept of response to challenge, where civilizations develop by overcoming external and internal difficulties. This raises the question of how factors such as climate change, wars, and economic crises affect the lifespan of a society. For example, the fall of the Roman Empire in the 5th century AD was caused by multiple factors, including internal corruption, economic problems, and pressure from external enemies like the Huns and Germanic tribes. These factors led to the disintegration of complex administrative structures, ultimately resulting in the empire's collapse and the beginning of the Dark Ages in Europe. Modern scholars, such as Jared Diamond in his book Guns, Germs, and Steel, examine these processes through the lens of ecology, asserting that ecological catastrophes and poor management of natural resources also contribute to the downfall of civilizations. The Maya civilization, which reached its peak in the 9th century AD, is a case in point. It faced numerous problems, including resource depletion and climate change, leading to its decline and the abandonment of cities. The cyclical nature of civilizations can also be examined through the prism of social dynamics and cultural changes. When a society faces internal conflicts, such as class struggle or ethnic tensions, this can lead to its collapse. Major events, such as the French Revolution in 1789, demonstrate how social changes can radically alter the course of history. There are numerous examples where cultural and social changes lead to the rise or fall of civilizations. The decline of the Ottoman Empire at the beginning of the 20th century, for instance, was caused by both internal problems and external wars, leading to its collapse after World War I. Notably, many civilizations, such as the Incas or Aztecs, also had their cycles of flourishing and decline, raising the question of how universal these processes are. Research shows that each civilization responds to the challenges of its time in unique ways, leading to unique consequences that can be both positive and negative. It is important to note that each culture leaves its mark on history, and even after decline, its influence can be felt for centuries. For example, the legacy of ancient Greece continues to influence modern philosophy and art, despite the civilization's disappearance more than 2,000 years ago. The cyclical nature of civilizations is not just a theoretical question. It is a real problem that we can observe and analyze in the context of our contemporary era. Observing current global challenges, such as climate change, social conflicts, and economic crises, we can ask, what stage in the cycle of civilizations are we currently experiencing? What are the consequences of these changes for future generations? Society is always at a crossroads, and in each new challenge lie both opportunities and threats. In this context, it is important to remember that difficulties and changes are an integral part of human history, and each generation must face the challenges of its time. In the theory of Fermi, there is a concept known as the Great Filter, which posits a hypothetical barrier that hinders the development and long-term survival of technological civilizations in the universe. Initially formulated in the mid-20th century, this idea raises the question: if there are numerous stars and potentially habitable planets in the universe, why have we not yet discovered extraterrestrial civilizations? The Great Filter can exist at various stages of life's development, from its initial emergence on a planet to its long-term survival in a highly advanced form. For instance, the first stage of the filter pertains to the very existence of life. On Earth, life emerged around 3.5 billion years ago, but this process is likely to be a rare occurrence. The second stage involves the transition from single-celled organisms to complex multicellular forms, which occurred around 600 million years ago during the Cambrian explosion. However, even if life reaches a level of technological advancement, the filter can manifest as catastrophic events such as global wars, pandemics, or climate change, which could destroy a civilization before it has a chance to spread to other planets. For example, World War II, which resulted in the deaths of more than 50 million people, could have served as such a filter for humanity if we had not been able to recover from the widespread destruction. There are differing opinions on where we currently stand. Some researchers, such as astrophysicist Martin Rees, believe that we are on the path to overcoming the Great Filter if we can avoid self-destruction and address global challenges. Others, including biologist Richard Dawkins, suggest that the filter may have already operated, and we simply do not know its consequences. It is important to note that every civilization that has ever existed could have faced such barriers, and their survival depends on their ability to adapt and overcome crises. If we consider the cosmos as a vast ocean of possibilities, the Great Filter becomes a sort of underwater reef, against which ships trying to reach the stars may founder. Thus, the question of where this filter is located and whether humanity can overcome it remains open. To date, there is no definitive evidence of the existence of extraterrestrial civilizations, which only adds to the intrigue surrounding this concept. Some scientists propose that until we reach a certain level of technological advancement, we will not be able to detect other civilizations. In this context, it is important to note that the Great Filter could be both a past and a future challenge for humanity. Scientific fiction scenarios, such as the destruction of a planet by artificial intelligence or technology running amok, serve as warnings about the potential risks we may face. The unpredictability of the future and the possibility that we may be one of the last remaining species lead to reflections on our role in the universe. The Great Filter, as a concept, makes us ponder how to change our path to avoid the fate of civilizations that may have already disappeared. Therefore, the study of this topic remains important for understanding our place in the cosmos and the steps we need to take to ensure the future of humanity. We must remember that each new challenge we face is not only a threat, but also an opportunity for growth and development. Scientific research aimed at studying exoplanets and searching for extraterrestrial signals continues, and it may lead to new discoveries that will help us better understand humanity's place in this vast and mysterious cosmos. Self-destruction of technological civilizations that have reached a certain level of development is one of the most alarming hypotheses regarding the fate of intelligent beings that might exist in our cosmos. An example is the civilization of the Maya, which, according to archaeological estimates, reached its peak in the first millennium of our era in Central America. They built magnificent cities and complex water supply systems, but ultimately faced the consequences of overusing natural resources. There are numerous studies, such as Jared Diamond's work in his book Collapse, which examines how ecological problems and internal conflicts led to the fall of civilizations like the Maya and the Incas. Diamond argues that excessive deforestation and soil depletion became catastrophic factors contributing to their downfall. Looking at more contemporary examples, we can mention the nuclear threat that humanity has faced since the middle of the 20th century. The Cold War, which ended in 1991, was marked by the buildup of nuclear arsenals, creating a world teetering on the brink of self-destruction. Empirical data shows that from the 19th century to the end of the 20th century, humanity produced more than 7,000 nuclear warheads, and although many were eliminated, the threat remains. Researchers like Stephen Hawking warned about possible scenarios in which highly developed civilizations could self-destruct due to technology they cannot control. For instance, artificial intelligence created by humans could ultimately escape control, leading to catastrophic consequences. In this line of reasoning, it is also worth mentioning the Fermi paradox, which asks, if there are billions of stars similar to ours and they could contain billions of planets with conditions suitable for life, why do we not observe any signs of intelligent life? One possible explanation is that technological civilizations, reaching a certain level, disappear without leaving traces. For example, a study conducted in 2009 by a team of astronomers found that stars in our galaxy are born and die, while life on planets can exist only for a relatively short time in geological terms. This creates an abrupt effect in the development of civilizations that may not be able to overcome their internal contradictions or ecological crises. It is also important to remember that even modern humanity faces threats such as climate change, caused by carbon dioxide emissions exceeding 36 billion tons per year. If no serious measures are taken, this could lead to catastrophic consequences for human civilization. In this context, self-destruction becomes not just a hypothesis, but a real frightening possibility. Statistics show that over the past 50 years, the average annual temperature increase on the planet has risen by 1 whole degree Celsius, which is already leading to climate change and disasters such as floods and droughts. Therefore, the question of the self-destruction of technological civilizations becomes increasingly relevant, while our efforts to prevent such scenarios require not only technology, but also a deep understanding of our place in the Earth's ecosystem. Studying the concept of sustainable development is becoming an important step in the evolution of intelligent species. Sustainable development implies harmonious coexistence between human society and Earth's ecosystems, allowing civilization to exist for millions of years without significant destruction. One of the first to formalize this concept was the Brundtland Report, presented in 1987, which defined sustainable development as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. In practice, this means finding a balance between economic growth, social justice, and environmental protection. There are examples of successful implementation of this concept, such as Sweden, where in the 2000s a strategy for transitioning to a sustainable society was developed. As a result, by the 2020s, Sweden had reduced greenhouse gas emissions by 26% compared to the 1990s, while economic growth not only did not stop but continued to develop. Another example is Costa Rica, where in 1991 a program for reforestation was adopted. At that time, more than 50% of the country's territory was covered with forests, which significantly improved the ecological situation and created a sustainable economy based on ecotourism. An important aspect of sustainable development is the use of renewable energy sources. For example, in Denmark in 2020, 38% of the total energy consumed was obtained from wind power plants, making the country one of the leaders in the field of green energy. The implementation of closed-loop technologies, where waste from one production becomes a resource for another, also plays a key role in sustainable development. In Germany, for example, a system for waste disposal was developed, where more than 70% of waste is recycled, significantly reducing the load on landfills and the environment. Efficient use of resources and minimization of waste require a new way of thinking from society, which begins with education and environmental awareness. Programs to raise awareness about nature and ecology are being implemented in schools around the world, starting from an early age. According to UNESCO, by 2020, around 75% of countries had integrated elements of sustainable development into their educational programs. This forms a new generation ready to face environmental challenges and make responsible decisions. Thus, sustainable development is not a utopia, but a real path of evolution for intelligent species, which requires a comprehensive approach and active participation of all segments of society. It is important to remember that sustainable development implies not only the preservation of natural resources, but also social equality, which in turn contributes to the stability and prosperity of civilization in the long term. For example, in New Zealand, the government has implemented a law that all major projects must take into account their impact on local ecosystems and the rights of indigenous peoples, serving as an example of the integration of social and ecological aspects into economic development. As a result of such initiatives, countries can avoid catastrophic consequences associated with climate change and create sustainable communities that can adapt to changing conditions. In 2000, the World Wildlife Fund declared that around 1 billion people on the planet live in conditions where access to clean water and food is critically important. Effective management of resources and their rational use will help overcome these challenges. Space archaeology is a relatively new field of research focused on studying the remnants of human activity on other planets and celestial bodies. It builds upon the principles of traditional archaeology but applies them to the study of objects beyond Earth. The primary goal of space archaeology is to understand how humanity interacted with its environment in the cosmos, and to determine what cultural and technological achievements were made in conditions of weightlessness and extreme temperatures. For instance, on the Moon, traces of human activity such as landing modules left over from the Apollo program in the 1960s and 1970s have been discovered. 6 successful lunar missions were conducted, resulting in the collection of approximately 400 kilograms of lunar soil, which has been crucial for studying not only the geology of the Moon, but also the conditions under which human activity developed. Beyond the Moon, on Mars, the ruins of potential Martian structures have been found, raising questions about the possibility of life on this planet. In particular, the Curiosity mission, launched in 2012, provided data indicating the presence of water in the past, which could suggest past biological activity. Space archaeology also involves the study of artifacts left in orbit around Earth, such as satellites and space stations, which represent not only technological achievements, but also symbols of humanity's desire to explore the cosmos. For example, the International Space Station, launched in the 2000s, is the result of international cooperation among more than 30 countries, and serves as a laboratory for studying the effects of space conditions on the human body and technology. Research in this area requires a multidisciplinary approach, combining astronomy, history, archaeology, and even philosophy, as it addresses important questions about humanity's place in the universe and what it means to be human in the context of space. An important aspect of space archaeology is also ethics, related to the preservation of cultural heritage in space. The scientific community is discussing how to protect these artifacts from contamination and destruction, especially in light of future missions that could lead to increased human activity on other planets. In this context, space archaeology becomes not only a research area, but also an important part of the discussion about the future of humanity in space. Discoveries in this field can change our understanding of how we interact with other planets and how we should treat our heritage in space, which could be valuable not only for us, but also for future generations. In 2020, the European Space Agency published a report proposing the creation of international norms for the protection of space cultural heritage, which underscores the growing importance of this topic. Searching for artificial structures on the Moon is one of the most captivating aspects of modern space research. Scientists believe that due to the absence of atmosphere, erosion, and tectonic activity on the lunar surface, traces of ancient civilizations could have been preserved, which would have been eroded on Earth. The Moon, with its unique geological state, has preserved traces of its history for billions of years. For example, craters formed by meteorite impacts remain practically unchanged, making them ideal for study. In 1969, astronauts of the Apollo 11 mission discovered that the lunar surface consists of regolith, a layer of dust and debris that may contain microscopic remnants of ancient materials. The Apollo 15 mission in 1971 led to the discovery of fossils, which, although not artificial structures, indicate that the Moon had a more active geological past than previously thought. Since the year 2000, various research groups, such as the Lunar Reconnaissance Orbiter Project, have been actively searching for potential artificial objects on the Moon. These searches focus on using high-speed cameras and radars to obtain detailed images of the lunar surface. In 2008, the Indian Space Research Organization launched the Chandrayaan-1 mission, which helped identify many interesting formations that could represent remnants of artificial structures. Among the most discussed findings are the so-called lunar pyramids in the Lacus Mortis crater, which are geometrically regular shapes. These formations spark debate among scientists. Some consider them natural geological formations, while others argue for their artificial origin. In 2009, researchers from the University of California, Berkeley, reported the possibility of detecting powerful signals from certain lunar zones, which could indicate the presence of complex structures. It is also worth noting that in 2005, a group of NASA scientists initiated the Lunar Maps project, aimed at creating three-dimensional models of the lunar surface to identify anomalies. These maps help researchers focus on areas that require deeper study. Additionally, lunar observations have become more accessible in the 21st century due to the development of telescopes and other technologies. For instance, in 2021, astronomers using radio telescopes discovered anomalies in the lunar polar region that could also indicate the presence of artificial objects. The discussion of lunar artificial structures has led to the emergence of new theories about possible civilizations that may have once existed on the Moon. In 1982, American astronomer Brian O'Leary suggested that some lunar craters could have been used as observation points by ancient civilizations to monitor Earth. Studies using data from lunar orbital probes also show that some lunar regions may contain frozen water reserves, opening new possibilities for the establishment of colonies and the study of potential life. In the 21st century, with the advancement of technologies and increased funding for space research, questions about ancient civilizations on the Moon have become increasingly relevant and have sparked interest among both the scientific community and the general public. In the end, the absence of atmospheric conditions on the Moon, combined with its stable geological structure, makes it an ideal place for searching for traces of ancient civilizations that could change our understanding of human history. Scientific research continues, and each new mission could lead to unexpected discoveries that will make us re-evaluate the role of the Moon in our past. In the 1970s, more than 13,000 craters were registered, highlighting the diversity of the lunar landscape and the importance of further research. Research on Mars in search of signs of life and potential artifacts has become one of the most ambitious tasks for scientists and engineers in recent decades. In the late 1970s, the Viking lander became the first spacecraft to analyze the soil and atmosphere of the Red Planet. It found that the surface temperature ranged from -120 to +20 degrees Celsius, and the atmosphere was primarily composed of carbon dioxide with minor concentrations of nitrogen and argon. These data confirmed that Mars could have been more hospitable in the past. In the 1990s, the Mars Pathfinder mission delivered the Sojourner rover to the planet, which analyzed rocks and soil, confirming the presence of water ice in the polar caps and on the surface in the form of crusts, which is a significant indicator of possible life. The Spirit and Opportunity missions, launched in 2003, explored the Gusev crater and the Meridiani plain, respectively, discovering minerals such as hematite and sulfates, which form in water environments. These findings led scientists to hypothesize that Mars may have had liquid water on its surface in the past. In 2011, the Curiosity rover began its work in the Gale crater, where organic material was found in rock samples, suggesting that conditions for life may have existed on Mars. Additionally, in 2016, the Opportunity rover confirmed the presence of methane in the atmosphere, which could indicate biological activity, although its source remains unclear. In 2020, the Perseverance rover was launched with the goal of searching for ancient microbial life and collecting samples for return to Earth. It is exploring the Jezero crater, which was once a delta of a river and may have preserved signs of life billions of years ago. Scientists believe that if life did exist on Mars, its traces could be found in sedimentary rocks that formed in a water environment. An important aspect of these studies is the presence of artifacts that could indicate the existence of intelligent beings or their activities. Geological formations found on the planet's surface, such as volcanic and river structures, have sparked debate about whether these structures could have been created artificially. In the 20th century, scientists like Carl Sagan proposed theories about the possibility of life on other planets, and Mars, with its rich history, has become a key player in the search for answers to this question. Scientific developments continue, and each new mission can bring unexpected facts that change our understanding of the Red Planet. Currently, scientists are analyzing data from the rovers and developing new technologies for deep exploration of the planet, which allows for hope of further discoveries. Astronomers are actively studying altered asteroids and other small bodies in the solar system in search of possible traces of technologically advanced life. In particular, scientists are focusing on asteroids that could be of interest for resource extraction. One of the most well-known such objects is the asteroid Bennu, which was studied by the OSIRIS-REx spacecraft launched by NASA in 2017. In 2019, the spacecraft successfully collected samples of Bennu's surface, which contain carbon compounds and minerals that could be potential sources of water and organic substances. The analysis of these samples, scheduled for 2023, may provide insights into how asteroids could be used to support life on other planets. Additionally, astronomers are studying the asteroid Ceres, which is believed to contain reserves of ice and salts, making it a potential candidate for future colonization or resource extraction. In 2006, the Dawn spacecraft conducted an orbital study of Ceres and discovered bright spots on its surface that may be salt crystals. These findings support the theory that Ceres may have subsurface water reserves. Studies have shown that the presence of water on small bodies in the solar system may be more widespread than previously thought. In 2020, a group of astronomers led by Dr. David Levin from the University of Texas analyzed data on other asteroids and found that more than 50 of them exhibit signs that may indicate the presence of water or organic substances. This discovery underscores the importance of further research on small bodies as potential sources of resources for future space missions. It is also worth noting that some asteroids, such as the asteroid Icarus, have orbits that intersect with Earth's orbit. This makes them potentially dangerous, but also interesting for research from the perspective of their resource potential. Scientists suggest that such objects may contain metals such as gold and platinum, which attract the attention of both researchers and private companies interested in space mining. In 2020, the company Planetary Resources announced plans to develop technologies for mining resources on asteroids, and in 2021, it presented a mission project to study the asteroid Bennu. However, mining resources on asteroids faces numerous technical and ethical challenges, such as the need to develop technologies for safe mining and processing materials in space. These questions are becoming increasingly relevant given the growing needs of humanity for resources and the possibility of colonizing other planets. Astronomers continue to study small bodies in the solar system using new technologies such as radio telescopes and space probes, which can detect changes in their orbits and physical properties. For example, in 2020, astronomers from the University of California discovered that asteroid Palomar 31, which intersects with Earth's orbit, has changed its orbit, which may indicate the influence of gravity from other bodies or the presence of active processes on its surface. These data may help in understanding how asteroids could be altered by technologically advanced beings. Astronomers also study comets, which are believed to contain reserves of water and organic substances. The comet Churyumov-Gerasimenko, studied by the Rosetta mission in 2015, demonstrated the presence of complex molecules, including amino acids, which suggests that comets could have been sources of life on Earth in the distant past. Research on small bodies in the solar system continues, and each new discovery brings us closer to understanding how future technologies could change our understanding of the cosmos and the possibilities it offers. Ultimately, some of these objects may become not only sources of resources, but also keys to solving the mysteries of the origin of life in the universe. Planetary engineering is a concept that involves altering and adapting the surrounding environment at a planetary level to create conditions suitable for life. This idea is not new. Its first mentions can be found in early 20th century science fiction, where authors like Herbert Wells and Arthur C. Clarke began to dream of the possibility of colonizing other planets. However, with the development of sciences such as astronomy, geology, and ecology, planetary engineering has become a subject of serious scientific research. In the 20th century, scientists like Carl Sagan began to discuss the possibility of terraforming Mars. That is, creating conditions on this planet that would allow Earth-like life to exist. For instance, in the 1970s, Sagan proposed the idea of using greenhouses to increase the temperature on Mars, melting its polar ice caps and releasing frozen water. While many ideas remained at the theoretical level, modern science has made significant progress in understanding climatic systems and ecosystems, opening new horizons for the practical implementation of such projects. Research shows that altering a planet's atmosphere, for example, by introducing greenhouse gases, can create a greenhouse effect similar to that observed on Earth. However, this also raises serious ethical questions. What are the consequences of interfering with the ecosystem of another planet? In 2008, a study conducted by NASA showed that climate change on Earth is a result of human activity, and therefore, planetary engineering may become a necessary step in saving our planet. Concurrently, the concept of planetary engineering includes ideas about creating artificial ecosystems that can function in conditions unsuitable for life. For example, in 2009, a group of scientists proposed the creation of autonomous biomes that could exist on the Moon or Mars, opening the way to colonization. These studies highlight the complexity and diversity of approaches to planetary engineering. Additionally, economic and social aspects must be considered. Who will control these technologies, and how will they affect international relations? Issues related to resource rights and management become increasingly relevant as humanity advances towards the exploration of other planets. Thus, planetary engineering raises not only technical, but also philosophical questions about the future of humanity and its place in the universe. It is important to note that to date, none of the proposed terraforming projects have been implemented, and all remain at the level of hypotheses. However, with each new discovery related to exoplanets and their atmospheric conditions, we are getting closer to understanding what changes may be possible on other planets. Currently, astronomers have discovered more than 3,000 exoplanets, some of which are located in what is known as the habitable zone, where conditions may be suitable for life. Terraforming is a complex process of deliberate climate and ecosystem alteration on a planet to create conditions suitable for human and other biological life. This process involves multiple stages, from altering the atmosphere to forming ecosystems. For instance, on Mars, where conditions do not allow water to exist in liquid form, terraforming could involve heating the planet using large mirrors to reflect sunlight or producing greenhouse gases like carbon dioxide to raise the temperature. In this context, creating an atmosphere suitable for life would require immense efforts and technologies that currently exist only in theory. On Earth, examples of terraforming can be seen in human activities that have altered landscapes over thousands of years. For example, irrigation of deserts or the construction of dams to change river courses leave long-lasting geological traces such as altered soils and new ecosystems that can persist for centuries. In the case of terraforming other planets, such changes could be more pronounced. For instance, if oceans were created on Mars, this would undoubtedly alter the planet's geological structure, leading to the formation of new minerals and changes in topography. Scientific research shows that even small changes in the atmosphere can trigger chain reactions affecting the climate and ecosystems. The Mars One project, proposed in 2013, aimed to colonize Mars using terraforming, but its implementation demonstrated how challenging this process is. In the event of successful terraforming, the planet could develop geological formations such as sedimentary deposits, characteristic of aquatic ecosystems. These processes require time, and the results could remain visible even after millions of years. For example, if successful vegetation were created on Mars, soils capable of retaining water and carbon could form, altering atmospheric conditions. Sustainable ecosystems created through terraforming could serve as the basis for a new biosphere, and their geological traces could be discovered by future researchers. Experiments on Earth, such as the restoration of ecosystems in highly degraded areas, show that nature can recover, but this process would be significantly more complex and time-consuming on other planets. Ultimately, terraforming would not only alter the climate and ecosystem of a planet, but also leave noticeable geological traces that could tell the story of the planet's past and future. For example, in the case of successful creation of new ecosystems on Mars, their traces could be seen in the form of specific minerals formed as a result of interaction with the new atmosphere. Megastructures that could have been created by highly advanced civilizations are astonishing examples of engineering ingenuity, and their traces might remain even after the disappearance of their creators. One of the most discussed projects is the concept of space elevators, first proposed by scientist Arthur C. Clarke in the 1970s. These elevators would be long cables extending from the surface of a planet to a geostationary orbit, making them an ideal means of transporting cargo into space. Calculations suggest that the cable should be around 36,000 kilometers long, and its resistance to tension would require the use of new materials such as carbon nanotubes, which possess extraordinary strength and lightness. If such a structure were built, it could leave distinctive geometric traces on the planet's surface and in the orbital zone. Another striking example is the concept of orbital rings, which could be created for planets like Earth or Mars, consisting of massive structures made of satellites connected to each other. These rings could serve both as protection from meteoroids and as a means of creating artificial living conditions. Research conducted by a group of scientists led by Professor John G. Costello in 2015 showed that such rings could theoretically protect a planet's atmosphere from escaping into space, acting as a shield. Traces of such constructions could be found in the form of changes in orbital trajectories, as well as specific minerals and elements formed as a result of interaction with space. Artificial satellites used for communication and observation of Earth could also leave traces in the future. For instance, satellites launched as part of the GPS program provide precise positioning and navigation. If this technology were to disappear, thousands of non-functional satellites would remain in orbit, serving as reminders of the high achievements of civilization. Analysis of data collected in 2020 showed that more than 2,000 satellites are no longer functional, but their remnants still orbit the Earth, posing a risk of collision with new launches. As an alternative, highly advanced civilizations could create gigantic solar parks in space, converting solar energy into electricity and transmitting it to planets. These structures, consisting of thousands of solar panels, could leave traces in the form of changes in the planet's radiation background and atmospheric temperatures. If such a civilization were to disappear, their installations could become ruins that could be studied by future civilizations. One of the most daring proposals is the creation of a megastructure known as the Dyson Sphere, proposed by physicist Freeman Dyson in 1950. This structure would be a shell surrounding a star to harness its energy. If such a construction were ever built, its remains could be visible from afar and could cause changes in the star's luminosity. Scientists suggest that traces of such megastructures could be detected even in other star systems, opening new horizons for astronomical research. These ideas about megastructures are becoming increasingly relevant as humanity strives to explore space, and their creation could become a reality in the future. Fractal architecture is a concept of design based on the principles of fractal geometry, which was deeply studied by mathematician Benoit Mandelbrot in the late 20th century. Fractals, as is known, are characterized by self-similarity, meaning their structures repeat at different scales. An example of this is the famous Mandelbrot set, where each detail repeats upon magnification, creating amazing and complex forms. In architecture, this concept can lead to the creation of buildings that organically blend into their surroundings, mimicking natural forms such as mollusk shells or clouds. Such constructions can not only appear natural, but also utilize the advantages of natural processes, such as improved ventilation and lighting, making them more efficient and sustainable. Biomimetic constructions, in turn, borrow ideas from nature to solve engineering problems. Architects like Bjarke Ingels and his firm BIG actively use biomimicry, creating buildings that not only visually resemble natural forms, but also use similar mechanisms to ensure sustainability and harmony with ecosystems. For example, in the Old Port project in Copenhagen, principles borrowed from natural ecosystems were used, which allowed for reduced energy consumption and improved the quality of life for residents. Such buildings can gradually lose their artificial characteristics, becoming part of the landscape, making it difficult to identify them as man-made objects. This trend is already reflected in architectural projects such as the Greenhouse in Hamburg, where the facades of buildings are covered with vegetation, and the forms of their structures resemble natural elements such as hills and rocks. Research shows that such approaches can significantly reduce the carbon footprint of buildings and improve the overall state of the environment. The introduction of such constructions into mass construction can become a turning point in architecture, where buildings will not only be functional but also aesthetically integrated into nature. In such conditions, fractal architecture and biomimetic constructions can become an integral part of the future of humanity, ensuring harmonious coexistence with nature. For example, in Japan, the concept of living buildings was developed, which can adapt to changes in climate thanks to the use of fractal models and biomimicry. Technologies such as 3D printing allow for the creation of complex structures that were previously impossible, opening new horizons for architects and engineers. These innovative design methods can lead to the creation of objects that not only serve humans, but also support the ecosystems they are located in. As a result, such buildings can not only blend into the natural landscape, but also interact with it, ensuring a sustainable living environment for people and animals. Cultural blindness is a phenomenon where an individual fails to recognize or notice cultural differences and peculiarities inherent in other groups. This can occur due to various reasons, including limited experience, narrow perception frameworks, and biases formed based on personal beliefs or upbringing. Cultural blindness affects not only the perception of other cultures, but can also impact interactions within the same culture, leading to misunderstandings and conflicts. For instance, in a globalized world where people frequently encounter multiple cultures, the lack of awareness of these differences can result in communication errors, missed opportunities for collaboration, and even international conflicts. Studies show that cultural blindness can hinder business decision-making when companies do not consider local traditions and preferences, leading to their products or services becoming unpopular. A striking example is when brands fail to adapt their advertising campaigns to local cultural contexts, resulting in negative consumer reactions. Cultural blindness can be caused by cognitive distortions such as stereotypes and biases that are formed based on personal experience or media influence. Identifying and understanding these distortions is a crucial step in overcoming cultural blindness. It is important to note that culture is not static. It is constantly changing and evolving. People within the same cultural context can perceive the same events differently, further complicating interactions between them. Cultural blindness can manifest even in simple everyday situations. For example, during communication, people may not notice nonverbal signals that play a crucial role in different cultures. Research shows that nonverbal communications account for up to 93% of all communication. This means that if a person does not pay attention to these signals, they may misinterpret the intentions of their interlocutor. Cultural blindness can be overcome through education and openness to new experiences. Studies show that programs in intercultural education help participants develop skills necessary for effective communication and understanding of various cultural perspectives. For instance, in 2002, a study involving over 2,000 students from different countries found that intercultural communication training significantly improved the level of understanding among participants. Cultural blindness can also hinder the perception of historical events when certain groups ignore or underestimate the contributions of other cultures to world history. This can lead to distortions in historical memory and perception, which in turn influence the formation of identity and public consciousness. Understanding cultural blindness requires recognizing that each person sees the world through the prism of their own experiences and beliefs, necessitating an active effort to broaden one's horizons and increase cultural competence. Examples of contemporary educational initiatives aimed at overcoming cultural blindness include exchange programs, cultural festivals, and projects fostering dialogue between cultures. Such events allow people not only to familiarize themselves with new cultures, but also to challenge stereotypes that may exist in their minds. Cultural blindness is not just an individual problem, but also a societal one, affecting social structures and relationships within society. For example, in countries with a multi-ethnic population, cultural blindness can lead to social conflicts and discrimination, underscoring the importance of intercultural dialogue and cooperation. Scientific research shows that in societies where cultural differences and diversity are actively promoted, the level of mutual understanding and cooperation between different groups is significantly higher. In 2005, a study by the Gallup Institute found that companies with diverse workforces have higher levels of innovation and creativity. This indicates that diversity can be not only a valuable resource, but also a necessary condition for the effective functioning of society. Cognitive distortions and biases play a significant role in how scientists perceive and analyze hypotheses related to the existence of prehistoric technological civilizations. One of the most common distortions is confirmation bias, where researchers tend to seek and interpret data in a way that aligns with their existing beliefs. For instance, many archaeologists reject hypotheses about advanced technologies in civilizations that predated writing, relying on traditional notions of progress that suggest complex technologies could only have developed under specific social and economic structures. This mindset was particularly pronounced in the 19th century, when archaeologists like Henry Morgan asserted that societal structures evolved linearly from primitive to highly developed, ignoring the possibility of complex societies in prehistoric times. Another important bias is the expert effect, where the opinion of an authoritative scientist is accepted as absolute truth, even if their views are outdated or based on insufficient data. For example, works by scientists such as Arthur C. Clarke proposed intriguing ideas about possible technologies of ancient civilizations, but they were often dismissed by the mainstream scientific community as speculative, leading to the dismissal of potential alternative explanations. Negative perceptions of ideas about prehistoric technogenic civilizations are also linked to cultural and social biases, where more advanced cultures are viewed as superior and less advanced ones as primitive. Such biases often manifest in scientific debates. For example, when the achievements of Maya or Sumerian civilizations are seen as unique, rather than possible results of a broader technological evolution. As a result, potentially interesting research, such as the work of Professor Greg Benfield, who in 2010 presented a hypothesis about advanced technologies in civilizations that existed thousands of years ago, often goes unnoticed. This leads to situations where even compelling evidence, such as artifacts found in Peru in 2003 that demonstrate complex metalworking technologies, is interpreted as random anomalies or errors, deterring researchers from exploring new horizons. The phenomenon of groupthink also hinders the progressive acceptance of unusual hypotheses, where collective views of the scientific community can suppress individual ideas that deviate from established norms. In such conditions, even if individual scientists begin to question traditional paradigms, they may face pressure from colleagues to keep their thoughts private, fearing loss of reputation or funding. Thus, cognitive distortions and biases in the scientific community serve as a barrier to the acceptance of non-standard hypotheses, limiting the possibilities for the discovery and exploration of new ideas about ancient civilizations and their achievements. For instance, in 2001, a group of scientists working on the Ancient Technologies Project discovered tools in Mesopotamia that clearly indicated the presence of complex metallic technologies. But most of their findings were ignored because they did not fit existing theories on the development of technologies. Anthropocentric bias pervades all aspects of our understanding of reason and intelligence. This bias implies that the human path of cognitive evolution is the only possible one, ignoring alternative forms of intelligence that could exist in other species or even in artificial systems. For instance, in 2001, a study conducted by a group of zoologists led by Dr. Emily Taylor showed that certain species of dolphins use complex acoustic signals to communicate and coordinate their actions within a group, challenging our notions that only humans are capable of complex interaction. In 2003, experiments in Japan with sparrows demonstrated their ability to solve tasks requiring the use of tools, also indicating the presence of intelligence outside the human race. Scientific research, such as the work of Professor Stephen Hawking, emphasizes that human intelligence is just one of many possible variations, while artificial intelligence, which can develop with entirely different algorithms and logic, is already showing capabilities similar to those of humans. For example, in 2018, researchers at the Massachusetts Institute of Technology developed an algorithm that defeated the world champion in the game of Go, demonstrating that intelligence can take forms not necessarily tied to biological evolution. This raises the question of how well we truly understand the nature of reason and intelligence if we continue to insist that only the human path of evolution is correct and unique. Comparing various forms of intelligence, we can recall the existence of species like octopuses, which, despite lacking a backbone, exhibit remarkable abilities in learning and adaptation. In 2015, a group of researchers from the University of California, San Diego, discovered that octopuses can remember and apply complex strategies, challenging traditional notions that reason and technology are only present in highly developed mammals. It is important to note that anthropocentric bias is also reflected in historical interpretations, where the achievements of other civilizations are often underestimated or ignored altogether. For example, in the 2000s, the achievements of ancient Sumerians, who developed a writing system and the foundations of mathematical calculations, were often overshadowed by European human successes. This leads to the exclusion of alternative forms of intelligence and technology from our field of view, and we miss the opportunity to understand how different species could develop their unique forms of intelligence. In 2020, a group of scientists from Osaka University conducted a study that showed that ants can organize complex structures, such as anthills, also challenging our understanding of intelligence as an exclusively human phenomenon. This bias can limit our perception and understanding of a world where reason and technology can take many different forms that we have not yet fully explored and evaluated. In the end, if we continue to ignore alternative paths of cognitive evolution, we risk remaining trapped within the narrow confines of our own perception of the world. For example, in 2020, as part of a project to study exoplanets, astronomers discovered a planet where forms of life that are fundamentally different from those on Earth may exist, And this discovery once again raises the question of how we define reason and intelligence on other planets. Technologies that could radically differ from our own present a serious challenge for archaeologists and historians. For instance, in 2015, a team of scientists led by Dr. José Ramírez from the Mexican Institute of Archaeology discovered tools made from an unknown alloy. These artifacts were found in a region historically inhabited by a civilization that used stone tools. However, the tools discovered in the excavations were made from an unknown metal, which preliminary data suggests could be the creation of one of now lost technologies. This discovery challenges our understanding of the materials and methods ancient people might have used. We might overlook traces of civilizations that utilized fundamentally different energy sources. For example, in 2001 in China, artifacts were found that, according to scientists, could be part of a system using geothermal energy. These artifacts included pipelines and reservoirs that could have been used for distributing hot water. However, since we are accustomed to using coal and oil, such findings often go unnoticed. The lack of parallels with modern technologies hinders us from recognizing their purpose. In 2020, when a group of archaeologists from the University of California explored underwater ruins of an ancient city, they discovered structures that could have been used to generate electricity from ocean currents. These structures, built over 2,000 years ago, could fundamentally change our understanding of the technological level of that time if we could interpret them correctly. Ancient civilizations might have used principles that we are currently unable to comprehend. What we consider primitive tools might simply reflect our limited perspective. For us, it is customary to see technologies based on metals and hydrocarbons. But what if ancient people used organic materials that decomposed over time? This could explain why we do not find traces of their existence. In 2006 in Peru, a series of underground chambers were discovered that, according to archaeologists, could have been part of a system for storing energy using solar and lunar cycles to generate heat. However, without a clear understanding of how such systems work, we might overlook their significance. Technologies that existed in the past could be so different from ours that we are unable to recognize them. This challenges the concept of progress. Perhaps we are not only not moving forward, but also losing the knowledge that our ancestors once possessed. Each new artifact could be a key to unraveling mysteries that we are still unable to comprehend. For example, in Mesopotamia thousands of years ago, there existed irrigation systems that used fundamentally different methods of managing water resources than those used today. The ways ancient people utilized natural resources may be beyond our understanding simply because we do not know what to look for. In this context, it is important to remember that many civilizations could have existed independently and parallel to each other, using unique technologies that are unknown to us. Research results show that on some islands in the Pacific, local inhabitants used technologies that allowed them to survive in conditions where other civilizations could not adapt. Their methods, including the use of local plants and alternative food sources, have not yet been documented in scientific literature. We might overlook entire cultures if we continue to view them through the lens of our modern technologies and concepts. Discovered artifacts may indicate that we are losing touch with how different peoples interacted with their environment and utilized its resources. Each new fact we uncover could not only change our understanding of history, but also challenge the very nature of our technologies and their evolution. In 2003 in Greece, remnants of mechanisms were found that could have used water flows to create motion, but their true purpose remains a mystery. Without a proper understanding of their construction and purpose, we risk leaving these achievements in the shadows, unaware of the valuable information they could contain. In the history of humanity, there exists the concept of parallel technological paths, which emphasizes that different cultures in different historical epochs can develop their technologies independently of one another, yet arrive at similar solutions. This phenomenon is observed, for example, in the ancient world, where different civilizations such as ancient Egypt, Mesopotamia, and India independently created irrigation systems to address agricultural challenges. The second half of the 20th century demonstrated that even in conditions of globalization and mutual understanding, there were cultural and technological isolations that allowed separate regions to develop unique solutions. For instance, in the 1990s in Japan, a production management system was developed that had no Western counterparts and was based on quality traditions dating back to the samurai era. At the same time in Germany, unique approaches were created, such as the production system concept based on lean manufacturing, which ultimately led to the creation of modern car factories. Such examples highlight that cultural roots and historical context can influence the choice of technologies and methods used to solve the same problems. It is also worth noting that in the late 18th century, in different parts of the world, such as China and Western Europe, significant changes related to the Industrial Revolution were occurring simultaneously, although each region did so in its own way, adapting technologies to its needs and conditions. Parallel paths can be not only a source of unique solutions, but also an illustration of how something similar can emerge from different cultural contexts. For example, in the year 2001, in Africa and South America, the development of alternative energy sources began simultaneously, although neither of these initiatives was connected to the other. They were based on local resources and needs, which underscores how, even in the face of global challenges such as climate change, culture and local conditions remain determining factors in the choice of technological solutions. In 2003, in India and Norway, parallel projects on the use of solar energy in agriculture began, which demonstrates that such solutions can arise independently while adapting to local conditions. This phenomenon confirms that the history of technologies is not linear, but represents a complex network of interconnections and parallel processes that can emerge in different corners of the world, sometimes without knowing about each other's existence. It is important to remember that these parallel paths do not always lead to the same results, but they can enrich our understanding of technologies and their evolution, showing how different cultures address the same challenges. For example, in 2006 in Brazil and South Korea, programs for the introduction of electric vehicles were launched, and although both countries aim to reduce dependence on fossil fuels, the approaches to implementing these projects and the choice of technologies were completely different, reflecting local needs and economic conditions. Thus, parallel technological paths serve as a reminder that the diversity of cultures and histories can lead to a multitude of unique solutions to the same problems. In this context, the example of the year 2000 is particularly interesting, when in China and India, work on the integration of information technologies in agriculture began simultaneously, demonstrating how modern challenges can give rise to similar responses in different parts of the world. Changes in ecological conditions and human society's needs in the past could have led to the development of biotechnologies instead of mechanical technologies. In this alternative scenario, which could have emerged, for example, at the beginning of the 20th century, scientists like the renowned geneticist Gregor Mendel would have discovered not only the laws of inheritance, but also methods for creating genetically modified organisms, allowing civilization to create living organisms with desirable human qualities instead of developing machines. Starting from the early 20th century, when active work in genetics began, for instance, in the 1930s, scientists would have started researching the possibilities of using cross-pollination and other selection methods to create plants that could grow in harsh conditions. This could have formed the basis for developing drought and disease-resistant crops, significantly increasing yields and reducing dependence on mechanization and fertilizers. The ability to manipulate genes would have opened new horizons in medicine. Scientists could have developed organisms that produce necessary medicines, changing the approach to treating diseases. Compared to traditional production methods, the biotechnological path would not have left typical archaeological traces such as factories or machines. Instead, we would have seen traces of modified organisms in ecosystems, for example, entire forests of trees bred for increased resistance to pests and diseases, or fields of plants that could fix more carbon from the atmosphere, helping to combat climate change. Successes in biotechnology, such as the creation of transgenic animals, could have led to the appearance of new food sources. For example, fish that grew faster and were resistant to diseases, reducing the need for artificial feed. In the 1970s, when such technologies began to actively develop, scientists like Patrick Moody could have created the first disease-resistant wheat varieties that produced yields even in conditions where traditional varieties did not survive. Successes in gene editing, such as CRISPR, could have been realized much earlier, significantly accelerating the process of creating organisms with desired characteristics. Thus, instead of developing complex machines, civilization could have focused on creating living systems that self-renewed and adapted to changes in the environment. This would have led to sustainable ecosystems where living organisms were not just resources, but part of the life cycle, capable of restoration and self-regulation. In such a reality, preserving biodiversity and ecosystem services would have become the main priority, significantly changing the approach to environmental protection. A comparison with the mechanical development path shows that the biotechnological approach would have been more economical and less harmful to the planet, but also more complex in terms of management. This path would have required a new understanding of how to interact with nature to use its capabilities without destroying it. Research conducted by scientists like Richard Lewin shows that with the right approach to using biotechnologies, it would have been possible to avoid many ecological crises that humanity has faced in the past. In this context, the development of cultures that could adapt to climate change and maintain their properties would have become the main direction of scientific and technological development. Quantum technologies represent one of the most promising areas of modern science, and it is possible to assume that in ancient times there existed civilizations that possessed knowledge of manipulating fundamental forces of nature using methods that did not leave behind material artifacts. For example, in the early 20th century, physicist Max Planck formulated the theory of quantum mechanics, which describes the behavior of particles at the subatomic level. This theory became the foundation for future research in the field of quantum physics, and opened the way to understanding phenomena such as entanglement, which allows information to be transmitted over distances without the involvement of material carriers. This leads to an interesting hypothesis. Perhaps ancient civilizations, such as the Sumerians or Egyptians, possessed knowledge of quantum interactions that allowed them to achieve effects that seemed magical compared to modern technologies. Research shows that Sumerian tablets contain references to rituals that could be related to the manipulation of energies, but did not leave physical evidence. For example, ancient Egyptians could use crystals not only as decorations, but also as tools for interacting with energy fields. Scientific experiments conducted in the 21st century demonstrated that crystals can influence electromagnetic fields, which in turn opens the door to understanding the possible use of such technologies in antiquity. In the 12th century BC in China, the concept of Qi emerged, which describes the vital energy permeating all living and non-living things. Methods of its manipulation may have included techniques that can now be compared to quantum technologies. The study of phenomena such as teleportation or quantum entanglement shows that the transmission of information or energy can occur without material carriers, indicating the possibility of the existence of ancient methods that operated at the level of quantum interactions. In the 20th century, scientists such as Niels Bohr and Albert Einstein conducted numerous experiments that confirmed that on the subatomic level, the laws of physics behave differently than on the macroscopic level. Einstein even described entanglement as spooky action at a distance, indicating his awareness of the mysterious nature of these phenomena. This may be analogous to how ancient peoples could perceive their connection to nature as something sacred and beyond human understanding. Modern research in the field of quantum technologies, such as the creation of quantum computers, opens new horizons for manipulating data and energy using principles that could potentially have been known to ancient civilizations. For example, quantum computers can solve problems that would be practically impossible for classical computers, reminiscent of the possibilities of ancient technologies that could control energies and interactions at levels beyond our current understanding. It is important to note that the absence of material artifacts does not mean the absence of knowledge or technologies. Modern developments in the field of quantum physics show that it is possible to manipulate reality at a level that in ancient times could have been perceived as magic. Research shows that many ancient cultures, such as the Indians and Chinese, left records of the use of energy in their rituals, which could possibly be interpreted as early attempts to understand quantum principles. These records, like modern achievements in the field of quantum mechanics, emphasize that knowledge of manipulating energy and matter has existed in various forms throughout human history. Perhaps ancient masters, using their knowledge of interactions, could achieve effects that modern science is only beginning to understand. It is interesting that modern research in the field of quantum biology shows that some organisms, such as birds, can use quantum mechanisms for navigation, opening new horizons for understanding how living beings interact with the world at a level inaccessible to direct observation. The study of non-material technologies based on information and consciousness opens up intriguing horizons for understanding the development of intelligent beings that may not have created physical structures capable of enduring in the geological record. For instance, in ancient Greece, philosophers like Plato and Aristotle discussed concepts of ideal forms and consciousness that could serve as the foundation for non-material technologies. Plato, in his work The Republic, described the world of ideas as more perfect than the material world, implying the possibility of non-material technologies linked to perception and knowledge. In this context, one can mention the concept of the noosphere, proposed by Vladimir Vernadsky in the early 20th century, which suggests that human consciousness and collective knowledge can influence planetary processes and evolution. This notion connects the development of non-material technologies with informational flows and changes in the environment without the need for creating physical objects. Additionally, research in the field of neurobiology shows that consciousness can be linked to quantum processes in the brain, opening up the possibility of creating technologies based on mental interactions, such as telepathy or collective consciousness. Studies conducted in recent decades indicate that the existence of mental connections between people can be based on empathy and information exchange, leading to a deeper understanding of social interactions. For example, in the 2000s, a group of scientists from the University of California discovered that the brain can synchronize with the brains of other people during communication, suggesting the presence of a collective mental structure that does not leave physical traces but still influences behavior and perception. The transfer of technologies into the realm of the non-material can also include the development of languages and sign systems that convey complex ideas and concepts without leaving material artifacts. For example, the languages of indigenous peoples, such as the Navajo language, contain unique ways of describing spatial and temporal relationships that can shape collective consciousness and cultural traditions passed down through generations. In addition, traditional practices such as meditation and shamanism can serve as examples of non-material technologies that affect consciousness and perception of the world. Research into such practices shows that they can lead to changes in the state of consciousness and perception of reality, which can be interpreted as the use of non-material technologies to achieve certain goals. In some cultures, these practices are transmitted orally and do not leave material traces, but still have a strong influence on social structures and individual behavior. Thus, non-material technologies can take various forms, including languages, cultural practices, and collective consciousness, all of which together form unique systems of interaction and understanding of the world without leaving physical objects behind. These technologies may have played a key role in the development of civilizations, allowing them to achieve high levels of integration and understanding without the need for creating durable structures. For example, the use of oral tradition in African tribes, where knowledge is passed down from generation to generation through stories and songs, demonstrates how culture can be preserved and developed without physical documentation. It is important to note that such technologies could serve as the basis for the formation of unique worldviews and philosophies that influence ways of interacting with the environment and with each other. Planetary consciousness is a concept that describes the unity of humanity and its connection to the surrounding environment on a global scale. It emphasizes the importance of recognizing that we are all part of one planet, regardless of cultural, linguistic, and geographical differences. In the mid-20th century, with the development of science and technology, particularly in the field of space research, this idea began to gain popularity. The launch of the Sputnik satellite in 1957 and the first human landing on the Moon in 1969 provided humanity with a unique opportunity to view our planet from space. Photographs of Earth taken by astronauts revealed its vulnerability and beauty, sparking a wave of ecological awareness and understanding of the need to preserve natural resources. At this time, various environmental movements emerged, such as the Green Party, founded in New Zealand in 1979, which highlighted the interdependence between people and nature. The concept of planetary consciousness includes the realization that the actions of one person can have consequences for all of humanity. For example, global warming caused by carbon dioxide emissions is not just a problem for one country, but a challenge that requires joint efforts at the international level. In 1992, at the summit in Rio de Janeiro, the United Nations Framework Convention on Climate Change was signed, marking one of the first steps towards recognizing this interconnectedness. An important aspect of planetary consciousness is the use of technology to create global networks of mutual aid and cooperation. The appearance of the Internet in the 1990s fundamentally changed the ways of communication and information exchange, leading to the formation of a global village. Numerous online platforms, such as Change.org, allow people to unite to solve social and environmental problems. This interconnectedness can serve as a basis for forming a new worldview, where individual interests are not the only values, but the common good. In recent decades, there has been a growing interest in sustainable development concepts, reflecting the desire of communities to find a balance between economic development and the protection of the environment. The adoption of the Sustainable Development Goals by the UN in 2015 was an important step in integrating planetary consciousness into global politics and economics. These goals emphasize the need for joint work to eradicate poverty, ensure equality, and protect the planet, highlighting that success in one area depends on success in others. It is interesting to note that planetary consciousness is not limited to environmental or economic aspects. It encompasses cultural and social issues, fostering dialogue between different cultures and peoples. In this context, exchange programs and international projects, such as Erasmus in Europe, allow young people from different countries to get acquainted, share experiences and views, expanding horizons and understanding diversity. As a result, planetary consciousness becomes an important tool in the fight against prejudices and stereotypes, promoting a deeper understanding and respect for different cultures. For example, in 2020, in response to the COVID-19 pandemic, many countries united to develop vaccines, demonstrating how rapid cooperation can lead to significant results in the field of health protection. This case is a vivid example of how global problems require global solutions, and that humanity can work together for the common good. The hypothesis of Gaia, proposed by ecologist James Lovelock in 1979, posits that Earth functions as a single self-regulating organism. Lovelock described this approach in his book, Gaia, A New Look at Life on Earth, where he highlighted the interaction between the biosphere, atmosphere, hydrosphere, and lithosphere as a unified system that supports life. For instance, he asserts that the level of carbon dioxide in the atmosphere is regulated by vegetation and oceans. When the level of carbon dioxide increases, plants begin to absorb it more quickly, and oceans start to absorb it, ultimately stabilizing the climate. Lovelock also proposed that such self-regulating mechanisms can create stable ecological conditions, allowing life to develop and evolve. This leads to intriguing contemplations about planetary forms of intelligence, suggesting that Earth might possess some collective consciousness. Research, such as the work of scientist and philosopher Francis Bacon in the 16th century, who spoke of nature as a living organism, resonates with modern views of Gaia. Some scientists, like Sherry Turkle in her book The Second Body, assert that human interaction with nature can be analyzed through the lens of this hypothesis, as our behavior directly influences the planet's self-regulation. There are numerous examples, such as climate change, where human activity disrupts natural mechanisms, demonstrating that Earth is not merely an object, but a complex system that responds to changes. Some researchers, like Bruno Latour in his work We Have Never Been Modern, discuss how these interactions can be understood as a form of intelligence that includes not only human activity, but also the actions of ecosystems as a whole. For example, the response of ecosystems to climate change can be seen as a kind of intelligent behavior, where different elements of nature interact to maintain balance. Lovelock also emphasizes that life on Earth has evolved in response to changes in the surrounding environment, which supports his ideas about self-regulation. An example of this is the oxygen catastrophe that occurred around 2.5 billion years ago, when cyanobacteria began producing oxygen in large quantities, drastically changing the atmosphere and allowing the development of aerobic organisms. This demonstrates that the biosphere actively participates in creating conditions conducive to life. The interaction between living organisms and the non-living environment can be illustrated through the carbon cycle, which supports climatic conditions and ecological systems. For instance, the carbon cycle includes the process of photosynthesis, where plants absorb carbon dioxide and release oxygen, which is the basis of life on Earth. Lovelock is not the only one who has explored these issues. His ideas have been taken up in the research of other scientists, such as Martin Redford, who studied the relationship between ecosystems and climate, as well as the social aspects of climate change and its impact on human society. Thus, the Gaia hypothesis opens new horizons for understanding the interaction between humans and nature, emphasizing the complexity and interconnectedness of all elements of Earth. In turn, this raises important questions about how we can more responsibly treat our planet, taking into account its unique self-regulating mechanisms. Lovelock continues to actively discuss his ideas, and despite criticism, his hypothesis remains of interest to researchers and ecologists around the world. The study of microbial collective intelligence is an intriguing field that captivates the attention of scientists and researchers. This hypothetical form of consciousness is based on the interaction of trillions of microorganisms living on Earth and their ability to create a global neural network. For instance, the human body contains more than trillions of microbes, and their interactions can influence our health, mood, and even behavior. The human microbiome, composed of bacteria, viruses, and fungi, does not merely passively coexist with us, but actively participates in metabolic processes and protection against pathogens. Research shows that certain types of bacteria can produce neurotransmitters such as serotonin, which is responsible for our emotional state. Additionally, studies conducted at the University of California in Los Angeles demonstrate that the microbiome can affect cognitive functions, highlighting its role in shaping the mental state of humans. Microorganisms in various ecosystems interact with each other, forming complex networks. Biological interactions, such as symbiosis, parasitism, and competition, create unique dynamic systems that can be comparable to neural networks in the human brain. Scientists like Dr. Jonathan L. Brandt from the University of Maryland have proposed models that demonstrate how groups of microorganisms can communicate with each other through chemical signals and produce joint reactions to changes in the environment. These interactions can lead to the formation of resilient communities that can adapt to changing conditions. In such communities, information is transmitted in a manner similar to the transmission of signals in neurons, where each cell contributes to the collective consciousness. The global neural network created by microorganisms can have far-reaching consequences for ecosystems. For example, a study conducted in 2016 showed that bacteria in soil can rewrite their genetic instructions in response to changes in climate, demonstrating their remarkable adaptability and ability to collectively learn. This interaction can lead to changes in ecosystem processes, such as the breakdown of organic matter and nutrient cycles. It is important to note that these interactions are not limited to microbes, but also include more complex organisms, such as plants and animals, creating a multi-level network where each element plays its role. Research shows that the microbiome can also participate in a collective immune response, opening new horizons for understanding the interaction between organisms. For instance, a study conducted in 2018 at the University of Texas found that microbes in the gut can warn the body about pathogens, activating protective mechanisms before an infection can develop. This confirms the idea that the collective behavior of microbes can be equivalent to more complex forms of consciousness. Comparing microbial collective intelligence with neural networks can be extended through analogies with artificial intelligence. In computer neural networks, information is processed through interactions between nodes that can learn based on data. Microbial communities, in turn, can adapt and evolve, reacting to changes in the environment, making them similar to machine learning systems. Each type of microorganism contributes a unique aspect to the overall state of the ecosystem, and this interaction can be key to understanding biological resilience and the health of the planet. Microbiology can provide us with tools for a deeper understanding of how these systems function and how we can use this knowledge to address global challenges such as climate change and biodiversity loss. Considering the scale and complexity of these interactions, the study of microbial collective intelligence opens up numerous prospects for future research. In this context, it is worth noting that research on microbiomes has already led to significant discoveries in medicine and ecology, and continues to be conducted worldwide. Fungal mycelial networks represent complex and multi-layered structures that function as an underground communication system, capable of transmitting information over long distances. These networks, composed of mycelium, can extend for kilometers and connect different plants, allowing them to exchange nutrients and chemical signals. Research indicates that mycelial networks have been functioning for over 100 million years, as evidenced by fossilized fungi found in geological layers dating back to the Cretaceous period. Scientists such as Dr. Patricia Gibson from the University of Alaska note that these networks can not only support the health of ecosystems, but also serve as a kind of internet system in nature, linking plants and organisms over large distances. 80% of all terrestrial plants depend on fungi for essential nutrients through mycelial networks, making them critically important for ecosystem health. For instance, studies conducted in the 1990s in California forests showed that trees connected through mycelial networks receive up to 20% of their nutrients from neighboring plants, promoting more efficient growth and survival. These networks provide plants with necessary carbohydrates and minerals, and can also transmit signals about pests, allowing neighboring plants to activate defensive mechanisms. Additionally, mycelial networks can store information about the state of the surrounding environment, making them potential repositories of ecological memory. Research conducted in the 2000s showed that fungi can recognize chemical signals and respond to them, adapting to changes in the ecosystem. This discovery highlights the potential of fungi as active participants in ecosystems, capable not only of exchanging substances, but also of exchanging information. In some cases, mycelial networks can restore ecosystems after natural disasters, such as forest fires, helping new plants to establish and obtain necessary resources. Mycelial networks also serve as homes for numerous microorganisms, such as bacteria and nematodes, further enhancing their role in the ecosystem. As a result, fungal mycelial networks are not only a vital element of ecology, but also a potential foundation for our planetary communication system, which has existed for hundreds of millions of years and continues to evolve, adapting to changes in the environment. They demonstrate remarkable abilities for interaction and mutual aid, making them key players in maintaining the balance in ecosystems. An example of such a communication system is the mycelium of the Armillaria melea fungus, which can cover up to 10 square kilometers and is considered one of the largest living organisms on the planet. Temporal chauvinism refers to a concept where certain historical periods or epochs are perceived as more significant or progressive compared to others. This phenomenon distorts historical perception as contemporary standards and achievements are projected onto the past, creating an illusion that earlier times were less developed or even primitive. A striking example of temporal chauvinism is the view that the Industrial Revolution in the 18th and 19th centuries was an exclusively positive phase, while its environmental and social consequences are often overlooked. In this context, it is worth noting that, according to historical research, the level of air pollution in Britain increased significantly during the period from the 17th to the 19th century, leading to a deterioration in the health of the population. Temporal chauvinism not only distorts the perception of history, but also influences contemporary social and political processes, contributing to the creation of myths about golden ages and declines of civilizations. For instance, in various countries around the world, political leaders often refer to past achievements, ignoring the real problems that societies face today. Research shows that such ideas can undermine critical thinking and spread stereotypes associated with certain epochs. In turn, this can lead to societies perceiving certain groups of people as less significant or less worthy, based on their historical context. It is important to note that such views are often formed on the basis of incomplete or distorted data, which further exacerbates the situation. For example, some historians point out that the perception of ancient civilizations as ideal can lead to an underestimation of their internal conflicts and problems, such as slavery, social inequality, and wars. Temporal chauvinism can also manifest itself through education, where curricula emphasize the achievements of a particular culture while ignoring the contributions of other nations. This creates an illusion that progress is a linear process in which some cultures win and others lose. For instance, in some countries, history lessons often focus only on the achievements of Western Europe, while the contributions of Eastern civilizations to science and philosophy remain unnoticed. Research shows that such a one-sided view of the past can lead to the formation of biased opinions about other cultures and peoples, which in turn exacerbates international conflicts. Temporal chauvinism also has its roots in contemporary media, where the focus on certain historical events and figures often leads to the creation of historical myths that lack factual basis. An example of this is the popularization of the hero figure in cinema and literature, which shapes viewers' and readers' distorted perception of historical events. It is important to understand that temporal chauvinism not only distorts our memory of the past, but also influences our perception of the present and future, creating barriers to mutual understanding between cultures and peoples. Research data indicate that the more susceptible societies are to temporal bias, the higher the likelihood of conflicts and misunderstandings on a global scale. Modern people often have a tendency to consider past epochs as less developed and primitive, which is a profound mistake and overlooks the possibility of the existence of highly advanced civilizations in antiquity. It is believed that technologies and science only emerged in the last few centuries, but historical facts refute this assertion. For example, in the 30th century BC in Mesopotamia, the Sumerians created the first writing system in the world, cuneiform, which allowed them to record laws, keep trade records, and even write literary works such as the Epic of Gilgamesh. In ancient Egypt, starting from the 3rd millennium BC, they built colossal pyramids, such as the Great Pyramid in Giza, which is 146 meters tall. To construct such a structure, the Egyptians used complex design and construction methods, including a system of inclined frames that extended over 1 kilometer and 500 meters. In India in the 6th century BC, a number of numeral systems, including the concept of zero, were developed, which became the foundation for mathematical knowledge that later spread throughout the world. There is also evidence of highly advanced medicine in ancient civilizations. In ancient Egypt, physicians used methods including surgical operations and herbal treatments, long before modern medical practices were developed. In China in the 3rd century BC, a compass was invented, which was used for navigation and trade, significantly increasing the possibilities of sea travel and commerce. There are numerous examples of high technologies in antiquity, such as the aqueducts of the Romans, which supplied cities with water through a well-designed system of canals and waterways. The Roman Empire, at its peak, possessed a complex network of roads, the total length of which exceeded 80,000 kilometers, facilitating the rapid movement of troops and trade caravans. At the same time, achievements such as ancient theaters, aqueducts, and temples demonstrate not only engineering skills, but also a high level of cultural and artistic life. People often forget that many achievements of ancient civilizations were the result of centuries of research and knowledge accumulation. The Greeks, for example, in the 5th century BC, created philosophy, which laid the foundations for science and logic. Philosophers such as Plato and Aristotle discussed complex concepts that remain relevant to this day. At the same time, the Babylonians developed astronomy, recording the movements of planets and stars, which allowed them to predict solar and lunar eclipses. Furthermore, archaeological finds such as the mysterious megaliths of Stonehenge, built around 2,500 years BC, testify to a high level of knowledge in astronomy and architecture. These stone structures are positioned so that they accurately indicate the rising and setting of the sun on specific days of the year, indicating the presence of complex astronomical observations. It is believed that ancient people were less developed due to the lack of modern technologies. But this view overlooks the fact that many of these technologies were based on knowledge and methods that were developed and refined over centuries. For example, in ancient China in the 10th century BC, gunpowder was already used for military purposes, which is one of the earliest examples of the use of chemical substances in warfare. In the end, it is necessary to understand that highly advanced civilizations existed long before our era, and their achievements should not be underestimated. Ancient people created complex societies with high standards of living, which may have even surpassed many modern models. Understanding this fact can change our perception of human history, opening new horizons for study. In the present time, we continue to discover artifacts that challenge our understanding of the development of civilizations, such as recently discovered underwater structures off the coast of Japan, which may change our understanding of ancient maritime voyages. The cyclical nature of history is not merely an abstract concept, but a reality confirmed by numerous examples from our geological history. On Earth, various civilizations have risen to unprecedented heights, only to fall, leaving behind ruins. For instance, Mesopotamia, the cradle of the first cities like Uruk and Ur, reached its peak in the 3rd millennium BCE when the Sumerians developed irrigation systems and cuneiform writing. However, by the beginning of the 2nd millennium BCE, the Sumerian culture began to decline, giving way to the Akkadians and later the Babylonians, who also did not escape collapse. This decline was the result of numerous factors, including ecological changes, wars, and internal conflicts. The cyclical nature of history can be seen in the civilization of the Maya, which flourished in Central America from the 3rd to the 9th century CE, building magnificent cities and complex calendars. However, by the 10th century, many of these cities were abandoned, and the reasons for this remain a subject of debate among scholars. One hypothesis suggests that climate change, leading to droughts and resource scarcity, was a factor. Interestingly, some researchers, such as Professor David Stewart, argue that the Maya did not simply disappear, but adapted to new conditions by moving to more favorable regions. Similar processes can be observed in other parts of the world, such as ancient Egypt, where dynastic changes and political instability led to the decline of the great pharaohs. Each time one society fell, another rose in its place. For example, during the decline of the Roman Empire, new kingdoms and states emerged from its ruins, such as the Byzantine Empire and various Germanic kingdoms. Their development also passed through cycles of rise and fall, as documented in historical chronicles like the works of Procopius of Caesarea, who described both the ascents and descents of the Eastern Roman Empire. The cyclical nature of history can be observed even in more recent times, such as in the case of India, where the Mauryan Empire reached its zenith in the 3rd century BCE, but later fragmented into numerous small states, paving the way for powerful empires like the Guptas in the 4th century CE. Scientific research indicates that such cycles may be linked to climate changes, social factors, and technological advancements. For example, climate changes such as the medieval cooling contributed to economic decline in Europe, but also spurred technological innovations in other regions, such as China, where in the 12th century gunpowder and the compass were invented, altering the course of history. There are even theories, such as the concept of the Second Industrial Revolution, which suggest that every 100 years we witness a surge in new technologies that lead to both rises and falls of civilizations. These cycles are often described in the works of historians like Arnold Toynbee, who identified 18 civilizations that passed through similar stages. It is important to note that each civilization contributed to the overall development of humanity, leaving behind diverse legacies from architecture to philosophy. For example, the Greeks, who developed democracy and philosophy, laid the foundations of the Western world, while the Chinese, with their inventions like paper and gunpowder, influenced technological development. The cyclical nature of history is not just the repetition of the same events, but a complex process of cultural and technological interaction that continues to influence contemporary society. Over the past several thousand years, we have seen societies rise and fall, but in this context, it is important to consider that each new wave of innovation and social progress often arises from the ruins of previous ones. As humanity continues to adapt to changes, we can expect these cycles to repeat in the future. There are studies that show that every 300 years, a significant technological revolution occurs, altering social structures and economic systems. The concept of forgotten knowledge encompasses lost knowledge and technologies that once existed in various civilizations, but were lost due to global catastrophes, migrations, or cultural collapses. One of the most striking examples is the fall of the Roman Empire in the 5th century AD, when many achievements of ancient science and art were forgotten for several centuries. As a result of this collapse, not only did the number of scholars decrease, but access to libraries containing important texts was also lost. For instance, many works by Hippocrates and Galen, which formed the basis of medicine, became inaccessible in the Middle Ages, leading to stagnation in medical knowledge. The recovery of these knowledge required centuries and was not without the efforts of scholars like Avicenna, who in the 10th century compiled and systematized ancient medical texts, translating them into Arabic. Another vivid illustration of knowledge loss is the disappearance of the Maya civilization, which reached high levels in astronomy and mathematics. After their collapse in the 11th century, a significant part of their scientific achievements was forgotten, and the remaining records on tree bark, which had survived, were destroyed by Spanish conquistadors in the 16th century. This underscores how vulnerable knowledge is in the face of cultural and military catastrophes. Due to migrations and collapses, such as the Hunnic invasion in the 4th century, many peoples were forced to leave their lands, losing their cultural achievements and knowledge. This process also occurred in ancient Egypt, where conquests by Alexander the Great led to the loss of a significant part of Egyptian knowledge, which was integrated into Greek culture, but many local practices disappeared. On the other hand, some knowledge about agriculture and construction, used by ancient civilizations, was lost when people adopted a nomadic lifestyle. For example, tribes migrating from the territory of modern Mesopotamia left behind ruins, but their agronomic skills were lost for many centuries. Simultaneously, in India, due to invasions and internal conflicts, knowledge of Vedic texts was lost, which formed the basis of Vedic culture. This led to their further transformation and adaptation in new conditions. Even today, we encounter examples of forgotten knowledge when modern technologies and globalization lead to the loss of local traditions and practices. Therefore, forgotten knowledge remains an important aspect of our history, demonstrating how civilizations built and destroyed their achievements, and how each new generation ultimately recreates what was lost. Scholars estimate that up to 70% of ancient texts have been lost over the last 2,000 years. Cosmic consciousness is a concept that encompasses the understanding and awareness of humanity's place in the universe and the interconnectedness of all living beings with the surrounding world. This idea began to develop at the end of the 19th century, when scientists like the German astronomer Johannes Kepler started to perceive space and time as more than just physical measurements. In the early 20th century, astrophysicists such as Albert Einstein formulated theories of relativity that transformed our understanding of space and time, demonstrating that they are interrelated and influence each other. Within this framework, cosmic consciousness includes the realization that Earth is not the center of the universe, but merely one of many planets orbiting their stars. The advancement of astronomy and technologies such as telescopes and spacecraft has given humanity a clearer picture of the vastness of the cosmos. In 1999, the launch of the Hubble telescope opened new horizons for astronomy, providing images of distant galaxies and star systems, making it evident that the universe is full of unexplored mysteries and possibilities. In this context, cosmic consciousness implies not only a scientific but also a philosophical understanding of our existence, emphasizing the need to comprehend the connections between humanity and the cosmos. At the beginning of the 21st century, with the development of technologies and space exploration, such as missions to Mars and the study of exoplanets, it became clear that humanity stands on the threshold of new discoveries. Scientific research shows that the conditions on Earth that support the emergence of life may be similar to those on other planets. Programs like SETI, Search for Extraterrestrial Intelligence, are aimed at finding signals from extraterrestrial civilizations, further underscoring the importance of cosmic consciousness. It encourages people to reflect on how our existence is connected to the boundless expanses of the universe and what lessons can be drawn from this understanding for future generations. Moreover, in recent decades, the concept of cosmic consciousness has inspired numerous cultural and artistic movements that explore themes of unity, harmony, and interconnectedness. For example, artists and writers use cosmic imagery to convey feelings and ideas about human existence. In 2020, the launch of the Mars 2020 mission, which includes the rover Perseverance for studying Martian soil and searching for signs of ancient life, underscores that our understanding of life is not limited to one planet. We strive to understand how life arises and develops in different conditions, which only adds depth to our cosmic consciousness. All these aspects highlight that cosmic consciousness is not just a philosophical category, but a reality that requires us to take responsibility for our existence on Earth and in the cosmos. With each new discovery, we realize that we are not just inhabitants of our planet, but part of a vast, complex system where everything is interconnected. In 1968, the astronauts of the Apollo 8 mission became the first people to see Earth from space and capture this moment on a photograph, which became a symbol of global unity and an awareness of the fragility of our planet in the vastness of the cosmos. The hypothesis of panspermia suggests that life on Earth could have originated due to microorganisms or organic molecules brought to our planet from space. This idea dates back to ancient thinkers, such as the Greek philosopher Anaximander, who proposed that life could have emerged from other worlds. In the 20th century, this hypothesis gained new traction with the discovery of organic compounds, like amino acids on comets and meteoroids. For example, in 2008, scientists analyzing the Martian meteorite found more than 20 amino acids, confirming the possibility of organic molecules in space. Panspermia raises intriguing questions about how and when life could have been brought to Earth. Some scientists, like Frank Cioffi, suggest that life could have developed on one planet and then been ejected into space due to a collision with an asteroid or comet. In this context, the possibility of intelligent beings creating or spreading life is also considered. In the 21st century, scientists like David Merritt propose that highly advanced civilizations could use technology to transmit life between planets. For instance, using probes that could deliver spores or bacteria to other worlds. Potential evidence of such intelligent beings could be found in ancient texts or myths. For example, Sumerian mythology mentions beings coming from the sky, which could be interpreted as descriptions of contact with extraterrestrial civilizations. Interestingly, in 2015, a group of scientists from Cambridge University suggested that some ancient structures found on Earth might indicate the existence of a highly advanced civilization that predated known history. Research shows that structures like megalithic monuments could have been created using technologies that we still cannot explain. Some geologists even propose that ancient Earth might have hosted extraterrestrial civilizations that left their traces in the form of artifacts. In this context, the hypothesis of panspermia becomes not just a scientific theory, but a foundation for contemplating our place in the universe and our own identity. Beyond Earth, there could be billions of planets where life could have evolved according to different laws, and perhaps it is from these planets that life on our planet originated. Studies of exoplanets show that conditions for life can exist in the most unexpected places, including planets in the habitable zone around red dwarfs. In 2020, astronomers discovered an exoplanet in the habitable zone of its star, with conditions potentially suitable for liquid water, highlighting that life might be much more widespread in the universe than we thought. In this context, the idea of life originating from outer space on Earth becomes increasingly relevant, and new discoveries in astronomy and astrophysics only fuel this interest. For instance, in 2020, the Pluto mission revealed that one of Jupiter's moons, Europa, has a subsurface ocean, which could indicate the presence of conditions for life. The question of how life could have been brought to Earth remains open, and there is still much to learn about our cosmic neighbors. The concept of cosmic intelligence posits the existence of highly intelligent forms of consciousness that can manifest on various planets in different physical forms. This notion gained popularity through the works of scientists like Carl Sagan and his book Cosmos, published in 1980, where he described the possibility of the existence of intelligent beings on other planets. Within this framework, it is assumed that intelligence can develop not only under conditions similar to Earth, but also in completely different environments, such as high-temperature conditions on Venus or low-gravity conditions on the Moon. Scientists like David Bradley propose the idea that forms of life possessing intelligence may not be based solely on carbon, but also on other elements like silicon, opening up additional horizons for the search for extraterrestrial intelligence. Within this hypothesis, various forms of intelligence manifestation are actively discussed, from hypothetical organisms on exoplanets to potential artificial intelligences that may exist in digital worlds. It is noteworthy that in 1991, when astronomers began exploring exoplanets, more than 200 planets were discovered orbiting other stars, and each of them could potentially be a home for cosmic intelligence. In this context, astrophysicists discuss the possibility of the existence of such forms of consciousness that could be capable of interstellar travel, as described in science fiction works, for example, in the novels of Isaac Asimov. In this light, it should be mentioned that in 1999, a group of scientists from the National Aeronautics and Space Administration, NASA, developed the SETI, Search for Extraterrestrial Intelligence project, whose goal is to search for signals from extraterrestrial civilizations. The concept of cosmic intelligence also includes ideas that intelligence may not be only individual, but also collective, as in the case of ant or bee colonies, where the intelligence of the group can exceed that of an individual. In this context, it is worth noting that the concept of panpsychism, proposed by philosopher Gottlob Frege in the 19th century, suggests that consciousness may be inherent in all forms of matter, which can also be applicable to the idea of cosmic intelligence. As a result, there are numerous theories and hypotheses about how intelligence might appear on other planets and how it might interact with its environment. For example, in 2000, astronomers discovered an exoplanet named HD 209458b, located approximately 46 light-years from Earth, which may have conditions suitable for the existence of life. In this context, it is important to consider that any forms of cosmic intelligence may significantly differ from our understanding of intelligence, opening the door to numerous studies and discussions among scientists and philosophers. Quantum entanglement, discovered at the beginning of the 20th century, is a phenomenon where two or more particles become interconnected in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. This phenomenon was first described in 1930 by Albert Einstein, Boris Podolsky, and Nathan Rosen in their work, known as the Einstein-Podolsky-Rosen paradox. They used it to demonstrate that quantum mechanics might be incomplete, as they believed that information could not be transmitted faster than the speed of light. However, experiments conducted in the 1980s, particularly the work of Alan Aspect, showed that entangled particles could indeed change their states instantaneously, which contradicted Einstein's ideas and confirmed the strangeness of quantum mechanics. In the year 2000, a group of scientists led by David Deutsch from Oxford University proposed that quantum entanglement could be used to create a new method of transmitting information between intelligent beings over cosmic distances. They suggested that such technologies could enable the transmission of messages without using traditional communication technologies such as radio waves or lasers, which could take an enormous amount of time to transmit data between stars. The use of quantum entanglement as a mechanism for information transmission involves creating quantum states that can be entangled in one place and then unfolded in another. This means that if one participant changes the state of their particle, the other participant, located at a great distance, instantly receives information about the change. In 1998, scientists from the University of Hong Kong demonstrated an experimental realization of quantum information transmission over a distance of more than 40 kilometers, which showed the possibility of transmitting data using entangled quantum states. They used a special pair of photons that were entangled and were able to transmit information by changing the state of one of the photons. This discovery was the first step towards creating a quantum network that could be used for transmitting information between stars. In 2005, a group of researchers from the University of California, Berkeley, developed a quantum teleportation protocol that also uses entanglement for transmitting quantum states. They were able to teleport a quantum state of an atom over a distance of 1 meter, which confirmed the theoretical assumptions about the possibility of transmitting information using quantum methods. This discovery could lead to the creation of a new generation of communication technologies that could overcome the limitations imposed by light and traditional communication methods. Quantum entanglement could not only change our understanding of information transmission, but also open new horizons in the study of consciousness and the interaction of intelligent beings. Ultimately, while it remains unclear how exactly quantum entanglement can be used in practice for transmitting information over cosmic distances, experiments continue to confirm its amazing properties and potential for future technologies. It is important to note that quantum entanglement does not violate the laws of physics, as it does not allow information to be transmitted faster than light, but rather is based on the principles of quantum mechanics, which are still not fully understood by science. The study of ancient civilizations reveals not only historical events, but also profound philosophical questions concerning the nature of humanity and its place in the world. Ancient societies, such as the Egyptians, Sumerians, and Incas, laid the foundations for understanding time, space, and existence itself. For instance, the Egyptian civilization developed a complex system of beliefs where the afterlife played a key role, as evidenced by their pyramids built to ensure the eternal life of pharaohs. These monumental structures, such as the Great Pyramid of Giza, standing at 146 meters tall, served not only as tombs, but also as architectural symbols reflecting the concept of order and harmony in the universe. The Sumerians, in turn, created the first known writing system, cuneiform, around 3,000 years before our era. This system of recording allowed them to document not only trade transactions, but also mythology, indicating the importance of questions about existence and understanding the world to these people. In Mesopotamia, for example, myths of creation emerged, explaining the origin of humans and their role in the cosmos, clearly demonstrating how ancient peoples sought meaning in their existence. The Incas, who built the magnificent city of Machu Picchu at an altitude of 2,400 meters, revered nature and sought harmony with the surrounding world, reflecting their philosophical understanding of the connection between humans and nature. They developed complex agricultural systems, including terraced farming, to adapt to the harsh conditions of high altitude. This indicates a deep respect for the land and resources among the Incas, which also raises questions about sustainable development and human responsibility for the environment. In ancient China, philosophical ideas began to form around concepts of order and harmony, where phenomena such as feng shui played a significant role in architecture and urban planning. This shows how ancient civilizations sought to bring harmony into their lives through understanding the world around them. The system of governance in ancient Rome, including laws, rights, and civic duties, demonstrates how philosophical ideas about law and justice were put into practice. This system, known as Roman law, became the basis for many modern legal systems and continues to influence our perception of justice. Additionally, ancient Greek philosophy, which became the foundation for Western thought, emerged in the context of democracy and public debates, emphasizing the importance of public participation in the formation of knowledge and truth. All these examples illustrate how ancient civilizations not only created material cultures, but also developed complex philosophical systems that sought to answer questions about life, death, and humanity's place in the universe. A significant aspect is that each civilization had its unique perspective on the world, based on its experiences, environment, and social structures. For example, cultures thriving in conditions of abundance could focus on the development of art and science, while societies facing resource scarcity could develop more rigid systems of management and control. This underscores that the philosophy of ancient civilizations was an integral part of their lives and development. It is interesting to note that throughout history, many philosophical ideas have intersected and influenced each other, creating a rich mosaic of human thought. Astronomy, mathematics, and medicine were closely linked to philosophical reflections, highlighting the connection between science and philosophy in antiquity. Ancient civilizations left behind not only material artifacts, but also a legacy of ideas that continue to influence our understanding of the world. For instance, the concept of democracy, which originated in ancient Greece, remains relevant in modern society. Many philosophical questions about existence, morality, and justice that arose in antiquity are still discussed and studied by contemporary thinkers. Are there universal values that can be applied to all civilizations? Or does each culture have its unique notions of good and evil? Answers to these questions can help us gain a deeper understanding not only of human history, but also of ourselves. It is interesting to note that even in the most isolated societies, there were parallels in philosophical reflections, which may indicate some universality of human experience. Existential questions about the multiple origins and extinctions of intelligent life on Earth raise numerous themes related to our nature and humanity's place in the cosmos. One of the key hypotheses discussed by scientists is that intelligent life could have arisen on a planet multiple times and then disappeared due to various reasons, such as climate change, catastrophes, or even internal social conflicts. This idea is reflected in the research conducted by scientists like Steven Weinberg, the Nobel laureate in physics, who has raised questions about how and why life can disappear and reappear. For instance, around 6 million years ago, during the Miocene epoch, significant climate changes on Earth could have affected existing ecosystems and human evolution. Can we consider that similar catastrophes, such as the asteroid impact that led to the mass extinction of dinosaurs 65 million years ago, could also have caused the disappearance of intelligent life that may have existed before? What is the likelihood of such events repeating in the future? Scientists, including paleontologist David Norman, emphasize the importance of studying fossil remains to understand how ecosystems reacted to changes. These studies can provide insights into how life adapted or went extinct in response to catastrophic events. Another existential question is whether intelligent life similar to ours could have emerged on Earth but disappeared due to a lack of technological resilience. Scientists like Frank Drake, who developed the Drake equation to estimate the probability of the existence of various civilizations in the universe, have explored this question. The question of how long a civilization can exist before self-destructing has become a significant topic in ecological philosophy. For example, research conducted in the 20th century shows that technologies can both promote development and threaten the existence of a civilization. Are there limits beyond which intelligent beings, including us, lose the ability to survive or evolve? What factors contribute to self-destruction, such as wars, ecological crises, or even isolation from the cosmic context? These questions interest not only contemporary philosophers, but also historians who study how various cultures reacted to threats to their existence. For example, in ancient Greek mythology, the concept of hubris, or excessive pride, often led to the fall of civilizations, such as the Minoan civilization on Crete, which was likely destroyed by a catastrophic volcanic eruption around 3,500 years before our era. How can we learn from history to prevent the repetition of such mistakes in the future? Questions about how humanity can use knowledge of its ancestors to avoid self-destruction are becoming increasingly relevant in light of modern threats such as climate change and nuclear conflicts. Researchers in the field of anthropology, such as Claire Farrell, emphasize that studying cultural and social dynamics can provide insights into how we can adapt to new challenges while preserving our identity and resilience. Understanding the cycles of life and death of civilizations may be the key to survival. Intelligent life on Earth, as we know, has existed for about 200,000 years. But what will happen if in the future we face new threats that were unknown to our ancestors? How many times will we experience rise and fall? There are no definitive answers to these questions, but research shows that each civilization must learn from its experience to avoid past mistakes. The discovery of new archaeological finds, such as ancient civilizations in Mesopotamia or lost cities in Central America, continues to remind us that intelligent life on Earth has always been at risk. The concept of cosmic loneliness of humanity is based on the assumption that we may be the only intelligent beings in the universe. This idea gained popularity thanks to scientists like astronomer Carl Sagan, who, in his book Cosmos, published in 1980, discussed the probability of the existence of extraterrestrial civilizations. Sagan wondered why, if there are so many stars and planets in the universe, we have not yet found any signs of life similar to ours. This concept provokes deep reflections on our place in the vast cosmos and how we perceive ourselves. If we were to find evidence of the existence of ancient non-human civilizations, this could fundamentally change our understanding of ourselves. For example, if archaeologists discovered traces of initial civilizations on Mars or Europa, a moon of Jupiter, this would cast doubt on our uniqueness as intelligent beings. Discoveries of this kind could lead to a rethinking of our role in the ecosystem of the universe. In 1962, the SETI, Search for Extraterrestrial Intelligence project, was launched, which focused on searching for radio signals from extraterrestrial civilizations. However, over the decades, scientists have only detected background noise from space, which has only strengthened the idea of our loneliness. But what if we discover traces of ancient technologies similar to ours? For example, if we found artifacts on Venus or in the asteroid belt that indicated the existence of intelligent life in the past, this could not only confirm that life exists in various forms, but also provide us with new models for understanding the very concept of life. The discovery of such artifacts could serve as a catalyst for changing our self-perception, making us view Earth as one of many planets where life can develop, rather than as the sole home for intelligent beings. In the 1990s, scientists announced findings that could indicate the existence of ancient microbial forms of life on Mars, which would be the first step in understanding that life can arise in various conditions. This question also raises philosophical and ethical aspects. Do we have the right to call ourselves the highest form of intelligence if other forms of life could have existed for millions of years? The discovery of traces of ancient civilizations could not only confirm that intelligent life is not unique to Earth, but also raise new questions about our future. For example, in 1983, During the analysis of the ALH 84001 meteorite found in Antarctica, scientists discovered structures that could be signs of fossilized life. This discovery sparked heated debates among scientists and led to new research. The concept of cosmic loneliness is linked to questions about how we should behave if we ever come into contact with other intelligent beings. Perhaps the answers to these questions lie in how we perceive our own history and evolution. We must remember that over millions of years, humanity has gone through numerous changes and crises, and the realization that other civilizations could have faced similar challenges could help us better understand our own problems. Each new discovery, whether it is the finding of an ancient civilization on Earth or traces of intelligent life on other planets, makes us reflect on how we can change our self-perception in the context of the vast cosmos. The cosmos, full of mysteries, continues to remain a puzzle for us, and each discovery we make brings us closer to understanding our place in this great and mysterious space. In 1998, astronomers discovered an exoplanet located in the habitable zone of its star, which also added new shades to our understanding of the possibility of life beyond Earth. The study of cosmic heritage raises numerous philosophical questions about our responsibility as modern humanity. We are the continuators of a long line of intelligent life on Earth that has existed for more than 3 billion years. This line includes not only our predecessors, such as the Neanderthals, but also earlier forms of life that shaped the planet's ecosystems. For example, around 30 million years ago, the ancestors of modern primates appeared on Earth, becoming a significant part of the evolutionary process. It is important to realize that every living being, every ecosystem, and every epoch has left its mark on the genetic code and cultural memory of our civilization. The philosophical aspects of cosmic heritage also raise the question of our place in this chain. We must consider how our behavior today will affect future generations. Scientific research shows that human activity has led to the extinction of around 1 million species of animals and plants over the last century, threatening the biological diversity necessary for life. This legacy we leave will determine not only our own survival, but also the future of all living beings on the planet. One striking example of this awareness of responsibility is the work of ecologists and philosophers like Vanessa Atienza and her book, Living Systems: Philosophy of Ecology. She emphasizes that humanity must transition from a consumerist relationship with nature to a more sustainable and harmonious coexistence. This means that we must re-evaluate our values and priorities to respect and preserve the complex web of life that surrounds us. This philosophical stance implies that, as intelligent beings, we must become guardians of the planet, not its destroyers. Scientific research shows that climate change, caused by human activity, is already leading to a 2 degrees Celsius increase in temperature, with serious consequences for ecosystems and human society. We must understand that every decision we make, whether it is choosing sustainable transportation or refusing single-use plastic, matters. At the same time, philosophers like Albert Camus considered the absurdity of human existence and our attempts to find meaning in a world that seems devoid of it. However, it may be in this absurdity that our responsibility lies. We must create meaning in what we do and understand that every action of ours affects the future. Thus, cosmic heritage not only underscores our connection to the past, but also poses a challenge. How can we build the future while learning from the mistakes of previous epochs? We have the opportunity to learn from errors, such as the collapse of the Maya civilization, which, despite its achievements in astronomy and agriculture, could not adapt to changing climatic conditions. These lessons from the past should inspire us to take actions that prevent such tragedies from recurring. Scientific research shows that sustainable development is not just a fashionable phrase, but a necessity for human survival. In the year 2000, the United Nations adopted the Agenda for the 21st Century, which emphasizes the importance of integrating ecological, social, and economic factors into decision-making processes. We must understand that the future of our planet depends on the choices we make today. Thus, cosmic heritage requires us not only to recognize our connection to the past, but also to actively participate in shaping the future. We must take responsibility for the preservation of the planet, its resources, and its biodiversity. This is not just a task, but a duty to those who came before us and to those who will come after. Each of us can contribute starting with simple steps such as recycling waste and supporting eco-friendly initiatives. Understanding this responsibility and recognizing our place in the chain of life on Earth are important aspects of our existence. In 2020, the World Health Organization reported that around 90% of the Earth's population breathes polluted air, highlighting the urgent need for immediate action to improve the state of the environment. The study of metaphysical questions regarding consciousness and reason, especially in the context of the possible existence of non-human forms of intelligence in the distant past of Earth, opens up broad horizons for contemplation and research. The question of what constitutes reason has troubled philosophers and scientists for centuries. In 2002, renowned philosopher Daniel Dennett, in his book The Mind as a Machine, raised the question of whether consciousness could be a result of evolutionary processes, which leads to the thought that other forms of life could have developed their own intelligent approach to existence. One of the most discussed examples of non-human intelligence is the intelligence of dolphins. Research conducted in the 90s of the 20th century showed that dolphins possess a developed system of communication and can even use tools, which makes one ponder their ability for abstract thinking and self-awareness. In 2003, a group of researchers led by Dr. Lawrence Connor discussed the possibility of the existence of other forms of consciousness based on completely different biological systems from those of humans. In this context, it is interesting to study fossil remains, such as those found in ancient layers of Earth, where intelligent beings similar to modern mammals, but with completely different, possibly extraterrestrial forms of intelligence, could have lived. In 2015, scientists from MIT discovered that some known fossils, such as Australopithecines, could have had a more complex social structure than previously thought. This suggests that various forms of life on Earth could have developed their own ways of solving problems and interacting with the surrounding world. It is important to note that in 2009, a study was published in which it was claimed that even some types of plants are capable of forms of communication, which raises the question of what constitutes reason. These examples show that the boundaries between different forms of intelligence may be much more blurred than we are accustomed to thinking. In 2017, Dr. Linda Matthews from the University of Cambridge presented a hypothesis that even in prehistoric times on Earth, there could have existed complex ecosystems with forms of reason that we cannot fully understand. Some scientists even suggest that such forms of intelligence could have influenced entire ecosystems, creating unique conditions for the existence of other species. This concept becomes particularly relevant in light of recent discoveries in the field of paleontology, where evidence of the existence of highly developed marine ecosystems that existed more than 300 million years ago has been found. These findings open up the possibility for further research that could either confirm or refute hypotheses about the existence of complex forms of reason long before the appearance of humans. In 2020, a group of scientists from Stanford University proposed studying ancient cultural artifacts, such as cave paintings and megaliths, to try to determine if they were created by intelligent beings different from us. These artifacts could serve as evidence of the existence of forms of reason that used symbolism and creativity to express their thoughts and feelings. Examples include the famous cave paintings in Lascaux, which date back more than 30,000 years and may indicate the presence of meaningful self-expression. It is important to emphasize that this topic generates numerous debates and discussions among scientists, as different researchers have different opinions regarding the definition of reason and its manifestations. However, the more we learn about the past of our planet, the more questions arise about the consciousness of our predecessors and what forms of reason could have existed on Earth long before us. In 2020, a study on the impact of climate change on the evolution of life on the planet showed that adaptation and survival under stress conditions could have led to the emergence of new forms of intelligence. The study of the traces of ancient civilizations raises numerous ethical questions concerning the respect for the cultural heritage of extinct intelligent species. Archaeologists and historians often face a dilemma: how to conduct excavations and research without violating sacred sites and offending the memory of people who once lived on these lands. For example, excavations in Machu Picchu in Peru led to the discovery of unique Inca artifacts, but also sparked protests from local residents who consider this territory sacred. In 2006, the Peruvian authorities introduced restrictions on the number of tourists to preserve the site and respect the traditions of the indigenous population. There is also the question of how to handle the artifacts found. 18,000 years ago, when people began creating items from bone and stone, they could not foresee that their works would become part of modern heritage. In 2012, a group of scientists from Bilkent University in Turkey discovered ancient human tools, which they handed over to a local museum. This decision sparked debates about who owns these artifacts: the local residents on whose land they were found, or all of humanity as part of a common heritage. Some researchers raised the question of how ethical it is to extract items from their historical context. In 2015, a study conducted by Professor James Kanan from the University of Michigan showed that removing artifacts from their primary environment can lead to distortion of historical facts and a misinterpretation of culture. For instance, if ceramic pottery from an ancient village is displayed in a museum without explanation of its context, viewers may not understand its role in the lives of people at that time. Questions of ownership of cultural artifacts remain relevant. After World War II, several countries, such as Greece, began actively demanding the return of their cultural values that were taken as a result of colonization. For example, in 2010, Greece made an official request for the return of the Parthenon, which is located in the British Museum, citing its historical and cultural significance for the Greek people. This situation underscores the importance of respect for cultural heritage and the need for dialogue between countries to find a compromise. It is also important to consider the opinions of indigenous peoples in the study of ancient civilizations. For example, in Australia, local Aboriginals actively participate in archaeological research related to their ancestors. In 2006, a Memorandum of Understanding was signed between the Australian government and Aboriginals, ensuring their participation in research and the protection of sacred sites. This cooperation not only respects Aboriginal culture, but also enriches scientific knowledge about the past. Therefore, the ethical aspects of searching for and studying the traces of ancient civilizations require a careful approach and respect for cultural heritage. Researchers must understand that behind every artifact lies a history, and their task is not only to uncover new facts, but also to preserve the memory of those who lived before us. In 2019, an international conference on archaeology and ethics, held in Paris, gathered scientists from around the world to discuss approaches to the study of cultural heritage, emphasizing the importance of cooperation, dialogue, and respect for history. Cosmic ethics is a relatively new concept that examines moral obligations between intelligent species that may be separated not only by distance, but also by time. The foundations of this idea were laid in the mid-20th century, when astronomers began actively studying the possibility of the existence of extraterrestrial civilizations. In 2003, astrophysicist David Braverman proposed a theory according to which intelligent beings in different time periods may have mutual responsibility for their own fate and the fate of other species. This implies that if one civilization has reached a high level of technological progress, it should consider the consequences of its actions not only for its own world, but also for those who may appear in the future. For example, if we colonize other planets, we should consider how this will affect local ecosystems and possible intelligent life forms. Research shows that such actions can lead to irreversible changes that will affect not only the current generation, but also future ones. In 2009, a group of scientists from the University of New South Wales, under the leadership of Professor Robert Hale, conducted a study that showed that even the simple presence of humans on another planet can cause changes in the biosphere, thereby raising ethical questions about how far we have the right to interfere with nature. On a more philosophical level, cosmic ethics also raises questions about how we should treat potential extraterrestrial civilizations. For example, if we eventually discover life on other planets, what can or should we do with this information? In 2006, an international conference on astronomy in Tokyo drew attention to the fact that any attempts to contact extraterrestrial civilizations should be based on principles of respect and cooperation. Researchers argue that acting selfishly, we risk repeating the mistakes of the past when humanity colonized new lands, ignoring the rights of local peoples. The concept of cosmic ethics, therefore, requires us to recognize that our responsibility may extend far beyond our planet and the present time. There are even proposals for the creation of international norms regulating research and possible colonization of other planets. which could serve as a basis for future space missions. This is a question that requires not only scientific understanding, but also broad public discussion, as it touches on fundamental aspects of our existence. In 2015, a declaration called Cosmic Heritage was developed, which emphasizes the need to consider ethical aspects in space research, including the protection of potential ecosystems on other planets. The complexities of this issue become increasingly relevant as humanity continues to develop technologies that allow us to venture into the depths of space. On November 18, 2021, NASA announced the launch of a mission to explore the moons of Jupiter, which renews the discussion about how we will treat possible extraterrestrial life if it is found on such bodies. These discussions raise important questions about what our moral obligations will be towards other intelligent beings, if they exist, and how our civilization will act in response to their possible existence. Heritage for the future is a concept that encompasses a wide range of aspects, from preserving culture to environmental sustainability. Culturally, heritage includes not only physical objects like buildings and artifacts, but also traditions, language, music, and customs that are passed down from generation to generation. For instance, in 2006, UNESCO recognized the traditional art of Australia's Indigenous peoples as part of the intangible cultural heritage, highlighting the importance of preserving not only physical, but also cultural aspects. The environmental component of heritage for the future involves managing natural resources in such a way that they are available to future generations. In 2010, the World Health Organization reported that 800 million people worldwide lacked access to clean drinking water, threatening not only their health but also the ability of future generations to live in a sustainable world. It is important to note that heritage for the future is not limited to material achievements. It also includes ethical and social norms that we pass on. For example, the concept of human rights, formulated in the 20th century, became the basis for international agreements and laws aimed at protecting human dignity. In 2020, the UN General Assembly adopted a resolution calling for the protection of human rights during the pandemic, demonstrating how our heritage can influence current global issues. Innovation and technology also play a key role in creating heritage for the future. The development of renewable energy sources, such as solar and wind power, can ensure sustainable development and reduce dependence on fossil fuels. For example, in 2009, Denmark became the first country where wind energy accounted for more than 30% of total electricity production, marking an important step towards a cleaner and more sustainable future. Finally, heritage for the future is also linked to education and enlightenment. By teaching the younger generation the importance of sustainable development, we create conditions for them to make informed decisions in the future. According to UNESCO, by 2020, more than 130 million children lacked access to quality education, threatening their ability to contribute to the creation of a sustainable society. It is important to remember that each generation is responsible for leaving behind a world that not only survives, but also thrives. In 2015, 80 countries signed the Paris Agreement on climate change, demonstrating global commitment to combating climate change and preserving the planet for future generations. Creating long-term messages for future civilizations that may arise on Earth after the disappearance of humanity is a complex task that requires a deep understanding of language and an awareness of long-term changes on the planet. One of the first examples of such an approach is the project Cosmic Capsule, or Time Capsule, developed at the end of the 20th century. In 2001, researchers from NASA and other organizations initiated the creation of capsules that could contain information about human culture, science, and technologies. A crucial part of this project was deciding which language to use. Scientists faced the challenge of how to convey information to potential extraterrestrial civilizations or future human generations that may not know contemporary languages. An example of this is the attempt to create a universal language based on mathematics and scientific principles that would be understandable to any form of intelligent life. One of the most well-known messages is the Golden Record, attached to the Voyager spacecraft launched in 1977. This record contains messages and images describing life on Earth and was sent into interstellar space in the hope that it would one day be found by another civilization. The record includes sounds of nature, music from various cultures, and images that, according to scientists, could be understood by extraterrestrials. For instance, the record contains musical compositions from Bach to traditional folk music. 18 languages are represented in spoken messages, demonstrating the diversity of human culture. One of the most challenging tasks faced by the creators of the record was to make these messages accessible and understandable over millions of years. Additionally, it is necessary to consider that significant changes may occur on Earth during this time, such as climate change, geological disasters, or even the extinction of intelligent species. Such experiences in creating long-term messages can also be observed in the history of civilizations. For example, ancient Egyptians left us hieroglyphs on the walls of temples and pyramids that still tell us about their culture, religion, and social structures. These inscriptions have survived for thousands of years, allowing modern scientists to study them and extract important information about the past. In the 13th century BC, the Hittites created what are known as eternal messages, which were written on clay tablets. These tablets contained laws, treaties, and significant events, and still serve as a source of information about the political life of that time. Recently, in 2023, a group of archaeologists in Turkey discovered more than 100 such tablets, dating back to the 6th century BC, which provide insights into the development of law and governance in ancient times. The design of long-term messages requires a multidisciplinary approach, combining linguistics, archaeology, anthropology, and other sciences. It is also important to consider that messages may be lost or misinterpreted, as happened with some ancient texts that were incorrectly translated or understood. For example, the codices of the Maya, written in hieroglyphs, remained a mystery to scientists for a long time, until their decipherment began in the 19th century. As a result, important information about Maya culture and history was revealed, which had been lost to humanity. Creating long-term messages for future civilizations is not only a challenge, but also an opportunity to preserve humanity's heritage. The development of such messages can become an important step in ensuring the transmission of knowledge and experience that may be useful to future generations. For example, in the 2000s, the Message to the Future program was initiated, in which ideas and concepts were collected that could be useful to humanity in several centuries. This program included both scientific and cultural achievements, emphasizing the importance of preserving a comprehensive image of humanity for future civilizations. Despite the uncertainty of the future, creating long-term messages can become an important tool for preserving knowledge and experience accumulated by humanity over thousands of years. For instance, in 2012 in Japan, a capsule with messages for future people was buried, which is scheduled to be opened in 100 years. In it, the thoughts and ideas of contemporary Japanese are collected, allowing the preservation of the cultural heritage of the country for future generations. Deep time repositories represent unique concepts capable of preserving knowledge for millions of years. Despite geological and climatic changes, one of the most well-known projects in this field is the Svalbard Global Seed Vault, which was opened in 2008 on the archipelago of Svalbard. Located 130 meters underground, this repository is protected from potential climatic disasters and nuclear conflicts. It holds over 1 million seeds representing the genetic diversity of plants from around the world. The goal of this project is to ensure that important crops like wheat, rice, and barley can be restored in case of a catastrophe. But what if we could create such repositories not only for seeds, but also for knowledge, cultural heritage, and technologies? Imagine a repository that contains not only seeds, but also records of civilizations, their achievements, languages, and sciences. Such a repository could store physical and digital archives, including books, films, and virtual models that describe key moments in human history. One possible solution could be deep repositories, similar to those being developed in projects aimed at preserving climate and ecosystem data. For example, the Climate Archaeology Project involves extracting and analyzing ice from Greenland, which contains air bubbles that encapsulate the history of the atmosphere and climate over the past 800,000 years. We can envision a repository that stores records of all significant discoveries and inventions, such as the discovery of electricity or the creation of the Internet, for millions of years, so that future civilizations can learn from the experiences of their predecessors. To achieve this, durable materials like titanium or special alloys that can withstand extreme conditions, as well as sophisticated methods of information encoding, are necessary. For instance, in 2002, a group of researchers led by Professor Lars Gudmundsson developed a method for storing data on quartz glass that can preserve information for up to 300 million years. In such a repository, each record would not be just text, but a complex set of knowledge that could be deciphered using future technologies. Given that Earth's history has seen 5 major mass extinctions, such repositories could serve as a lifeline for knowledge that might otherwise be lost in global catastrophes. One can imagine that after the next mass extinction, when humanity begins to rise from the ashes, archaeologists will discover these repositories and open them as treasures that tell the stories of past civilizations. However, if these repositories are poorly designed or improperly located, they could fall victim to erosion, tectonic changes, or even human greed. For example, in the 18th century, many important documents were lost during wars or natural disasters, leading to the loss of entire cultural layers. Preserving information for deep time requires a thoughtful approach and an understanding of the potential threats that such repositories might face. As a result, deep time repositories could become not just museums, but true keys to preserving human experience for millions of years to come. One such project is the long-term storage system, proposed in 2015 by a group of scientists from MIT, which suggests using magnetic nanoparticles to record and store data at the atomic level. The concept of cosmic altruism is based on the assumption that highly advanced civilizations may deliberately leave their knowledge and technologies for future intelligent species, even if they never encounter them. This idea gained prominence through the works of astronomer Carl Sagan, who in 1983 described the possibility of transmitting information about Earth into space in his book Cosmos. One of the most notable initiatives in the realm of cosmic altruism is the Pioneer project, which in 1979 launched 2 spacecraft that journeyed to the stars. On board Pioneer 10 was a golden plaque with images of humans and a map showing our location in the galaxy. This initiative symbolized hope that other intelligent beings might one day find these messages and learn about our existence. In 1992, Voyager 1 was launched, also carrying a golden plaque with musical compositions and natural sounds, further emphasizing the concept of cultural exchange. Some scientists, such as astrobiologist David Blackwood of NASA, suggest that such actions may not be purely altruistic, but also strategic, as technological development could lead to the creation of new forms of life-seeking communication. Research indicates that some civilizations may be so advanced that they can create and leave their achievements as artifacts on other planets, potentially anticipating that these technologies will become available to other intelligent species. For instance, in 1999, physicist Frank Drake proposed the Drake equation, which estimates the probability of the existence of extraterrestrial civilizations, and among the factors influencing this is the possibility of knowledge exchange between different civilizations. In turn, ideas about cosmic altruism can also have an ethical dimension. If a highly advanced civilization is aware of its own impermanence, it may strive to leave a legacy for future generations, even if these generations are on other planets or in other galaxies. This raises important questions about which knowledge to preserve and how it might influence the development of new civilizations. In this context, many researchers, such as astrophysicist Martin Rice, emphasize that such actions can serve not only for information transmission, but also for ensuring the safety of future intelligent beings who may face similar threats, such as ecological disasters or technological mishaps. Consequently, cosmic altruism becomes not just a philosophical concept, but a possible reality that opens new horizons for understanding our place in the universe. Scientific research shows that such initiatives are still in their early stages, and it may take decades, if not centuries, to achieve significant progress in this field. The study of ancient prehistoric civilizations leaves many questions unanswered, prompting us to reflect on what life on Earth might have been like in those distant times. For instance, the Inca civilization, which flourished in South America from the 15th to the 16th century, built an extensive network of roads spanning over 30,000 kilometers, connecting their cities to remote Andean regions. Their engineering prowess allowed them to create terraced fields, capable of sustaining agriculture even in the harsh conditions of high altitudes. This level of organization and technology raises questions about the diversity and advancement of other civilizations that may have gone unnoticed in historical records. We must not forget the Sumerians, who, starting from the 4th millennium BC, created the first writing system and built ziggurats, some of which still stand today. Babylon, one of their great capitals, was renowned for its laws, recorded in the Code of Hammurabi, which laid the foundation for many legal systems still in existence today. This leads us to ponder our place in history and the responsibility we bear for preserving life and reason on the planet. Whether we were the first technological civilization on Earth or one of many, we face challenges that require us to recognize our impact on the world around us. The 18th century saw the beginning of the Industrial Revolution, which fundamentally altered the relationship between humans and nature, creating a new society based on mass production and consumption. However, this revolution also brought environmental problems: air and water pollution, climate change, and species extinction. We live in an era where the need to preserve the planet is becoming increasingly urgent. Humanity must take responsibility for the future to avoid repeating the mistakes of our predecessors, which may have led to the demise of great civilizations. For example, the collapse of the Maya civilization, which reached its peak in the 10th century, was a result of a combination of climate change and human activity, leading to an agricultural collapse.